Welcome to the class. Today we are going to discuss a very important topic, subspace. This is the heart of linear algebra. This lecture is especially designed for semester level examination, and this will also make a very strong foundations for the exams like NET, GATE, JAM, TIFR, ISI, CMI and NBHM. So without wasting the time, let's begin the journey. So what will be the contents of this lecture? So these are the contents of this lecture. At first we will see the introduction, then we will see the applications. After that we will read the definition of subspaces, and then we will solve a lot of problems based on subspaces only. After that we will see the summary, and then we will see the references. By this we will end the lecture. Introduction of subspace. See, I have written this introduction in a very simple language so that you can understand it easily. So just read it at least once. Applications of subspaces. See, in the core areas, subspaces are used in the field of signal processing and communications, in the field of data science and machine learning, and in the field of computer vision and graphics also. And if you are a beginner and you don't know anything about this subject, then you may be amazed that how this subject is going to be used in these things. So don't worry, I am here for you. After completing this series, I will make some videos on these topics also, so that you will be able to understand that how these things are connected to each other. But for now, you have to focus on this concept. Okay, learn the concept in a very simple way. And also you can see that in the broader fields, subspaces are used to study physics and quantum computing, to study the control theory and robotics, and also to study the differential equation and mathematical modeling. And in the advanced field, it is used to study statistics and data analysis, in coding theory and informational theory, and to read functional analysis and modern mathematics also. So this was the very brief introduction of application, right? And I have written here very few so that you can understand the importance of the subject. Now what is the conclusion? The conclusion is that vector spaces describe all of these things. Just go through it at least once. Now let's move to the subject. Definition. What is the definition of subspace? See, till now we know the definition of vector spaces only, that V is a vector space over the field F, and we know that V is a vector space when it satisfies some certain condition, that it should be closed under addition, it should be closed under scalar multiplication, after that it should satisfy 4 conditions here, and it should satisfy 4 conditions here, right? Now what is subspace? So see, suppose you have a vector space. Let's write it name V over F. Suppose there is a vector space. Now you are taking a subset of this vector space. It is W. So what I have said, that suppose there is a vector space. Now you are taking a subset of that vector space. Then what is the next step? Now check if this subset forms a vector space. What I have said, that now check if this subset forms a vector space over the same field F. Over the same field means this field, right, on which V is a vector space, right? What I have said, that now if this subset forms a vector space over the same field, then we will say that this W is a subspace of VF. So this is the concept. What is the concept? That there was a vector space. Now you are taking a subset from that vector space, and now check whether this W forms a vector space or not. And if this W forms a vector space over the same field F, then we will say that yes, this W is a subspace of VF, right? Just you can see that this is the concept like set and subset, right? So this was the basic idea, right? And there a question maybe arises that what will be the what will be the operations for W. So see, I am writing here note. Okay, I am not going to give you a very structured note, right? I am here to make you understand the subject. So see what I have said. Number one, that W should be a subset of a vector space V, right? And secondly, it should form a vector space over the same field F, right? And what will be the condition? See, since VF is a vector space, so there will be some conditions like addition and scalar multiplication, right? So W should form a vector space over the same field F under the same operation which is defined on this vector space, right? I hope I am able to make you understand each and everything, right? So see, this is the official statement that a subset W of a vector space V over a field F is called a subspace of V if W is a vector space over F, right? What does it mean? It means that this was a vector space over the field F, means this line vector space over a field F, and this is W, my subset, this line, right? And it should form a vector space over the same field F, right? Then we will say that this is a subspace, and see, under the same operations, addition and scalar multiplication. Okay, so I hope till now everything is clear, and if not, if you have any doubt, then comment section is only for you. Just ask your doubts in comments. I will make you a reply. Now, here are some catches. What kind of catches? See, by set theory, we know that every set has at least two subsets. One is empty set and the another is the set itself, this one. So if I connect this thing to the subspace, then what results can we get? So see, suppose you have a vector space V over F, and since we know that every set is a set of itself, so V will be the subset of this vector space. Am I right? Yes. So now I am asking you that check whether V means this set forms a vector space or not. Forms a subspace or not. Okay. Check whether this subset V forms a subspace or not. For that, what will you do? You will check that whether that this V satisfies all the conditions of vector space or not, right? But see, by the given condition, we have that V is a vector space, right? So definitely it will satisfy all the properties of the vector space. Okay, so we can say that yes, V is a subspace. Okay, according to the definition of subspace. See, I am proceeding step by step so that you can understand each and everything very easily. So what we get, that V is a subspace. Okay, and there is a special name for this kind of subspace. What? Here V is called a improper subspace. Okay, means every vector space is a subspace of itself. What I said, that what we get, that every vector space is a subspace of itself. Okay, and this subspace is called improper subspace. Okay, so this was our first result. Now we will move. Now what about this one? What about this one? Does it form a subspace or not? So see, empty set. Now if I ask that, check whether that empty set forms a vector space or not, right? So you have a set V over F, you have a vector space V over F, and we know that phi is the subset of V. Okay, Now check whether this phi forms a vector space or not. So to check, we have to check that whether it satisfies all the conditions or not, right? So see, I am saying that it may satisfy all the conditions. What I am saying, listen carefully. I am saying that this phi may satisfy all the conditions, right? But what about identity? Means we know that in a vector space there must exist an identity element, right? There must exist an identity element. Okay, but what is it? It is phi means no element, right? So this is the set of no element. Here is no element. Okay, so where is identity? It means identity is not there. By using this argument that in this set phi there does not exist identity. Okay, by using this statement we can say that yes, this phi is not a vector space. Okay, since it is not a vector space, means not subspace. Okay, so what was our logic? That in phi there is no identity element, right? That's why it will not form a vector space, and that's why it is not a subspace. So what is the conclusion? That in a vector space the set itself forms a vector space, but the set phi will not form a vector space. Why? Because there does not exist identity element. So you can see the importance of identity element in a vector space, right? And what kind of identity element? This is additive identity element, right? This is a very special kind of element. That's why now we are going to make a set of identity element, right? Then we will check that whether this set forms a vector space or not. See, let me change the color. Suppose this is our vector space V over F, right? And this is our additive identity element, right? This is our additive identity element. And we know that in a vector space there is unique identity. Okay, so see, we are taking a set W, right? The set of identity element, right? And it will be a singleton set. Why? Because identity is unique, that's why it is singleton. And this is a subset of a vector space V over F, right? Now I am asking that check whether W forms a subspace or not, right? So check. So this is our set. Now check whether it forms a vector space or not. So does it satisfy the closure under addition and scalar multiplication? Yes. Here is only one element. So if you add 0 plus 0, it will be equal to 0, and this is an element of W. So it satisfies closure under addition. Now if you take any element C from F, right, and if you multiply it with the element of set, what is the element? 0. You will get 0, which is the element of W. Okay, what does it mean? That W is closed under addition and scalar multiplication. And similarly you can check that it will satisfy all the condition. And see, 0 is an identity element, right? That's why identity will not fail. Okay, and similarly you can check that it will satisfy all the conditions under scalar multiplication also. So what we get, that W is a vector space, means W is a subspace. Okay, so there is a special name for this subspace also. What is that name? This 0 is called a trivial subspace, right? So what we get till now, that in a vector space there will be at least two subspace, right? So see, I am writing here result. Okay, always remember it. in a vector space, there must exist at least two subspaces. What are that? One is zero subspaces, right, means the set of identity, and the second one is the set itself, right, and I am representing it with P. So there is a special name for it. This is called trivial subspace, and this is called improper subspace. Okay, and just remember one more thing, that any subspaces other than trivial and improper is called proper subspaces, right? It's called proper subspaces, right? So this is a very famous result. Okay, so always remember it. So what we get, that in a vector space V over F, there is always two subspaces. One is trivial, another is improper, and the rest are proper subspaces, right? So next, here I have written some theorems and results, which is very important. Okay, and I am not going to prove all the theorems at a time. At first we will prove this one, okay, and after that we will solve a lot of problems by using this theorem, and we will prove all of these, right, when it is needed the most. Students, I am advising you that just remember these results. Okay, remember it, just go through it at least once, right? Remember it. Why? Because these theorems are used rigorously to solve the questions of CSIR NET and GATE. Okay, students, till now what we have done, we have taken a vector space V over F, then we took a subset W of a vector space V over F, then we checked that this set forms a vector space or not, and for checking the vector space we have checked all the conditions, right, that it should be closed under addition and scalar multiplication. After that it should satisfy all the four properties and all the four properties. This was the way to check whether that a subset is a subspace or not, right? Till now we have this process to check whether this W is a subspace or not, and student, you can understand that this is a very lengthy process, right? This is a very lengthy process. Students, as we know that mathematicians are the lazy person, right? That's why they were looking for some other way, that is there any other way to check whether that this subset forms a vector space or not, right? And after a long time, finally they have discovered something new. What they discovered? They have discovered that there are three special properties, right? There are three special properties, and if a subset of a vector space satisfies these three properties, then it will also satisfy all of these properties. Understand? I hope I am able to make you understand. So now the question arises that what are those three properties? Okay, so this is our next theorem. Okay, see, I am teaching each and everything step by step, right, by connecting the basic things. Okay, and you have to learn like that, only then you will be able to find the beauty of mathematics. Okay, so see, this is our theorem. What it is saying: state and prove the necessary and sufficient conditions for a non-empty subset W of a vector space V to be a subspace of V. Right. So at first we have to state the theorem. Right. So what is the statement? So see, this is the statement, and this is a very special thing. We call it by standard subspace test, right? And we will use it rigorously throughout our lecture, right? So see, what is the statement? The statement is saying that let W be a subset of a vector space V over F. What does it mean? It means this is my vector space V over F and W is a subset of it, right? After that, then W is a subspace of V, means this W is a subspace of V if and only if. See, if and only if means both sided condition, right? So see, then W is a subspace of V if and only if zero vector condition, means 0 belongs to W, right? So what is the first condition? That 0 vector must be belongs to W, and the second condition is closure under addition, right? It means that if U and V belongs to W, then U plus V should also belongs to W, and the third one is closure under scalar multiplication, right? Means this one, if C belongs to field and U belongs to W, then CU must be belongs to W, right? So this is our special three condition, that if these conditions satisfy, then W will be a vector space, hence W will be a subspace, right? So see what we get. We get that if we wanted to check whether that a set is a vector space or not, we have to check closure under addition and scalar multiplication, then 4 properties, and then 4 properties, right? But if your set is a subset of a vector space, right, and you want to check whether that this subset forms a vector space or not, then you have to check only these three conditions, right? So see, here is a catch: don't mix the thing, right? What is the catch? See, so I have seen many students got confused that when they have to use the vector space test and when they have to use the subspace test, right? So for that I am writing here a note for you, right? Just go through it at once, right? I hope you will be able to understand each and everything, right? And if you find any problem or if you have any difficulty related to the subject, right, then student make comment, right? I will make you reply. Okay, now we are going to prove the theorem. So see, at first we have to write the statement, right? So what was the statement? This is our statement, right? So it is if and only if case, right? So we have to prove the both side. Okay, so just see how I am approaching. Okay, student, basically you have to learn the approach. Okay, see what is given. Whenever there is a theorem, at first write given that. Okay, after that write the data what is given to you, right? So what is given? It is given that let W be a subset of a vector space V over F. What does it mean? It means that W is a subset of a vector space V over F. This is our first data. Okay, and what is the second given data? Second data is W is a subspace of V, right? It means W is a subspace. W is a subspace. Okay, and what we have to prove? What is our claim, right? What is our claim? We have to prove that these three conditions hold, right? So write them. We have to prove, at first we have to prove that 0 vector belongs to W. This is vector, right? And second one, it is closed under addition. It means U plus V will belongs to W. and the third one is C into U. Third one is Cu belongs to W. Right. So see how to think, right? So what we have given this one, we have to prove these things, right? And till now what we know? Till now we know only the definition of vector space, right? By using the definition of vector space only, we will prove this one, right? So see, right, proof. So see what is given, that this is our V over F, right? And this is our W. Okay, W is a subspace, and the second condition is given that W is a subspace, right? So right, since W is a subspace, what does it imply? We know that subspace is nothing but a vector space. It implies that W is a vector space, right? I hope till now everything is crystal clear, right? And we know that a set forms a vector space only when it satisfies all the conditions. What condition? It should be closed under addition, it should be closed under scalar multiplication, it should satisfy all the properties here, and it should satisfy all the properties here. What was the properties? The first one was commutative, associative, identity, and inverse, right? So in the condition, what is given? W is a vector space. What does it mean? That W will satisfy all of these conditions, right? So see, so since W is a vector space, so it will satisfy all of these conditions. So now you can see that since W is a vector space, so it will satisfy this condition also and this condition also, right? So from the given condition, now you can write like that: since W is a vector space, right, it implies it will satisfy closure under addition and scalar multiplication also, right? So finally we get that since it is closure under addition, so it will satisfy this condition. Since it is closed under scalar multiplication, it will satisfy this condition, right? So two conditions we have proved, right? So you can write it proved, right? So see how I am using the logics and how I am connecting, right? So this is the work of mathematician, that from the given data, how he is reaching to his claim. Okay, so see what is remaining now. See, this one proved. Now the remaining is this one, right? And we know that in a vector space, additive property satisfied, additive identity property satisfied, right? That's why there will always exist a zero vector, right? There exists zero vector. Only then the additive identity will work, right? Right, so write it: since W is a vector space, right, so it will satisfy additive identity property, satisfy additive identity, right? And to satisfy the additive identity, there must exist a zero vector, right? It implies 0 must belongs to W, right? Only then the additive identity will satisfy, right? What was the additive identity? This one, right? So finally this is also proved that 0 belongs to W, hence this one is proved, right? So this is the way to think. Okay, now the second part, we have proved this one, now we have to prove this one, right? So now we will let this one and prove this one, right? So in next page, right, given that, okay, So see, let me change the color. Given that what is given, the first thing is that W is a subset of a vector space V over F, right? Then the second one is 0 vector belongs to W. The third thing is it is closed under addition, right? And the fourth thing is it is closed under scalar multiplication, right, where C belongs to the field. Okay, and what is our claim? See, what is our claim? These were given data, right, and this is also given. Okay, and what is our claim? Then W is a subspace of V, right? So what is claim? W is subspace of V over F, right? So proof. Let me change the color, right? See, we have to prove that W is a subspace of V. Okay, so we know that to prove that W is a subspace, we have to prove that W is a vector space, right? So write it. To prove that W, which is a subset of V over F, is a subspace, what we have to show? We have to show that W is a vector space, over F, right? See, I am using just the basic things, right? Whatever I have taught to you, right? Whatever I have teach you, right? Basically, just forget the grammar, focus on the subject, right? So when it will be a vector space, when W will satisfy closure under addition and closure under scalar multiplication, when it satisfies commutativity, associativity, identity and inverse under addition, and it will satisfy these conditions, that 1 into V equal to V, right? AB into V equal to A into VB, right? Third one, A of U plus B, wait, I am taking U plus V, U plus V equal to AU plus AB, and the last one is A plus B into U equal to AU plus BU, right? So we will say that W is a vector space when it will satisfy all the conditions, right? So see what we have given. We have given that 0 vector belongs to W, right? So since 0 belongs to W, it will satisfy identity, right? Since 0 belongs to W, so if you add any vector with this identity, you will get that vector as a result. What does it mean? Means identity satisfied. So from the given condition we get that identity satisfied. Now there are many remaining conditions. Let's check it, that how can we prove it. Okay, so right here, since 0 vector belongs to W, it implies that additive identity holds. Okay, and now what about this? See, this is also given. What is given? That U plus V will always belong to W. It means that additive identity will also satisfy, right? And see, what does it mean? It means that scalar multiplication will also satisfy, right? So from the given data we can see that from the given data, closure under addition and scalar multiplication satisfied, right? So 3 condition has been satisfied. Now there are remaining these conditions, right? So see, I am using a result here. What kind of result? See what is W? This is my V over F, right? According to the given condition, this is my V over F. And since V is a vector space, so it will satisfy all the conditions, right? Now just forget about W. Since V is a vector space, so it will satisfy all the condition. Means V will satisfy commutativity, P will satisfy associativity, and all of these conditions, right? And since W is a subset of V over F, right? So it will also satisfy commutativity, associativity, identity, right? And all of these conditions, and all the conditions under scalar multiplication, right? So we can write here that, see, since VF is a vector space and W is a subset of V over F, it implies that W will satisfy commutativity, associativity, identity. Okay, we will talk about inverse later, okay, because there is a catch, right? Then W will satisfy commutativity, associativity, identity, and all the conditions of scalar multiplication, right? So this and this thing, these are satisfied and these are also satisfied, and we are saying that this will satisfy by using the subset property, right? I hope I am able to make you understand. I know it is taking time, but don't worry, this will make your basic and thinking very strong, right? Which will be beneficial for you in future, right? So don't be frustrated, don't lose your patience, okay? So now what about inverse? See, why I am saying that inverse is something different. See, this is my V over F vector space, right? And this is my W, right? Subset. Now see, we know that for each element of V there will be a additive inverse, right? Means if here is any element, right? If here is any element, then its inverse will also be inside V, right? Yeah. And see, if we choose any element from here, right? So if we choose any element from W, then still it will be a member of V, right? And since it is a member of V, it implies that the inverse of this element will be exist in this V, right? See what I am saying, I am writing, okay, so that it will be helpful for you. And see, since VF is a vector space, right? It implies additive inverse will exist for all elements of V, right? Now let's choose an element from, let us choose an element U, let it be U, right? Let us choose an element U from W, right? And since it is an element of W, it implies that U will be also an element of V, right? And since U is an element of vector space VF, since U belongs to VF, implies additive inverse will be also there, will be in V, right? But the question arises that they are saying that the inverse element will exist inside V. Is there any guarantee that the inverse will exist inside W? What is my question? Is there any guarantee? Is there any guarantee that inverse will be inside of W, right? If you can show that yes, inverse of U exists in W, what does it mean? It means that inverse of each element of W exists inside W, right? So we will be able to say that yes, W is closed under additive inverse also, right? For that we are going to prove, right? So see, how can we prove that inverse of this element exists inside W? So see, we know that F is a field, right? And in a field, -1 is always there, right? And we know that W satisfies Cu belongs to W, right? Scalar multiplication property it satisfies. It is given over here, right? So by using that we are getting, right? So we can choose any number, right? So let C equal to -1. C is from the field and we can choose any number from field, so we are choosing -1, right? So if you choose -1, then what it will be? It will be -1 into U, which is equal to -U, right? And we know that Cu always belongs to W. That's why this Cu means this -U will also belongs to W, right? It implies that for all U there exists -U belongs to W, such that I am writing here, such that U plus -U will be equal to 0. What does it mean? That inverse of each element of W exists in W. It means that it is closed, means W is closed under additive inverse 2, right? Hence all the properties has been satisfied. See, by logically I have proved that W satisfies all the conditions of the vector space. Hence W is a vector space, right? It implies W is a subspace, right? So this is the steps, this is the approach to connect, to prove the theorems, right? Just go like that, right? Only then we will be able to solve the new problems related to net and gate. Okay, so see, now we are ready to solve the problems of vector spaces, and believe me, we are going to solve a lot of problems, right? So see, our first question, what it is saying? It is saying that S be the subset of R3 defined by this one, so that S is a subspace of R3. And we know that how does this R3 looks like? R3 is equal to, it is of the form XYZ such that X, Y, Z belongs to R. Okay. Now see what they are saying, that S is a subset of R3. What does it mean? That this is my R3, right? And this is my S. And we know that R3 forms a vector space over R. We have seen it in the previous lecture, right? So see, now we have to check that whether this subset forms a vector space or not. So what we have to check? Basically we have to check three conditions, right? That we have to check that zero vector belongs to S or not, then is it closed under addition and scalar multiplication or not, right? So see, what is S? S is given by S is equal to X, Y, Z belongs to R3 such that Y equal to Z equal to 0, right? So if Y and Z will be equal to 0, then how does the elements of X, Y, Z looks like? Then the elements of X, Y, Z will be looks like this, sorry, X 0 and 0, right? Where X will belongs to the real number, right? So basically this is our set S, right, according to the given condition. Okay, so now check whether this zero vector belongs to this set or not. Okay, so see, here x is from real number, right? So we can choose that x is equal to 0, right? And now if x is equal to 0, then this and this, right? This will also belong to the s. Why? Because see, we have to see that what is here. We have to only check that y and z should be 0, right? See, y and z is 0, right? And x should vary. Okay, so we are choosing x equal to 0, so these elements belongs to s, right? And see, this is basically 0 element, right? This is 0 element, right? Or better to say that this is additive identity element, right? So the first condition holds. Okay, now the second condition. What is second condition? Closure under addition. Closure under addition. So see, let us choose any two arbitrary elements of S, right? So let and y00 belongs to S be arbitrary elements, right? So we have to check whether their addition belongs from S or not, right? So see, x00 plus y00, what it will be? It will be equal to x plus y, right? Tuple wise addition, x plus y, then this tuple plus this tuple means 0 plus 0, it will be equal to 0. Then again 0 plus 0, it will be equal to 0. So we get this one, right? So what is at x and y? X and y are from real number, right? And so x plus y will also be from real numbers, right? So basically this is a real number, right? So see, what was our s? Our s was that here will be, in the first position there will be a real number and the rest will be 0. So see, here is a real number and the rest is 0, right? What does it imply? It implies that this belongs to S. So what we get? We add two elements and we get that their addition is from S. What does it imply? It implies that S is closed under addition. Now the third property, closure under scalar multiplication. See, closure under scalar multiplication. So how can we prove? See, let us choose C belongs to R. Basically this is field. Okay, C belongs to R, be arbitrary, and x comma 00 belongs to R3. Okay, x comma 00 belongs to R3. Basically this is the set of vectors. Okay, be arbitrary. Now multiply it. Since this is an element of field, right, and this is a element of vectors, so their multiplication will be called as scalar multiplication, right? So it will be equal to C into x, C into 0 will be 0, C into 0 will be 0, right? And since, and we know that their multiplication will belongs from real number, right? Why? Because x is from real number, right? So this is a real number. So see, this is a real number and the rest things are 0. What does it mean? It means that this will also belongs from S. So what we get? That scalar multiplication is also from S. So the third condition satisfies, right? So you can write that therefore by subspace test, what was that, right? Let me check again. What was that? Subspace test, standard subspace test. Sorry, wait. So by a standard subspace test, we can conclude that S is a subspace of R3, and this is our result, right? So see, what was the question? That show that S is a subspace, right? So we proved that S is a subspace, right? So next, what is this? Let T be the subset of R3 defined by this, so that T is a subspace of R3. What is the condition? X equal to Z equal to 0. Okay. So basically we have to check like this one, right? If it will be X equal to 0, right? So X, Y should vary, yeah. Then Z equal to 0, right? So this is our set such that Y belongs to real number, right? So you can do it. It is your homework. Okay, and if you find any difficulty, then comment. I will make a reply. Okay. Next, what it is saying that same question. What it is saying that X equal to X and Y will be equal to 0, means 0 0, and Z should vary, right? So Z belongs to R. This will be also your homework. Do it. These are the similar questions, right? So now I am giving you a question, right? See, wait, I am saying here there are spaces. See, suppose I am changing the conditions for a time, right? If I change like U equal to X, Y, Z belongs to R3, right? Such that X equal to 1, right? So check whether it forms a subspace or not, right? So see, how does the elements of U will look like? It will be like this: 1 0 0, right? Belongs to R3. Okay. Now check whether this forms a subspace or not. So check the first condition. Does the 0 belongs here? Means does this element will be from this set? So no. Why? Because in this set there are elements whose first one is 1, right? But see here, first one is not 1. That's why this is not from W. Sorry, this is not from U. That means that 0 does not belongs to U, right? Since it does not satisfy the property of standard subspace test, so we can say that this is not a subspace, right? And you can see that it will also satisfy the closure under addition. Why? Because if you add this element, you will get 2 0 0, right? And which is still not an element of it, right? And similarly you can check that scalar multiplication will also fail, right? So do it yourself. I have already said whatever is there, right? Now you have to do it in your notebook, right? So that you will have a proper note at the end of the lecture, right? So next, what it is saying? It is saying that let S be the subset of R3 defined by this. Now we have to check whether this forms a vector space or not. So what is the condition? X square plus Y square equal to Z square. So write it: X, Y, Z belongs to R3 such that X square plus Y square equal to Z square, right? So we will check the first condition, that whether this 0 vector belongs to S or not. See, if we choose X equal to 0, Y equal to 0 and Z equal to 0, right? Now check whether this will satisfy this condition or not. So see, X square means 0 square plus Y square means 0 square equal to 0 square. See, 0 square plus 0 square equal to 0 square. So see, this condition holds, right? X square plus y square equal to 0. What does it mean? It means that 0, sorry, it means that 0 0 0 belongs to S. Yes, the first condition has been satisfied, right? Now the second condition. What was the second condition? Closure under addition. See, we will choose two elements, right? So let x1 x2, sorry, let me write like that, x1 y1 z1 and x2 y2 z2 belongs to S, right? See, we are assuming that these two elements are from S, right? Since this is from S, so it will imply that this will satisfy this condition, right? So it will be x1 square plus y1 square, it should be equal to z1 square, and similarly x1 x2 square plus x2, sorry, y2 square plus y2 square equal to z2 square, right? Since these are from the set S, so it will satisfy this condition, right? Give it name 1, give it name 2. Now check the addition, right? Now add them. So x1 y1 z1 plus x2 y2 z2, it will be equal to x1 plus x2 y1 plus y2 and then z1 plus z2, right? So what we get, we have added two elements. No, at first we have taken two arbitrary elements from S, now we are adding it and we get this one, right? So now we have to check that whether this belongs from this set or not. For that we have to check this condition. If this will satisfy this condition, if this will satisfy this condition, then we will say that yes, this is from the set S. Otherwise this will not belong to the set S, right? So check the condition. Checking the condition. Checking the condition. I hope I am able to make you understand the subject, right? If not, then comment section is only for you. Comment. So check the condition. What was the condition? X square plus y square means this square of this, means this one square plus this one square, right? So x1 plus x2 square plus y1 plus y2 square, right? It should be equal to z1 plus z2 square, right? See, I am writing so that it will help you to write in your semester examination, right? So see what it will be. It will be equal to x1 square plus x2 square plus 2x1 x2 plus bracket y1 square plus y2 square plus 2y1 y2, and this is equal to z1 square plus z2 square plus 2 z1 z2. Okay, now see, we can write it, rearrange it, x1 square plus y1 square, this one and this one, this two, right? So x2 square plus y2 square, right? Now take 2 common, so what will you get? You will get x1 x2 plus y1 y2, and this will be equal to z1 square plus z2 square plus 2 z1 z2, right? Now see, it implies, see, from equation 1 what we have, this one, right? So x1 square plus y1 square, it will be equal to z1 square from the given condition, right? Plus x2 square plus y2 square, it will be equal to z2 square, okay? Plus this one 2x1 x2 plus y1 y2 equal to z1 square plus z2 square plus 2 z1 z2. See, we get this one, okay? So see, when it will be equal. So it will see z1 plus z1 square plus z2 square, z1 square plus z2 square, right? Sorry, z2 square. Okay, and it will be equal if and only if these two conditions will be equal, right? So right, when it will be equal when x1 x2 plus y1 y2 will be equal to z1 z2, right? Only then it will belong to the set S, right? Now the question arises that is it always true or not, right? So let's check it. For that, let us choose x1 equal to 1, x2 equal to 0, and y1 equal to 0 and y2 equal to 1, and this one, right? Now check x1 into x2, right, means 1 into 0, it will be equal to 0, plus y1 into y2 means this one into this one, this is equal to 0. It should be equal to z1 into z2. What is it? It is 1 into 1 means 1. So see, 0 is not equal to 1. What does it mean? It means that this condition is not always true, right? This is not always true. What does it mean? It means that addition, closure under addition fails. It means that this does not belongs to S, right? Why? Because this does not satisfy this condition, right? So the addition does not belongs to S. What does it imply? It implies that S is not closed under addition. That's why this is not a subspace, right? So in your semester exams you have to write like that. Only then you will get the full marks, right? And you have to remember an example, or you have to give an example. You can think of other examples also. Okay, so see whatever I have discussed, this is for your semester exams, right? And suppose if the same questions comes in your NET or GATE exam or IIT JAM level examination, then what will you do? And at that time, if you proceed like that, then it will be a very time taking process and lengthy process, right? For that, what you have to do, if you get this kind of questions, always try to find an example, right? So if you want two elements from here, then what it will be? You can see that if you choose x equal to 1, y equal to 0, z equal to 1. So see, x square plus y square equal to z square means x square plus y square equal to z square. Yes, this condition satisfied. Choose another element. It will be x square y square z square. So it will be 0 square plus 1 square equal to 1 square. So see, again this satisfies this condition, means we got the two elements, right? Now add it. If you add, then what will you get? You will get 1 1 2, right? So now check whether this satisfying this condition or not. So check, x square means it will be 1 square plus y square means again 1 square. It should be equal to z square means 2 square. But we know that 1 square plus 1 square equal to 2 and 2 is not equal to 4, right? So that's why this does not belong to S, means closure under addition fails. Okay, that's why this is not a subspace. If you get the question in your competitive level exam, then you have to solve like this. Okay, just to think like this. Okay, and if you get in your semester level examination, then you have to write like that. Okay, so I hope I am able to make you understand, right? And if not, then comment section is only for you. Write your comment, ask your doubts. I will be there to solve it, right? So next, what it is saying? It is saying that let V be the vector space over a field F and alpha belongs to V, so that this W forms a subspace of V. So let's check the condition. What is given? It is given that W equal to C alpha such that C belongs to F and alpha is from V. Now see, here alpha is a fixed vector, right? Here alpha is fixed. So at first we will check that 0 belongs to it or not, right? So since C is from F, right, and F is a field, so definitely 0 will be there, right? So choose C equal to 0. Choose C equal to 0. What does it imply? It implies that C into alpha means 0 into alpha, and we know that 0 into alpha it will be equal to 0 vector. Okay, so C, and we know that C alpha are the elements of W. It means that this into this will be equal to this, and this is the element of W, right? I hope it is clear. So the first condition holds. Now check the second condition. So choose any two elements from this set. So let C alpha and C alpha. See, here is something different. What is the difference? See, here alpha is the fixed element, right? Here alpha is fixed, right? But we want two vectors from this set, right, to check this condition, right? So how can we get the different vector? Only when we will change the scalars. Let it is C1 and it is C2, right? It belongs to W such that C1 is not equal to C2. Clear? Good. See, this vector is same, right? But when you multiply it with the different scalars, then this will be different vectors, right? So by using this concept I am going to prove it. Okay, so these are my two vectors from W. Now check the second condition. What was the second condition? C2 alpha, right? Now check whether this belongs to W or not. So see, we can take common C1 plus C2 into alpha, right? And what is C1 and what is C2? C1 is from the field, right? And we know that see, C1 and C2 are from fields. Okay, I am writing. And we know that F is a field, and by the property of field we know that it is closed under addition. It means C1 plus C2 will also be from the F, right? What does it mean? This is a single element, right? When you add, you will get a single element, and that single element will be from F, right? So an element from F into alpha, right? It is of the form this, right? So what does it mean? It means that this belongs to W. What does it mean? It is closed under addition 2, right? Hence the second condition also satisfied. Now check the third condition. What was the third condition? Scalar multiplication, right? So let us choose, let C alpha belongs to W. We are choosing a vector from W, right? Now choose a scalar from F, right? Let C alpha belongs to W and K belongs to F, right? And now check the scalar multiplication. So this is our K into the element of W, right? What it will be? By the associative property we can write Kc into alpha, right? And see what it is. Here C is from F, right? And here K is from F. And we know that it is closed under multiplication. F is closed under multiplication also, right? That's why this will be from F, right? So see, an element from F into alpha, right? So it is of the form this. It means that this is closed under scalar multiplication 2, right? Hence it satisfies all the conditions. Therefore W is a subspace proved, right? So next, what it is saying, let V be the vector space over a field F and alpha beta belongs to V, so that this set forms a vector space of V. What is W? W is equal to of the form C alpha plus D beta such that C and D are from F, and alpha and beta are from V, right? So now we will check three conditions. So condition number 1, we have to check the zero vector, right? So we know that 0 is always there in a field, right? So if we choose C and D is equal to 0, right, then what will we get? Then we will get 0 scalar into alpha vector plus 0 scalar into beta vector, right, which will be equal to, see, 0 into alpha, it will be 0 vector, plus 0 into beta, it will be 0 vector, and 0 vector plus 0 vector, it will be equal to 0 vector, right? So 0 vector belongs to W, right? So the condition 1 holds, right? Now the second condition. So now if you have not watched the lecture of vector spaces, right, then you may be confused that what is this, how is it coming, right? And if you are facing such kind of difficulties, then please go back to this lecture, right, and see the theorems, right? This is the first theorem which I have proved after the definition in that lecture, right? So their timestamps has been given to you, right? Just check the time and go to this page, okay, and learn it. So now, see, now we have to check the closure under addition, right? So choose two elements, let C1 alpha plus D1 beta, right, and C2 alpha plus D2 beta belongs to W, right, where C1, C2, D1, D2 is from F, right? Then add them. So if you add them, it will be C1 alpha plus D1 beta, right, plus C2 alpha plus D2 beta, right? Now check whether this addition belongs to W or not, right? So see, now rearrange it. What will you get? You will get C1 alpha plus C2 alpha plus D1 beta plus D2 beta, and which will be equal to, take the common, it will be, wait, it will be C1 plus C2 into alpha plus D1 plus D2 into beta, right? And we know that C1 and C2 are from fields, right? And we know that field is closed under addition, right? So it will imply that since F is closed under addition, right, so F is closed under addition, right, so it will imply that C1 plus C2 will be from the F, right? Similarly, D1 plus D2 will be also from F, right? So what we get? We get that this is of the form this, right? So it implies that this will belongs to W also. Hence the second condition holds, right? See, I am writing in such a way that if you write these things in your semester exams, then you will get full marks, right? And you have to learn that how to deal with the pure mathematics and how to write the proofs, right? So next, what is remaining now? The remaining condition is scalar multiplication. So see, how can we prove? So let any element, let, what is the form? C alpha plus D beta, right? Let C alpha plus D beta as an element of W be arbitrary, right? Now choose any scalar, choose K belongs to the field F, right? Now check the scalar multiplication, K into the vector. What is the vector? The vector is of the form this, right? Now see, if you multiply, then what will you get? See, there was a property of vector space, right, that it was A into x plus y, right? What it will be? It will be equal to ax plus ay, right? By using this result, we will get here that k into C alpha plus k into d beta, right? And now there was another property that AB into x is equal to A into bx, right? So this is of the form this, so we can write it. So write it, it will be equal to Kc into alpha plus Kd into beta, right? So see, K is from F, right, and C and K is from F, and C and D is from F, right? So their multiplication will be also from F. Why? See, I am writing here Kc and Kd will be from F. Why? Because F is a field and F is closed under multiplication, right? So this will be from F and this will be from F, and this is of the form W, right? So it implies that this will also belongs to W, hence the third condition is also satisfied, right? So we can write the conclusion like that. So therefore, by standard subspace test, we can conclude that W is a subspace, right? So if you have any doubt, any question, then comment section is only for you. I will make you reply, right? So next, what it is saying? It is saying that let V be the vector space over a field F, and alpha 1, alpha 2, dot 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 alpha r from V, so that these forms are subspace of V, right? So see, this is nothing but just the extension of this, right? Here was two vectors, right? See, here are r vectors, right? So this is same, okay? So this will be your homework, right? Prove it. I hope you can do it. This is very easy. Next, what it is saying? It is saying that examine whether the following sets are subspaces of R3 or not, and these are my sets. Now we have to check whether that this set satisfies all of the three conditions or not. So students, this is a special kind of question, and you can see this type of questions in your competitive exam like JAM, NET and GATE, right? And believe me, this is 3 to 4 seconds questions. You can get the answer in 3 to 4 seconds, right? And if you are preparing for semester exams, then don't worry, I will show you that how to write in semester level examination, right? So basically here are some tricks. What are the tricks? These are the tricks, right? So just forget these things right now. I am going to explain it, right? What it is saying? It is saying that if you have any equation, right? If you have any linear equation like ax plus by plus c of this form, right? If you have any linear combination, right? Or if you have any linear equation, right? And their RHS side is equal to 0, right? Then it will form a vector space, right? And if you have any linear combination and RHS is not equal to 0, right? Here this is not equal to 0, right? Then this will not form a subspace, right? And if you find any equation which is non-linear, right? Like there is, if in any equation there is x and y, this is non-linear, right? So it will not be a vector space, right? If in an equation there is x square, right, then it will be not a vector space, right? Or it will not be a subspace, right? Or if you see that in any equation there is sin x, then it will not form a subspace, right? Why? Because these are non-linears. And similarly there will be many things, right? So these are the key ideas, right? What are the key ideas? Now read it. If you find an equation which is linear, right, and the RHS side is 0, then it will be a subspace, right? See, the question may be like that ax plus by equal to c, right? So what is the first step? So at first try to write all the things at your RHS, right? Let it be cz, right? This will be constant otherwise, okay? So it will be minus cz, it will be equal to 0, right? Now see, we are getting this form, right? So be aware about this thing, right? So if you find any equation which is linear plus their right hand side is 0, then it will form a subspace. And if you find the equation which is linear but RHS side is not 0, then it will not form a subspace, right? And if you find any equation which includes some non-linear terms, then it will not form a subspace, right? Why? Because closure under addition maybe fails, right? So see, I will show that why this will satisfy all the conditions and why this will not satisfy all the conditions, right? So see, now we are solving as a competitive level examination, right? See what it is. This is our subset, right? S is this subset, and see the condition x equal to 0. So see, this is linear equation and right hand side is 0. What does it mean? It will form a subspace, right? And what is this? Left hand side is linear but the right hand side is not equal to 0, right? It means that it will not form a vector space. Similarly, you can see that this is my non-linear term, right? So it will not form a subspace, right? Similarly, you can see that this is my linear combination, means this equation is my linear and RHS side is 0. So yes, it will form a vector space. And see, RHS side is not equal to 0, it will not form a vector space. And see here, this is my linear combination or this is my linear equation and RHS is 0. Yes. Now check this one. This is linear equation, RHS is 0. Yes, this will form a vector space. And if it was given like that, this will be equal to 1. So see, this will satisfy, but this condition will make problem. That's why this will not make a subspace, right? So all the equations should satisfy these conditions, right? Only then you will be able to say that yes, this set is a vector space or subspace. And see here equation is linear, yes, RHS is not 0, right? So it will not form a vector space, not need to check further, right? So see, this is the same, so this will not form a vector space. So see, in between 3 to 4 seconds you can get the answer in your competitive level examination, right? Now why this is not forming a vector space, right? Why these are not forming a vector spaces? So what is the reason? So to know the reason, you have to enter to the semester level examination thought, right? So now we are going to write the proof, right? Or we are going to solve the problem. So see, what is the first condition? This is S equal to, wait, let me erase it first. Oh, wait. What is it? That S is equal to of this form. So you can see that x is 0, right? And yz may vary, right? So this is of the form this, and if you choose any other vector, right? So see, 0 will belongs here. Yes, if you choose y equal to 0 and z equal to 0, right? So 0 vector will be from this set, right? So condition 1 satisfied, right? And if you choose any two vectors, right? If you are choosing 0 y1 z1, right, plus 0 y2 z2, what it will be? It will be equal to 0 y1 plus y2 and y1 plus y2 and z1 plus z2, right? So see, this will be also from S, right? Why? Because the first one is 0, x equal to 0, right? And the remaining are these things, okay? So similarly, you can see that if you multiply with C, then you will get that, yeah, still the first one will be 0. That's why the third condition will also satisfy. So yes, this is a subspace, right? What about this one? See, choose any element. Let us choose 1 y z, right? This is our element. So see, check whether the 0 vector belongs to it or not, right? So if we choose y equal to 0, z equal to 0, see, this is not 0 vector, right? Not 0 vector. And you can see that you will never find a 0 vector for this condition. So we can say that since 0 vector does not belongs to W, right? So the condition of subspace will not hold. Why? Right? So now the second condition, what it is? X into y equal to z, right? We have to prove it, right? So I will prove. Let me discuss all of these things first, right? What it is saying that x plus y plus z equal to 0, right? So you can see that yes, 0 vector will be there. If you choose 0 0 0, right? So see, this will satisfy this condition. Add them, you will get 0. So the first condition solved. Now the second condition, you can see that check any two elements, right? So x1 y1 z1 plus x2 y2 z2, right? Add them, what will you get? You will get x1 plus x2 y1 plus y2 z1 plus z2, right? So now we have to check whether that this belongs to S or not. So to be in S, it has to satisfy this condition, right? So add all of them, what will you get? You will get x1 plus x2 plus y1 plus y2 plus z1 plus z2, right? Now rearrange it, what will you get? x1 plus y1 plus z1 plus x2 plus y2 plus z2, and we know that this is equal to 0, right? So this is 0 plus 0 is equal to 0. So yes, this is in S, this belongs to S. It means it is closed under addition true, right? So similarly we can say that it is closed under scalar multiplication also. You can check, right? So it will be a subspace, right? Now see this one, see 0 vector will be not there, right? 0 0 0 is not belongs to S, that's why this is not a subspace. Similarly you can see that yes, this will form a vector subspace, right? And this will not form a subspace. Okay, so this is the reason that why these conditions are used. And remember, these are not theorems, right? These are not any theorems. These are especially observation, right? Observations and result, right? So in an interview, if someone asks that why this is not a subspace, then don't give the logics like that, right? Then you have to tell that this does not satisfy the zero vector property, right? This will not satisfy the additive property and scalar multiplicative property, right? So in an interview you have to tell like that, okay? But in the competitive level examination you have to remember this thing just to save your time, right? Now I am going to prove this one, and for the semester level examination I will prove this one, right? I will give the solution of it so that they will understand that how to write the mathematical proof. Okay, so see, at first we are going to prove this one, that x is equal to this one, xy equal to z. So see, what is it? It is 3. Okay, so see, 1 2 3, right? S equal to x y z belongs to R3 such that xy equal to z, right? So see, first condition, that does 0 belongs to it. So if we choose x equal to y equal to z equal to 0 vector, right? So it will be this, right? And you can see that x into y means 0 into 0 will be equal to 0, means z, right? So it satisfies this condition. What does it mean? It means that 0 vector belongs to S. So the first condition satisfies, right? Now the second condition, what it is? Closure under addition, right? So see, let us choose two elements, right? So let x1 y1 z1 and x2 y2 z2 belongs to S, right? So what it will imply? It will imply that x1 into y1 will be equal to z1 and x2 into y2 will be equal to z2, right? Give it a name, let it is equation 1 and it is equation 2. Now add them. So if you add, then what will we get? We will get x1 y1 z1 plus x2 y2 z2, which will be equal to x1 plus x2 y1 plus y2 and z1 plus z2, right? Now the question arises that whether this element belongs to S or not, right? So to be in S, it has to satisfy this condition. So check whether this satisfying that conditions or not. So checking the condition, right? So let us check. X into y, what does it mean? x1 plus x2 into y1 plus y2, and it should be equal to z1 plus z2, right? So break it. What it will be? It will be x1 y1 plus x1 y2 plus x2 y1 plus x2 y2, which will be equal to z1 plus z2, which will imply that, see, what we have, x1 y1 x2 y2, right? So see, x1 y1, where is this x1 y1 x2 y2, what it will be? It will be equal to z1 and z2. So z1 plus z2, what are the remaining conditions? Plus x1 plus y2 plus, sorry, this is not plus, this is x1 y2 plus x2 y1, which will be equal to z1 plus z2, right? Now see what we get. We get that this is equal to this one, right? And see, this is my z1, this is my z2, right? So this is my z1, this is my z2, and we can see that with this element these are same, right? And we are adding something with it, right? So what does it imply? It implies that this will be not equal to this, right? Generally this does not hold, right? Generally this is not true. This is not true. Why I am saying that? See, I am giving you an example, that suppose we know that 3 is equal to 3, right? So if we add anything here, suppose I am adding 1, right? So will it be equal to 3? No. Why? Because it is 4 and it is not equal to 3, right? So see, these are same and we are adding something to it, so the equation will not hold, right? Similarly, this is equal, these two things are equal and we are adding something to it, yeah. So this is not true. What does it mean? It means that this does not belongs to S, means closure property fails. Closure of addition fails. That's why not a subspace, right? So this is the way to write in your semester level examination, okay? And solve this thing also, right? See, as we have proved that this will satisfy this condition, x1 plus y1 plus z1 equal to 0, x2 plus y2 plus z2 equal to 0. From here we get from here that since x1 y1 z1 belongs to S, it will imply this condition, means x1 plus y1 plus z1 will be equal to 0, and similarly x2 plus y2 plus z2 will be equal to 0, right? So by using this condition here we are getting here, right? So I hope each and everything is clear, right? So what about this thing? So shall I need to prove it or not, right? So I am giving it homework, right? This is your homework, and if you find any difficulty, then ask your doubt in your comment, right? I will make you reply, okay? So let's move, and always remember this thing, this will save you a lot of times in your competitive level examination, right? So now I am giving you some results, right? Just go through it. It will give you an idea that, see, I have written here expression and conditions, right? And see, is it linear or not, and what is the shortcut, right? So you can see the, just go through the non-linear terms, right? See, this is non-linear, so this is not subspace. This is non-linear, that's why this will not be a subspace. Similarly, you can say that 1 by x, see, this is non-linear. Why? Because if you simplify, what will you get? LCM will be x, and 1 plus xy equal to 0, right? And we know that xy plus 1 is equal to 0, right? So see, this is non-linear term, right? So this will not be a subspace. Similarly, you can see that this will be, multiply it, what will you get? You will get y will be equal to xz, right? So this is non-linear term, so this will not be a subspace. Since here is sin x non-linear term, e to the power x non-linear term, log x non-linear term, x square non-linear, xyz non-linear. That's why this will not form a vector space or subspace, right? So there may be lot of other examples also, so try to go through all of these, right? So I think I am able to make you the basic idea and the approach that how to connect each and everything from the basic definitions and results, right? So let's move to the next. What it is saying? It is saying that so that the following sets are subspaces of the vector space this, right? So these are my sets. See, here is a catch. What? You can solve it by using the shortcut trick, right? Oh no, basically we have to prove it now. But see, if this kind of question will be in your competitive level exam, then how to think? See, there is also a shortcut. See, this is of the form that this side is linear and right side is 0. This side is linear and the right side is 0. This side is linear and the right hand side is 0. Right, so definitely by using this condition we can say that yes, this will form a subspace. Right, so what was the condition? See, whenever you see f of a equal to 0, f of b equal to 0, or f of c equal to 0, or any finite number, right, in the condition of the form this, right, function of any point is equal to 0, right? So just think of this trick, that linear combination plus RHS side is equal to 0. It will imply that it is a subspace, right? So I will show you more results on it, right? But at first let me prove it for the semester level examination. So see what is given. It is given that S is equal to f belongs to c 0, 1 such that f of 0 is equal to 0. See, what is c of 0, 1? What does it mean? It means that set of all real valued continuous functions defined on 0, 1 to r, means this is equal to set of all functions, right, from close interval 0, 1 to r such that f is continuous, right, and this is the subset of it, right? So see how can we prove it. So see whether 0 belongs to it or not, right? So we know that 0 function is continuous. 0 function is continuous. What does it mean? It implies that 0 function is continuous, plus we know that 0 function, right, over any point, what does it give? It will always give 0, right, by the property of functions. Okay, so since 0 is a continuous function, right, so it will belongs to this set, right, and since 0 satisfies this condition, so this 0 will also belongs to this set, right? So it implies that 0 vector, I am writing like that, okay, that 0 function belongs to S. What does it imply? Implied that the first condition satisfied. Now check the closure under addition, right? So see, let us choose two elements from S. So let f and g belongs to S. What does it imply? It implies since f and g are the elements of S, so it will satisfy this condition that f of 0 will be equal to 0 and g of 0 will be equal to 0, right? So give it a name, equation 1 and equation 2. Right, now add them, f plus g over x, right, means f plus g over 0. Why? Because we have to check this condition, right, function over 0. So this is my function over 0, right? Why we are going to check this one? That's why we are writing f plus g instead of a single function, right? So what it will be? It will be equal to f of 0 plus g of 0, right? And it will be equal to, see, from equation 1 what we get, f of 0 equal to 0, and from equation 2 we will get f of 0 will be equal to 0. It implies this is equal to 0. So what we get? We get that f plus g over 0 is equal to 0, right? So by condition what we get? So it will imply that this will, means this f plus g will belongs to the set S, right? So see, finally we have proved that it is closed under addition also, right? Now there is only one remaining condition. What is this? This is scalar multiplication, closure under scalar multiplication, right? So see, let us choose any element. Let C belongs to F, right, means C belongs to R. Basically R is the field here, right? So C belongs to R. Now let us choose any vector from S. So choose F belongs to S. What does it imply? It will imply that f of 0 will be equal to 0. Right, now check the scalar multiplication. So it will be CF, right, and C of f over 0. Right, we have to check that whether this condition satisfies or not. Right, so C of f, so by the function property we get this one, and we know that f of 0 is equal to 0, so c into 0, this is equal to 0. So c we have we got that c of f of 0 is equal to 0. What does it imply? That this c of f belongs to S, right? So this S is also closed under scalar multiplication. So since S satisfies all of these three conditions, so by the standard subspace test we can say that yes, the S is a subspace of C, and hence proved, right? I hope everything is clear. If not, then comment section is only for you. If you have any single doubt, right, then make comment, I will make you reply. Okay, now the second one, what it is saying. So see, you can prove it by yourself, right? See, this is my linear right side 0, right side 0, right? So it will form a subspace. Okay, so just prove like that. Okay, this is your homework. See, in this case you have to check only one condition, but for the second one you have to check two conditions, right? So check whether it satisfies or not. This is your homework. Now see what I have said, that if LHS is linear, right, and RHS is 0, then it will be a subspace. Now, and see the another condition, that if RHS is not equal to 0, then it is sure that it will not form a subspace, right? There no need to check anything. If RHS is not 0, then 0 vector will be not there, and since 0 vector is not there, so it will never form a subspace, right? Always remember that. Now there are some special cases, right? See, what are the special cases? So see, now we have to check all of these, right, that whether this forms a subspace or not. And students, you can see that these are the standard questions, right? You can see these types of questions in your IIT JAM exam, in CSIR NET and GATE also, right? And students, we will solve it by using the shortcut trick. Okay, so that it will save your time in this examination. Okay, so listen carefully. See what it is saying. It is saying that f of a equal to 0, right? So we have already seen that if it is of the form f of any point equal to 0, right? See, LHS is my linear condition plus RHS is equal to 0, right? So see, this is my linear, means f of alpha or f of a, this is my linear, right, and RHS is 0, right? So from the shortcut trick, what can you say? That yes, this is a subspace, right? So yes, it is a subspace. Now what about this? See, this is linear and the RHS is 0, so yes, it will also be a subspace, right? And the third one is f of a to the power n equal to 0, right? So students, listen carefully. If we choose a equal to 2, then it will be equal to 0, right? And see, this is non-linear, right? This is non-linear, but students, see, you have to simplify it, right? You can't say like that, since f of a to the power n equal to 0, that's why this is non-linear. So we can say that yes, since it is non-linear, so this will not form the subspace. But student, at first you have to simplify the conditions, right? So if you simplify it, what will you get? You will get f of a equal to 0, right, which is the same condition like it, right? So actually this is nothing but just f of a equal to 0, right, which is my linear condition, and RHS is 0. So yes, this will also form a subspace, right? So use your brain, right? The conditions, the results and the theorems and the definitions are same, right? Only you have to know that when and how to use it, right? So this will also be a subspace. And now see, what about this one? This is mod of f of a, right? So we can say that mod of f of a, it will be equal to f of a equal to 0, right? So yes, this is this condition and this condition, right? All are same. That's why it will also be a subspace. Why? Because LHS is linear, RHS is 0. Similarly, you can say that yes, this will also be a subspace, right? Because it can be simplified as f of a equal to 0, right? So always try to simplify the conditions, then check whether it satisfies or not. Similarly, see, this is a very beautiful question. Okay, but you can solve it in a fraction of second. See what it is, log of 1 plus f of a square equal to 0, right? So see, wait, sorry, what it is, log of 1 plus f of a square equal to 0. And students, earlier I have said that log is a non-linear function, right? So many students will say that yes, since log is a non-linear function, so these will not form a subspace. But student, always simplify first, right? So what it will be, it will be log 1 plus f of a square, it will be equal to, and we know that log 1 is equal to 0, right? So we can write 0 as log 1. Now since log of this equal to log of this, what does it imply? If you simplify, then you will get 1 plus f of a square is equal to 1, right? Now see, if you simplify, you will get this one, right? And we know that this is equal to this, right? So basically this is nothing but this is actually f of a equal to 0, right? So this is actually f of a equal to 0, right? So it will be a subspace, right? Always simplify, okay? There may be any other condition also, and when you simplify, you will get that yes, this is, right? So be careful and be smart, right? What I have said, that be careful, be smart, right? Only then you will be able to solve the questions of JAM, NET and GATE, okay? Never forget your basics, never forget your root, never forget your definition, never forget your theorem, right? Only then you will be able to play with them, okay? So now what is it? It is saying that f of a square plus f of b square is equal to 0, right? Now tell, does it form a vector, will it form a subspace or not, right? The student will see that yes, this is nonlinear, this is nonlinear, right? But RHS is 0. Since these are nonlinears, so this will not form a subspace, right? But students, here is a catch also, right? Wait. Oh, the system is lacking little much. Wait. See what it is. It is saying that f of a square plus f of b square is equal to 0, right? And we know, see this is positive number, this is positive number, right? So positive plus positive will be always be equal to positive, right? But RHS is 0, right? So when does it satisfy, right? So you can say that this condition will satisfy only when f of a equal to 0 and f of b is equal to 0. Only then this condition will satisfy, right? So basically this set, what it is saying, it is saying that this is the set, right? This is the set of, what kind of set? This is the set like f such that f of a equal to 0, f of b equal to 0, right? This is the set of this form, right? So you can see that yes, this is linear RHS 0, linear RHS 0, right? So it will form a subspace, right? Students, I know that this is something different, right? This is something different for you, but be clear about it. Why? Because in the competitive level examination, it will test your knowledge, right? Test your patience, that how you are using the concepts and short tricks, right? So always remember, this will satisfy only when RHS is 0, and you can see that this equation will satisfy only when f of a and f of b are equal to 0, right? And see, this is linear, this is linear, okay? So at first from here come to here, then check, right? And one question, suppose if here is any other number instead of 1, instead of 0, right? Suppose in the RHS there is 1, then will it satisfy? No. Why? Because RHS is not 0, so it will not satisfy. Why? Because the 0 vector will be not there, right? So next, what it is saying, that W8, f of a equal to f of b. So at first rearrange it, f of a, if f of b we take it here, it will be f of b and it will be equal to 0, right? So see, this is linear, right, and right side is 0, so it will form a subspace, right. Similarly you can see that this is linear, this is linear, right, so this is linear and RHS is 0, so it will satisfy all the conditions, hence this is subspace. So here all of them are subspaces. I hope I am able to make you understand the approach, that how you have to approach in your competitive level examination, right. And it is not enough to know the shortcuts, to know the theorems, to know the definition and to know the results, right. You have to know that how to apply them, only then you will be able to score a good marks, right. See, I have told you the shortcut tricks, but see how we can use. These are the way to use, right. At first simplify, then do it. Okay, so be patient. Now check all of them. What is it? See, f of a into f of b. See, this is non-linear, right. And see, we can choose that f of a is my 1 and f of b my 0, right. F of b is equal to 0. Then you multiply it, you will get that f of a into f of b, it will be always equal to 0, right. If you choose here 3, 4, 5, no matter, but this will be always 0, right. But students, see, this is non-linear, right. Since this is non-linear, so it will not form a vector space, right. When it will form, when you have guaranteed that yes, this f of a and f of b is equal to 0. If you have given the condition that yes, f of a is equal to 0, f of b is equal to 0, right, only then it will satisfy. Okay, so since this is non-linear, so we discard it. Okay, but in this case, see, here are no other choices except 0, right. That's why though it was in the form of non-linear, but it forms a subspace, but here is not like that. Okay, so what is the next? See, RHS is 1, so it will not form a subspace, 0 vector will not belong here. And what about this one, log of f a equal to 0? Simplify it, it will be log of f of a equal to, we know that log 1 is equal to 0, it implies f of a equal to 1, right. And we know that this is not subspace. Why? Because 0 will not belong here, RHS is not 0. Okay, similarly you can say that, see, f of a is equal to 1, RHS is not equal to 0, not a subspace. Okay, similarly you can say that, see, RHS is 1, so 0 will be not there, right. But in this case RHS was not here, RHS was not, but in this case RHS was 0. Okay, and what it is, see, this is non-linear, right. So what it can be, is there any, sorry, why we are checking it, see, RHS is non-zero, so that's why it is not a subspace, right. And what about it, RHS is non-zero, not a subspace, RHS is non-zero, not a subspace, RHS is non-zero, not a subspace. So I have discussed all the varieties of questions. Now students, see, suppose there is a set in the form xyz belongs to R3 such that x square is equal to 0, right. If I say that, check whether this set forms a subspace or not, right. So many students will say that, see, here this is non-linear form, right, that's why it will not be a subspace. But students, what is the process, what is the step? The step is that at first we have to simplify it, and when you simplify you will get this one, right. And see, this satisfies the condition, right, hence this will be a subspace, right. And you can see that all x to the power n equal to 0, for this condition it will be a subspace, right. So I hope I am able to make you understand each and everything, right. And students, this is the way to connect each and everything, right. And you can apply this approach in your competitive level examination. Okay, but for semester examination you have to prove it, right. So students, this is your homework, prove each and every result, okay, theoretically, for your semester level examination. And if you find any difficulty, then comment, I am here only for you, I will make you reply. So next question, what it is saying, prove that the subset D, which is a subset of all real value differentiable functions defined on AB, is a subspace of this. What does it mean? Basically this is the set of all continuous functions, right. So let us define the sets first, right, that which one is subset of which one. So C of AB, this is equal to functions defined on the closed interval AB to real number, yes, R, real valued. Okay, so it is from closed interval AB to R, right, such that f is continuous function. Okay, and what is D? D of AB is equal to functions from closed interval AB to R such that f is real valued differentiable. Real valued differentiable function. Right? So see, this is our C over AB, right? And we know that this is a vector space over the field real number, right? And now we have given a set, this D of AB. Now we have to check that whether this D forms a subspace or not, right? For that, what we have to check? We have to check the three major conditions. What are those? Number one, zero vector. See, we know that zero function is differentiable. We know that zero function is differentiable, right? It implies that 0 belongs to D, right? See, from where we are getting it from the property, from the result of differential equation, right? So first condition satisfied. What is the second condition? Let us choose, let f and g belongs to D, right? Since f and g are from D, so what does it imply? It will imply that f is differentiable, and if f is differentiable means f dash is differentiable and g dash is differentiable, right? F is differentiable, not f dash. Okay, since f is differentiable, it implies f dash exists, right? Means the derivative will exist. Similarly, since g is differentiable, so it will imply that g dash will also exist, right? Now we have to check whether that this f plus g exists or not, right? So see, as we know that f plus g dash, it will be equal to f dash x plus g of dash by using the property of differentiation, right? And see, this one exists, right? So their addition will also exist, right? It means that f plus g dash x exists, right? Since f plus g exists, so it will imply that f plus g belongs to D. See, here basically we are using the properties of differentiation. Why? See what it is saying, that f is D is the set of all differentiable functions, right? So we are checking that whether this is differentiable or not, right? So we are taking the derivative of it, right? We get this one, and by the assumption we have f dash exist and g dash exist, right? So their addition will also exist by using the property of differentiation, right? So f plus g is differentiable, so f plus g will belongs to D. Now what is the remaining condition? Scalar multiplication, right? So let k belongs to R field, okay, and f belongs to D. What does it imply? F is differentiable, right? Means f dash exists, right? Now see, we will check the scalar multiplication. Okay, so c f dash x, it will be equal to c into f dash x, right? And we know that this is a real number and this exists, right? So their multiplication will also exist, right? So what does it mean? It means that cf belongs to D. Why? Because their derivative is in D, right? So we have proved that D satisfies all the conditions of subspace. Therefore, by standard subspace test, we can conclude that D is a subspace of C over AB. So students, I hope that you are enjoying the lecture and you are understanding each and everything. And students, see, basically if you are preparing for your competitive level examination, then these are basically results. Means these are basically some special kind of results that you have to remember. What are the results? That the set of differentiable function, the set of continuous function, the set of integrable functions, these forms a subspace, right? You have to remember. But if you are a semester level student, then for your semester examination you have to learn that how to prove it, right, and how to write it. So just because of you I am writing here, right? So next, it is saying that examine whether the following subset of these are subspaces or not, right? So we have to check that whether these are satisfying all of three conditions or not, right? And here what is V and what is W? So see, I mean what is set and what is the subset. So here the set of matrices, right, set of matrices is the vector space, right, over the real number, and S is the subset of it with different kind of conditions on the matrices, right? So now we have to check that this S forms a vector space or not. And students, the set of matrices forms a vector space, and I have proved it in the previous lecture, okay, vector space, okay. So if you want to know that how does it forms a vector space, so go to the lecture, and in this in that lecture I have given timestamps, right? Just go there and check and see the proof, right? So now see how can we prove it. Okay, by using the shortcuts you can do it also, right? See what it is. It is my linear and the RHS is 0, right? What does it mean? It will form a subspace. Similarly, this is my linear, right, and RHS is 0, so it will form a subspace. What about this one? That determinant of this. What is the determinant of it? So the determinant will be AD minus BC, right? So students, see what is it? This is my non-linear, right? This is my non-linear equation, right? See, since this is non-linear, right, so it is not a subspace, right? See, I am using the tricks, right, and you can see that in a fraction of second we are getting our answer, right? And we will discuss these things also. But students, this lecture is not only for your competitive level examination, right? This is especially designed for the semester level students, right? So I will prove each and everything here, right? I will give you a detailed proof, okay? And for the students who are preparing for your entrance level examination like NET and GATE, right, you also have to know the proof. Why? Because in the interviews they will ask these things, right? In the interview they are going to ask basically the basics questions, right? So you have to be very smart at your basic, right? So students, see how can we prove it. Let me change the color, right, one, right? What is S? This is S, right? So see, can we choose a matrix like that, 0 0 0 0, right? And see, is it satisfying this condition that A plus B equal to 0? So yes, this one plus this one, right, this one plus this one, this is equal to 0. What does it mean? It means that this matrix belongs to S, right? As students, you can see that this is my 0 matrix. What does it imply? It implies that the first condition holds, right? What about the second condition? See students, my this condition is satisfying, right? And no matter what is at this position, right, you can choose anything, right? So I am choosing here 0 0. Okay, so first condition satisfied. Now take two elements, right? So let A1 B1 C1 D1, right, and A2 B2 C2 D2 belongs to S, right? Since these are the elements of S, so it will satisfy this condition that this plus this will be equal to 0, a1 plus b1 is equal to 0, and a2 plus b2 is equal to 0, right? Now we have to check that whether the addition of it is in this set or not, right? So see, we are going to check if we add a1 b1 c1 d1 plus a2 b2 c2 d2, right? It will be equal to a1 plus a2 b1 plus b2, right? And then c1 plus c2, then d1 plus d2, right? And now students, we have to check the condition that does this plus this is equal to 0 or not, right? So let's check the condition. Checking condition. Okay, so add them, a1 plus a2 plus b1 plus b2. Check. See, this is equal to a1 plus b1 plus a2 plus b2. Can we write it? Yes, we can write by rearranging it, right? So it will be equal to, see, a1 plus b1 is equal to 0, so 0 plus a2 plus b2 equal to 0, 0 equal to 0, right? So a1 plus b1, sorry, this plus this is equal to 0, hence their addition belongs to this set, right? This belongs to S. What does it imply? It implies that S is closed under addition, right? Now we have to check the scalar multiplication, right? So see, third condition. Okay, so let C belongs to F and F is my R, so I can write R, and let an element A, B, C, D belongs to S. Since ABCD belongs to S, what does it imply? It will imply that A plus B equal to 0, right? Now we have to check the scalar multiplication condition, so we have to multiply it, see the element of field into the element from the set S, right? This, and it will be equal to CA, CB, C square, sorry, there is C now, let it be DE, right? Because, yeah, it will be EA, EC, wait, what is happening, wait, so see, it will be EC, ED, right? Now we have to check that whether this satisfying this condition or not. So checking, right? So if you check, what will you get? EA plus EB, right? It will be equal to, if you take E common, then it will be A plus B, and by this condition 1, what we have, this is equal to 0, so E into 0 is equal to 0. So see, yes, it satisfies the condition. It means that scalar multiplication also belongs to S, right? So therefore, by standard subspace test, we get, what we get? We get that S is a subspace, right? So this is the way to prove. Now what about the second one? See, similarly we can prove it also, right? See, basically you can prove, there is nothing harder here. Okay, so in this case, what will you do? You will take a matrix, right? A1 b1 a2 b2. See, 0 will satisfy, right? If you take all the elements 0 0 0 0 0, so add them, you will get 0. So yes, 0 belongs to S, right? What about the second one? Take A, B, C, D, A1 b1 c1 d1 plus A2 b2 c2 d2, right? Take here A2 b2 c2 d2, then add them, right? And by rearranging the condition, you will get that yes, this will also satisfy, right? So this is your homework. Okay, and what about this one? So I have yeah, we can counter it by an example, right? So see, so what is our S? Write it. S equal to A, B, C, D belongs to R 2 cross 2 matrix such that determinant of A, B, C, D is equal to 0, right? So if we choose two matrix, right, let A be a matrix and A is equal to 1 0 0 0 and b is equal to 0 0 0 1. Right, see, determinant of a is equal to 0, determinant of b is equal to 0. Right, that's why we can say that a and b are from S. Right, since it satisfies this condition. Right, now check whether it satisfies the closure order addition or not. Right, so a plus b, what it will be? It will be equal to 1 0 0 and 1. Right, and see, determinant of a plus b is not equal to 0. Right, what is the determinant? Determinant is 1. Right, since determinant of a plus b is not equal to 0, it implies that a plus b does not belongs to S. Right, so it implies that closure of addition fails. Right, that's why it will not be a subspace. So students, this was the counter example. Right, and students, if you are a semester level students, right, and if you want a detailed proof, then don't worry, I am also going to give that. Okay, so see, let us choose. See, at first we will satisfy the first condition, 0 belongs to it or not. So see, this is my 0 matrix, right, and if you take the determinant is 0. What it implies? It implies that this 0 matrix 2 cross 2 belongs to S. Right, so the first condition satisfies. Now how can we prove the second condition? So see, let A equal to A1 B1 C1 D1 belongs to S, and B equal to A2 B2 C2 D2 belongs to S. Right, since these are from S, so it implies that determinant of A will be equal to 0 and determinant of B will be equal to 0. Give it name 1 and 2. Right, now check A plus B. Right, so A plus B, does it belongs to S or not? Right, so when it will belongs to S? It will belongs to S only when determinant of AB will be equal to determinant of A plus determinant of B. Right, so students, you can see, if you have read the matrix theory, then you can understand that this does not holds. Right, we can see that this is not always true. Right, and from where we get? By matrix theory. Right, when I will teach the matrices, right, there I will show you that this is the property of matrices. Right, so for now just remember it, this is not always true. Right, that's why closure under addition fails. Right, since among 3 one condition fails, it means that this is not a subspace. Right, so this is the analytical way, and this is your counter example. Okay, so see, what is the next question? What it is saying, that the set of all 2 cross 2 real diagonal matrices. Right, so see, so how does the set S will looks like? Right, so S is the set of all 2 cross 2 diagonal matrices. Right, so we can say that this is of the form these and these. Right, such that such that AB belongs to R. Right, what is this? This is the set of diagonal matrices. Okay, now see, we have to check whether that this forms a subspace or not. So at first we will see the first condition. See, what does it mean by a diagonal matrices? It means that all the element except the diagonal will be 0. Right, in short you can say that diagonal means all the elements except diagonal position is 0. Right, so we can choose anything here, 0 0 0 0. Right, so see, in this case all the elements except diagonal are 0. Right, and we can choose that diagonal is also 0. Right, no problem. So see, this will belongs to S right? So yes, first condition satisfied. Now the second condition, if you choose any two matrices from the set S, right? So let us choose A0 0 B and another is P0 0 Q, right? We have chosen two matrices. Now add them. What will you get? A plus P 0 0 B plus Q. And see, this is again a diagonal, right? Since it is again a diagonal, so it will belongs to S, right? So closure under addition also satisfied. Now the third one, what is it? It is take any element C from R. This is field, okay? This is field. And now take any matrix 0 0 0 0 from S, which is diagonal, right? Now multiply it. What will you get? You will get CA0 0 CB, right? So see, again this is a diagonal matrix, okay? So it implies that this belongs to S. Therefore this is closed under scalar multiplication also, right? So therefore by subspace test we can conclude that S is subspace, right? So now what is the next? Here the set of all symmetric matrices, right? So see, set of all symmetric matrices. So see, what will be the S? The S will be of this form, that this is 5, okay? So S such that here will be the matrices belongs to R2 cross 2 such that this is symmetric. Symmetric means it will hold this condition, right? And for the students who don't know that what is symmetric, so a matrix is called a symmetric when their transpose is equal to that matrix. Like if you are choosing a matrix like 1 2 3 4, right? What will be the transpose of it, right? Its transpose will be 1 3 2 4, right? And see, if this is my A, if this is my A, then this is my A transpose, and see, this is not equal, right? So this matrix is not symmetric, right? We will take that special kind of matrix that the transpose matrix will be the same as A, okay? So we will discuss these things in our next lecture, right? It will be on matrices, right? So be patient. So what is the set? This one, right? So now check all the conditions. So if we choose 0 0 0 0, right? So see, if we take the transpose of this matrix, then again this will be this one, right? We take transpose, right? So this is my symmetric matrix, and since this is symmetric, so this matrix will belongs to S, right? So the first condition satisfied. Now the second condition, right? Take any two matrices A and B. Wait, I am writing in a proper way. Let A and B, let me erase it first. Let AB belongs to S, right? What does it imply? Since AB are from S, so it will satisfy this condition: A transpose equal to A and B transpose is equal to B, right? Now we have to check this one, that does it satisfy or not? AB belongs to S or not? And when does this A plus B will be in S? Only when their transpose will be equal to AB, right? So see, A plus B transpose, we are going to check whether this satisfies or not. So by the algebra of matrices, we can say that yes, this is equal to A transpose plus B transpose. From here we get it. So we are getting it from the properties of, okay, you can write that from the matrix theory, right? Basically these are the basic things in matrices, right? So you can see, right? So see, since A transpose plus B transpose, and we know that A transpose is equal to A, B transpose is equal to B, so it will be equal to AB. So see what we find. We find that A plus B transpose is equal to A plus B, right? So what does it mean? It means that A plus B belongs to S, right? So this is closed under addition also. Now what about the scalar multiplication? if we choose any element C from F, right, and A from S, since A is from S, so it will imply that A transpose is equal to A, right? And then we have to check this one, C of AT, right? And by the matrix theory, we have this will be this one, A transpose, and we know that A transpose is equal to A, right? So CA, right? And we know that, see what we get that this transpose is equal to this one, right? We find the transpose of this one and we get the this one. What does it imply? It implies that CA belongs to S. It means this is closed under scalar multiplication 2. Since this satisfies all the three conditions, hence by the subspace test we can say that yes, this S forms a subspace, right? So this is the way to connect each and everything, right? I hope I am able to make you clear each and everything, and if you have any doubt, if you have any difficulty, right, then comment your doubt. I will clear your doubt, right? So now next, what is next? The set of all 2 cross 2 skew symmetric matrices, right? So yeah, it will also form a subspace, right? And this is your homework to prove it, right? This is your homework, prove it. This is your homework, right? And what is the condition? The condition is that A transpose will be equal to minus A. This is the condition of skew symmetric, right? And this is your homework, prove all the three conditions, and if you have any difficulty then comment, right? And what is it? It is set of all upper triangular matrices and lower triangular. Yes, this will also satisfy. How? If we choose any matrices like upper triangular and lower triangular, then you can see that their addition will be also from that set and their scalar multiplication will also from that set, and we know that this 0 matrix is upper triangular as well as lower triangle too. That's why 0 matrix will belong to all of them, right? So these three are your homeworks. Okay, so I hope I am able to make you each and everything clear. And students, just remember some things. Here we are checking for R2 cross 2, right? And remember that all of these results are true for n cross n also, right? If you have given any matrix, if you have given any diagonal matrix or skew symmetric matrix or symmetric matrix or triangular or upper triangular matrix of order n cross n, right, with these conditions, then they will form a subspace, right? And see, what about this one? So this will never form a subspace. Reason? I have proved it, right? So finally we have completed it. Okay, so now next, what it is saying that determine whether the following subsets of R3 are subspaces or not. So students, you can check with the shortcut trick, right? So see, this is my linear condition, this is my linear condition, right? See what it is? It is basically A1 minus 3A2, and the second one is, sorry, A1 minus 3A2 equal to 0 and A3 plus A2 is equal to 0, right? So these are my conditions. So see, this is linear, RHS is 0, linear, RHS is 0. What does it imply? It will imply that this is a subspace, right? See, in a fraction of second I have solved this question. Okay, so see, what about this? So see, linear, linear, see linear, yes, RHS 0, right? But see students, 0 will be not there, right? If you take A1, A2, A3, 0, right, A1, A2, A3, 0, right, then it will not satisfy this condition, that 0 minus 0 plus 2, this is not equal to 0, right? So 0 does not belongs to S. That's why this is not a subspace, right? What about this one? See, this is my linear combination, this is my linear equation, right? And RHS is 0. So yes, this is a subspace, right? Similarly, linear equation, RHS is 0, yes, subspace. Okay, what about that? 0 vector will not be there, right? 0 is not there, RHS is not equal to 0, so it is not a subspace, right? Similarly, you can see that here this is my non-linear equation, right? That's why this will not form a subspace, right? And students, see, you can simplify it. How? See, A1 plus no sorry, a1 minus a3 is equal to minus 2, right? This is our condition, and from here you can see that RHS is not equal to 0, right? Though in this side this is linear equation, but RHS is not 0, that's why this will not form a subspace. You can think like that also, right? And here 0 vector will not belong. I have given you two idea, right? So students, this is your homework to prove for your semester level examination, right? Prove for semester. And if you are preparing for net gate, then you also have to try these kind of questions, right? It will be very helpful for you. So next, what it is saying that let w1 equal to this, right? Prove that w1 is a subspace of fn, right? So students, see, since this is linear, right, RHS is 0, so it will satisfy. What about that RHS is not equal to 0? It will not satisfy, right? So students, further show that w2, this one, is not a subspace. So students, which condition it will fail? So definitely it will fail the 0 condition, 0 n times, right? Nth tuple, so this is nth 0, right? And this does not belongs to w2, that's why w2 is not a subspace. You can write it. And what about this one? You can show it that if you choose any tuple of 0, it will belongs to w1, right? And if you choose anything, any two elements from this set, right, and if you add them, then you will be able to see that yes, that is an element of w1. And similarly you can prove the scalar multiplication also. So this will be also your homework. I hope you will solve each and every questions of this slide. Okay, so next, what it is saying? It is saying that is the set w equal to this one is a subspace of PF where n is greater than equal to 1. Justify your answer. See, what is w here? W is equal to this one, right? And here are two conditions, that f of x equal to 0 and f of x has degree n, right? So we will proceed with this condition. See, at first we will check closure under addition. Closure under addition, right? And why we are not checking the first condition? Because see, what it is said that degree fx has degree n, right? So if we choose 0 polynomial, why we are saying polynomial? Because this fx is from set of all polynomials. So see, if we choose 0 polynomial and 0 polynomial to the power n of x, what we get? It will be always 0. So see, we find a polynomial of degree n which satisfies this condition, right? So see, this belongs to w. So the first condition holds. Now we will check the second condition, that closure under addition. So let us choose any two elements. See, let f of x and g of x belongs to w. It implies that fx will be of degree n, right? So it implies that how does the fx will looks like? Then the fx will looks like this, that an(xn) plus an minus 1 xn minus 1 plus dot 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 plus a0, right? Basically this is the polynomial of degree n. And what will be gx? Now we will choose the gx, right, of degree n, but in a different way, right? So see, what we have chosen, this one, right? So if we choose gn equal to minus an(xn), right, plus an minus 1 xn minus 1 plus dot 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 plus a0. So students, see, this is our two polynomials, right? Now add them, f of x plus g of x. So if we add them, then what will we get? If we add, then we will get that this plus this, right, it will be equal to 0, plus what it will be? It will be equal to if you add them, then it will be equal to 2an minus 1 x to the power n minus 1. Similarly, plus so on plus 2a naught, right? So see, we have two polynomial of degree n, right? Since it was degree n, so it will be from w, right? And then we added it, right? We are taking addition of them, right? Then we got this one. So see students, this is not a polynomial of degree n, right? It is the polynomial of degree n minus 1, right? So since this is not a polynomial of degree n, it implies that this does not belong to w. Why? Because w has the polynomials of degree n only, right? So this is not closed under addition, not closed under addition, which implies that not subspace, right? So this is the way to prove. A student, I am asking you a question from here, right? Suppose it was something different, like if here was the condition that fs has degree at most n, right? If this was the condition that w is equal to fx belongs to p of f, such that f of x equal to 0 or f of x has degree at most n, right? If this was my set, then my question is that then will it form a subspace, right? This is my question to you. Okay, so this is your homework. Solve it, think it, right? And if you find any difficulty, then comment it. I will clear your doubts. Next, what it is saying? It is saying that let this denote the set of all real valued functions defined on R having continuous nth derivative. Prove that this one is a subspace of FRR, right? So see, new notation, right? So what it is, what does it represent? So see, basically this represents set of all real valued function defined on R. What? That set of all real valued function defined on R, right? What it is? It is set of all real valued functions defined on R, right? So this is our vector space. Now we have to take a subset, right? What is subset? This one. And how is it defined? It is defined as this is equal to set of all real valued functions defined on R, right? So it is a real valued function defined on R such that having continuous nth derivative, means the functions are nth derivative and it is continuous, right? So basically here are two conditions, such that fn exists, right? What does it mean? It means that derivative of f n times, right? So fn exists and is continuous on R, right? So see, basically this is the set, right? Once you define the set, then it will be easy for you. So see, now we have to check the condition for this subset, right? So see whether the zero vector belongs to it or not, right? So see, we know that zero function is differentiable function, right? So see, 0 of x equal to 0, we know, right? For all x belongs to R, right? We know that 0 of x equal to 0, and if you take derivative of it, first derivative, it will be 0. If you take second derivative of it, it will be 0. Similarly, if we take nth derivative of x, then it will be equal to 0. So students, see, this 0 function is derivative at n times, right, and it is also continuous on R. That's why 0 belongs to, therefore 0 belongs to c to the power n of R, right. So the first condition satisfied. Now let us move to the second condition. What is the second condition? See, if we choose two elements from this set, right, so choose, let f and g belongs to this set, right. So since f and g belongs to this, so it implies that it will satisfy these conditions, right, because these are the members of this set, right. So it implies that fn exists, right, and is continuous on R, right. Similarly, gn will also exist and it will be continuous on R. Let it be equation 1 and then let it be equation 2, right. Now we have to check the addition, right. So see, now we have to check that whether this belongs to this set or not. So what we have to check? We have to check their derivative, that is it nth time derivatives or not, right. So c of x equal to, so by using the sum condition of differentiation, what will we get? We will get this one plus gn of x, right. From where we get it? We are getting it from the sum of differentiability, right. So see, from 1 and 2 we can get that this is my differentiable, this is my differentiable, right. So by using the property of differentiation, see, by using the property of differentiation, we get that, see, what is the property? That if two functions are differentiable, then their sum will also be differentiable, right. So see, this is differentiable, this is differentiable, so their sum will also be differentiable, right. It implies this is differentiable, right. Since this is differentiable and this is equal to this one, so this one is also differentiable, right. So it implies f plus g is differentiable n times, right, or fn f plus g of n exists, right, and these are continuous and continuous on R. So the second condition satisfies that this set is closed under addition, right. Now what is the remaining condition? Now the remaining condition is scalar multiplication. So let us check it. Let C belongs to R, R is my field. Now let another element F belongs to Cn over R, right. Since F is from this set, so it will imply, so it will satisfy the condition that Fn exists, right, and is continuous on R. Now check the scalar multiplication condition. So C of f, right, to the power n of x. We have to check whether this is closed or not, right. So see, by using the differentiation property, we will get C of fn of x, right, and we know that this is differentiable, right, means this exists, right, from the given condition. Since this exists, right, and this is a finite number, right, so by using the condition of differentiability, I am writing, okay, by using the property of differentiability, right, what we get? We will get that this one also exists, right. So see, finally we get that this is n times differentiable, right, and it's continuous. So finally we can say that C of f belongs to the set this, right? Hence this set is closed under scalar multiplication too, right? So therefore we can write that by using standard subspace test, we can conclude that Cn over R is this is normal C, okay? R is a subspace, okay? Hence proved, right? So I hope I am able to make you understand each and everything, and still if you have any doubt, then comment section is only for you. Ask your doubt here, okay? I will make you reply. Next, what it is saying? It is saying that so that the set of all convergent sequence, this one is a subspace of the vector space of all real sequences, right? Zero vector. So see, we know that the sequence, this one 0 0 0 0 0 dot 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 and so on, right? And we know that this is a constant sequence, right? This is a constant sequence, and by the properties of sequences we know that constant sequences are always convergent, right? Constant sequences are always convergent, right? So implies it is convergent, right? And it converges to 0. So write it, and converges to 0. So students, see, we find a sequence which is convergent, right? And this is a 0 sequence, right? So finally we can say that this is from the set W, right? And since 0 belongs to W, so the first condition satisfied, right? Now the second one. What is the second condition? We have to choose two sequences from this set, right? So let us choose. Let An belongs to W and another sequence Bn belongs to W, right? Since it is from W, so it will be convergent, right? And since it is convergent, so this will exist. So it implies limit n tends to infinity An exists, right? Similarly, it implies that limit n tends to infinity Bn will also exist, right? And students, as we know the basic things about sequence and series, right? And why? Because in the previous lecture, in the lecture of vector space, I have proved that set of all convergent sequence forms a vector space, right? And for that I have given some basic idea of sequences, right? Here I have discussed some important results related to the sequences, right? Though this is the topic of real analysis, but for our proof we have learned some basic, right? So if you have any difficulty to understand this sequence, then please go to that lecture, right? See the timestamps, right? And then clear your doubts from there about the sequences, then come back here, right? So what does it mean that limit exists? Implies it will be a finite number An, right? It is a finite number, let it is L1, right? Belongs to R. Okay, similarly n tends to infinity Bn, it will be equal to, let it is L2, right? So since it is given that An, the sequence An is from W, right? So it will be, so limit will exist, right? Since it is convergent, so let us consider that it is converging to a real number L1 and it is converging to a real number L2. Now we have to check the addition, right? So add it. If we add An plus Bn, then what we get, right? If we add this one, so see, by the property of subspace, by the property of sequences, we can say that if this one converges to L1 and this one converges to L2, right? So their addition will converges to this one, right? L1 plus L2, and we know that L1 plus L2 is from real number, right? So finally we get that limit n tends to infinity, an plus bn exists, right? And it converges to this real number, right? From here we are getting from the properties of sequences, right? If you have any problem, then please go here, right? You will get a lot of benefits, right? So it is closed under addition, right? So closure property under addition satisfied. Now what is the remaining condition? The remaining condition is scalar multiplication, right? So choose, let C belongs to R, where R is a field, right? Now let us choose another element, an from the set W. What does it imply? It implies that an is convergent. An is convergent implies limit of an will exist, right? And let us choose that it is converging to L, right? Limit of an equal to L, right? Now check the scalar multiplication. So it will be C of an, right? And we know by the property of sequences, which I have discussed in the lecture of vector space, that if an converges to L, right, then C into an will converges to C into L, right, where C is from scalar, right? So see, this is convergent, right, and this converges to this real number. It means that it is closed under scalar multiplication too, right? So finally we have seen that this set W is closed under addition and it is closed under scalar multiplication, and zero vector belongs to it, right? So by the standard subspace test we can say that yes, this W is a subspace of these vector space, right? Student, this is important result, right? It will be very helpful for your competitive exams like NET and GATE, right? So just remember the things, right? Next, what it is saying that let f1 and f2 be fields. A function g belongs to this is called even if this one for every t belongs to f1. A function f belongs to this one is called odd if it satisfies this condition for every t belongs to f1. Prove that the set of all even functions in this is a subspace of this. The set of all odd functions in this is a subspace of this. I will solve this one, right, and this one will be your homework. Why? Because if you remember, then in the previous lecture, which was on vector space, there was a question that prove that the set of all even functions and the set of all odd functions forms a vector space. And at that time I have proved for the even one, right, and I have said that for odd functions you have to check yourself. This is your homework, right? I have said like that, but here I am going to prove this one, right, and here this one will be your homework, right? So see, at first we have to construct the set. So see what it is. It is basically f from f1 to f2. Basically it is the set of all function defined on f1 to f2, right, defined from f1 to f2, right? And what is the subset? Subset are the odd functions. What does it mean? See, this is my vector space f1 f2, and this is a subset. What kind of subset? This is the set of all odd functions, right? So let us construct the set for this. W equal to f belongs to f of f1 f2 such that f of minus t is equal to f of t. Now we have to check that whether this set forms a subspace or not. For that we have to check three conditions. So let us check the condition number 1. Right. See, by the functional properties we know that the zero function will always map to 0 for all t belongs to the domain, right? So write it. What is domain? Here domain is f1. See, what is f1? Basically this is a function, right? This is a 0 function, okay, and this is my f1, this is my f2, and here is my t, right? And t be any element of f1, and when you operate 0 on this t, then you will get here 0 element, right? It will always map to 0 for all t, okay? So see, 0 of t equal to 0, right? And we know that it will satisfy for all t, right? And since this is a field f, right, so in a field for all t there exists a minus t also, right, from additive inverse property, right? So 0 over minus t, it will be also equal to 0, right, for all minus t belongs to f1, right? I hope I am able to make you understand, right? Now give them numbering, right? Suppose this is my equation 1 and this is my equation 2. Now see, if we multiply it by minus from both sides, then what will we get? Then we will get minus of 0 of t is equal to minus 0, right? Multiplying minus with equation 1, right? Minus 1 with equation 1, right? Don't be confused, this is negative 1 and this is my equation 1, right? So what we get? We get this one, and we know that minus 0 is equal to 0, right? So when you simplify, you will get 0 of t minus 0 of t is equal to 0, right? Suppose this is my equation 3. Now if we compare 3 and 1, then what will we get? Now from 1 and 3 we get what we get? We get that, see, this is equal to 0, this is equal to 0. It implies that this is equal to this one, right? So see, this is equal to this one, right? No, sorry, I am wrong, sorry, it's my mistake. We are comparing 3 and 2, okay, sorry, we are comparing 3 and 2, right? So if we compare 3 and 2, see, this is 0, this is 0, right? So this will be equal to this. So if we compare 3 and 2, we will get 0 of minus t is equal to minus of 0 of t, right? See, the 0 function satisfies this condition, right? So it implies 0 vector belongs to W, right? So the first condition satisfies. Now see the second condition. What was the second condition? Closure under addition, right? See, choose two arbitrary elements from the set. See, let f and g belongs to W. So it will imply that it will satisfy the condition of W. What does it mean? It means that f of minus t will be equal to minus of f of t, and g of minus t will be equal to minus of g of t for all t belongs to the field. Now see, now we have to check this one, that whether this f plus g belongs to the set W or not. For that we have to check that f plus g of minus t, right, it will be equal to f of minus t plus g of minus t, right? Now then this will be equal to, let it be equation 1 and equation 2, sorry, let it be equation 3 and this is equation 4, right? So from equation 3 and 4, what will we get? F of minus t will be minus of f of t, and g of minus t will be minus of g of t, right? So right here minus of g of t, right? From 3 and 4. Now take the minus common, so it will be equal to f of t plus g of t. So students, see, finally we get that f plus g of minus t is equal to minus of f of t plus g of t, right? And which is equal to minus of f plus g of t, right? So see, the condition has been satisfied. What does it imply? It implies that f plus g is a odd function and it belongs to W. So closure under addition satisfied. Now what is the remaining condition? The remaining condition is scalar multiplication. So see, let K belongs to the field, right? And let and F belongs to W, right? What does it imply? It will imply that f of minus t will be equal to minus of f of t, right? Let this is equation 5. Now check whether this c into f of minus t belongs to the set W or not. For that, what will we do? We will do that f of minus t, though, see what we will do. See, c of, from equation 5, what will we get? Minus of f of t. F of minus t is equal to minus of f of t, so we get it, right? This is into, and when you multiply you will get minus of c of f of t, right? And this will be equal to minus of cf of t. So finally we get that cf of minus t is equal to minus cf of t, right? So what does it imply? It implies that this cf will also belongs to W, right? So this W is closed under scalar multiplication too, right? So we have proved all the three conditions. So by standard subspace test we get that W is a subspace. Okay, hence proved. So this is the way to prove, this is the way to write, and this is the way to think, right? So I have done this one, and this is your homework. Do it yourself, and if you find any difficulty and if you have any problem related to the subject, then the comment section is only for you. Write your doubt, ask your doubts, I will make you reply and I will clear your doubt in the comment section, right? So next, what it is saying, see, let V be the real vector space of all functions this, determine which of the following are subspaces of V. So we have to check for all of these subsets, right? And let's start. What it is saying, see, let V be the real vector space of all functions this, determine which of the following are subspaces of V. So we have to check the subspace condition for all of these, right? So see, we are using here shortcut. Okay, by using the shortcut, what can we get? See what it is. Basically this is equal to f of x square minus, take it to this side, then it will be f of x whole square equal to 0, right? And students, you can see that this is my non-linear term, this is my non-linear term, that's why this will not be a subspace. And the second one is that, see, you can write it in this form, that f of 0 minus f of 1 is equal to 0, right? So see, this is my linear and RHS is equal to 0, right? So it implies that this will form a subspace. Now rearrange it, what will you get? You will get f of 3 plus f of minus 5, sorry, minus f of minus 5, this is minus, okay, equal to 1. So see, LHS is my linear but RHS is not equal to 0, that's why it will not form a subspace. And similarly you can see that this is my linear and RHS is equal to 0, so it will form a subspace. And students, we have already proved that the set of all continuous functions forms a subspace. Means how does this set will looks like? It will looks like C of AB, right? So we have already proved that this forms a subspace. So students, you can see that we can solve the problems by using the shortcut trick in a fraction of second, right? So see students, this is your homework, right? Prove it theoretically, right? Prove theoretically, right, that this will form a subspace, this will form, this will not, this will, and this will not, right? So this is your homework, and if you find any difficulty, then comment section is only for you, right? Ask your doubt here, I will make you reply. Next, what it is saying, it is saying that so that the set this one is a subspace of v3 over f, right? So students, we have already done this kind of problem, right? So this will be also your homework. Next, what it is, let V be the vector space of all polynomials over a field f if W equal to this one. So students, you can see that we have done this kind of problem in the previous question number 14, right? What was there? There was a slightly change in this condition. There was that degree of P will be equal to n, right? And here it is saying that degree of P of x is less than equal to n, right? What does it mean? It means that degree of P is at most n, right? So if you remember, then you can see that I have given these questions and homework, right? So this is also your homework. And if you find any difficulty, then comment section is only for you, just to ask your doubt, right? Ask your doubts, I will make it clear, right? So next, what it is saying, so that the following are subspaces of the vector spaces of all real valued functions on R, right? What are the, see basically what it is saying, it is saying that this is your vector space, and what is this vector space? This is the vector space of all real valued function, right? Means this is the set of all real valued function on R, right? And this is my vector space. Now we have to check that whether this subset of odd function, right? This is the subset of even function, this is the subset of continuous function, right? And this is the subset of bounded functions, right? Does all of them are forming a subspaces or not, right? So students, see here it is said that so that, right? So definitely all of them will form a subspace. Now we have to prove it, right? So see, I have proved this one, I have proved this one, I have proved this one, right? And I have not proved this one, I think, right? So student, you can prove it easily. Why? Because you see, we know that every constant function is bounded, right? So we know that 0 is a constant function, right? It implies 0 is bounded, right? Since every constant sequence is, since every constant function is bounded, that's why 0 is also bounded. What does it mean? It will belong to this set, right? And we know that addition of two bounded function is still a bounded function, so closure under addition satisfied. And similarly you can show that scalar multiplication will also satisfy, and rest of them we have already proved, right? So this is again your homework, right? Try to prove the theorems 2 to 3 times, okay? Only then you will be able to make your basic very strong, right? So next, what it is saying, it is saying that determine which of the following subsets of Rn are subspaces, right? See what it is, this is linear and the RHS is 0, right? So it will form a subspace. And this is, what is it? See, this is a linear condition, right? And RHS is equal to C, where C is a fixed constant, right? So students, when it will form a subspace? It will form a subspace when subspace if C is equal to 0, right? And it will not form a subspace if C is not equal to 0, right? If C is equal to 0, then this will form a subspace. If C is not equal to 0, then this will not form a subspace, right? Now what about these two, right? So see, what is this one? So let W is equal to alpha equal to, and alpha is of the form this one, such that A1 is less than equal to 0, right? So let us choose any element from here, right? So students, yeah, 0 will be from here. Yes, 0 vector allowed. So I think scalar multiplication may be fail, right? So see, let A1 must be 0 or negative, right? So I am choosing that alpha is equal to minus 1, right? And it will be, I think, 0 0 0 0 0 0 0 0, okay, n times, right? Let us choose this element from the set W. So let alpha belongs to W. Why alpha belongs to W? Because the first tuple is minus 1, right, according to the condition, right? Now choose, we can choose an element C from F, right? What is F? F is my R, okay. So let us choose C is equal to minus 1. Why? Because we know that minus 1 always belongs to the field, right? So we are choosing that element. Right now check the scalar multiplication. If you choose if you check scalar multiplication, then it will be C into alpha, and this is equal to minus 1 into this tuple, minus 1 0 0 0 dot 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 0 n times, okay. And what it will be? And it will be equal to minus 1 into minus 1, it will be equal to plus 1, and then the rest will be 0, right? So students, see, this is not an element of W. Why? Because this is not less than or equal to 0, right? So this does not belongs to W, right? What does it imply? That not closed under scalar multiplication, that W is not closed under scalar multiplication, right? So not a subspace, right? So this is not a subspace. Now what about this one? So you can see that if you choose, what is given, that A3 is an integer, right? So let us choose an element. See, here I am also showing the scalar multiplication, right? So if we choose alpha equal to 0 0 1 0 dot 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 0 n times, okay, this belongs to W. Let this is W, right? So see, this belongs to W. Why? Because the third entry is my integer, right? A3 is my integer. Now if we choose C equal to 1 by 2, right? So students, does this 1 by 2 belongs to the set of real numbers? Why? Because this is a field, so definitely it will belong. Why? So how can you justify that this will belongs to the field, right? So see, how can we justify? See, yeah, basically you can see that this is a member of R, but how can you justify if I ask? So you have to say like that. See, I am giving you the steps, right, that how to connect. See, since we know that 2 belongs to R, right, and we know that since R is a field, so by additive inverse property, the inverse or so by the multiplicative inverse property, the inverse of 1 by 2 will be also there, right? So that's why this belongs to R, because of multiplicative inverse, right? So now see, now if we check the scalar multiplication, then what will we get? This will be equal to 1 by 2 into 0 0 1 0 dot 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 n, right? So it will be equal to 0 0 0 1 by 2 0 dot 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 0, right? So students, see, the third entry is not an integer, right? That's why this C alpha does not belongs to the set W, this one, okay? That's why, sorry, this one, right? That's why this is not a subspace, okay? So this is the way to write the problem's solution, okay? I hope you are enjoying the lecture, right? I hope you are understanding each and every concept, right? And I hope you are able to solve the questions, right? So next, what it is saying, determine which of the following subsets of Rn are subspaces. So students, you can see that what is it? It is a1 plus 3a2 minus a3 equal to 0. What it is? This is linear plus RHS is 0. So yes, this is a subspace. Similarly, you can see that a2 minus a1 square equal to 0. See, this is my non-linear. That's why this is not a subspace. Similarly, this is a non-linear. This is not a subspace, right? So what about this one? A2 is rational. What about this one? Think. Okay, just think about it. This is your homework, right? So students, solve all the questions which I have given you as homework, right? Don't skip any question, okay? And if you find any difficulty, then comment your doubts. I will make you reply, okay? So this is your homework, that check whether this forms a vector space or not, right? Sorry, this forms a subspace or not. So next, so what it is saying? It is saying that let V equal to this one, determine which of the following are subspaces. So students, see, what is this? This is basically the set of all n cross n matrices, right? And students, see, we have proved that upper triangular, lower triangular, diagonal, singular, symmetric and skew symmetric forms a subspace, right? And we have proved it for 2 cross 2 matrices, right? So I hope you will be able to prove it for n cross n matrices, right? So prove all. This is your homework, right? And see, now we have to check whether the scalar matrices forms a subspace or not. So students, see, basically we have to know that what is the meaning of scalar matrices, right? So scalar matrices means a matrix, right, in which all the diagonal elements are same, means all the diagonal elements are same, right, and the rest values are 0, right? So this kind of matrix is called scalar matrix, right? And students, if you take a set of it, then you can see that yes, this will form a subspace. Why? Because 0 will be here. Why? Because if you choose lambda equal to 0, so see, all the diagonal entries are equal, right, and rest are 0, right? So it satisfies the definition of scalar matrices. So this is a scalar matrix, so this will belongs to it, right? Similarly, if you add or if you take a scalar multiplication, then again you can see that this will be in this matrix, right? So this is a subspace, right? So write it theoretically, right? Now see, what is tridiagonal matrix? A matrix, right, in which diagonal, this is called super diagonal and this is called subdiagonal, right? A matrix in which all of these diagonals have non-zero entries and rest have 0, right? So check whether this forms a subspace or not. So this is also your homework, right? And what it is? It is non-singular matrices. What does it mean by non-singular? Means determinant is not equal to 0, right? So see, students, this will not form a subspace. Why? See, non-singular means determinant should be non-zero, right? So there will be no 0 matrices, right? Why? Because determinant of 0 matrix is 0, right? But it is asking for non-zero matrices, non-singular matrices, right? So 0 will not be here. And you can see that addition will also not satisfy. If you choose A equal to identity matrix and B equal to this matrix, right? So if you add, then you will get A plus B equal to 0 matrix, right? So see, determinant of A is 1, determinant of B is 1, right? But determinant of A plus B is not 1. That's why it fails closure under addition also, right? And what about this one? Matrices having determinant equal to 1, right? So similarly you can see here, determinant is 1, determinant is 1, right? But see, determinant is 0. So by this example we can show that yes, this will not form a subspace, right? So I hope I am able to make you understand each and everything. And students, whatever I have given you as homework, solve all of them, right? Solve all the questions, right? Now see, I have given you some list, right? Just go through it at once. See, upper triangular matrices, subspace, yes, 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 all of them will form subspaces, right? And what about this is singular matrices, no, it will not form subspace. Region, it fails this condition, right? Non-singular, this, so go through all of them, right, at least once. See, basically I am not discussing here each and everything. Why? Because this is the topic of matrices, right? I will take a separate video on it, right? So for now, just go through them. So students, next, theorems on subspace. So students, till now we have proved only one theorem. What was that? It was the necessary and sufficient condition of a subset of a vector space to be a subspace, right? And based on these theorems we have solved a lot of problems, right? So now we will solve the remaining one. See, this is done. Now we will prove this one and all of these, right? So what it is saying? It is saying that prove that the intersection of two subspaces W1 and W2 of a vector space VF is also a subspace of VF, right? So see, so students, see what we have to prove. We have to prove that intersection of W1 and W2 are subspaces, right? And what we have given, that W1 and W2 are subspaces of VF, right? So students, what is the approach to solve a theorem? At first write given that, right? So see, I am writing given that. After that write the given data. What is the given data? See, prove that intersection of any two subspaces W1 and W2, right? So it is given that W1 and W2 are subspaces of VF, right? So write it. It is given that W1 is a subspace of V over F, right? And the second condition is given that W2 is a subspace of V over F, right? This is our given data. Now write claim. So students who are preparing for your semester level examination, right, this is for you, right? Fill the proof. Now what is our claim? Our claim is that the intersection of two subspaces. What does it mean? Our claim is that W1 intersection W2 is a subspace, right? So see, this is our given data, this is our target, right? So as a mathematician, you have to think logically that how can you reach from here to here, right? So see, let me change the color. I hope you are enjoying the lecture and you are learning the mathematics from the basic, right? So see students, how can you think it? See, W1 is a subspace of VF, right? What does it mean? It means that it will satisfy all the conditions of subspaces, and this will also satisfy all the conditions of subspaces, right? See, since W1 is a subspace, so 0 vector will be there, right? Similarly, W2 is a subspace, so 0 vector will be also there, right? So see here, 0 vector belongs to W1 and 0 vector belongs to W2, right? So what does it mean? It means that, write like that, since 0 belongs to W1 and 0 belongs to W2. What does it imply? It will imply that 0 will belongs to the intersection 2. Right? See, from the given condition we got it. Right? So first condition proved. Right? Now we have to prove the remaining two conditions, that it is closed under addition and it is closed under scalar multiplication. So see, closure under addition. Right? See, so how can we prove? So what was the approach to prove? See, this is our subspace, right? So how it is defined? See, closure under addition. So at first we have to take two elements from the set, right? So choose, let alpha and beta is from the set W1 intersection W2, right? Now see, W1 is a subspace, means this is a subset, this is a subset. So this is a set, this is a set. Intersection of two set is still a set, right? So it means W1 intersection W2 is a set, right? What it is? It is basically set. Okay. So if we assume two elements from that set W1 and W2 alpha beta, what does it imply? By set theory, what we get? We will get that alpha will belongs to W1 and alpha will belongs to W2, right? Similarly, beta will be from W1 and beta will be from W2, right? See, so we get that in W1 there are two elements, right? Alpha beta, and in W2 there are again two elements, right? So see, we choose two elements from this set and by the given condition we get this one, right? Now what we have to show? We have to show that alpha plus beta belongs to W1 intersection W2, right? So see, alpha plus beta. Now see, here is a magic. What is the magic? See, W1 is a subspace, right? W1 is a subspace and this is an element of W1, this is an element of W1, and we know that in a subspace, means subspace is closed under addition. So by using that property, right, if you use that property, then this is an element, this is an element, so their addition will also be from W1, right? So what does it imply? It implies that alpha plus beta will be from W1. Similarly, you can see that W2 is also a subspace, right? And these are their two elements. So if we add them, alpha plus beta, by using the second property of subspace, what will we get? We will get that this will also belong from W2, right? What does it imply? It will imply that, see, alpha plus beta belongs to W1, alpha plus beta belongs to W2. It means that alpha plus beta will belongs to the intersection 2, right? See how I am using the logics here, right? See, alpha beta belongs to this set, right? So alpha beta will be from this and alpha beta will be from W2 also, right? So since alpha beta is from W1 and W1 is a subspace, so alpha plus beta will be from W1. Similarly, alpha plus beta will be from W2. Since alpha plus beta belongs to W1 and W2, so it will belongs to intersection 2, right? So the second condition satisfied, closure under addition, right? Similarly, by using the same logic, we can show that this is closed under scalar multiplication 2. See, closure under scalar multiplication, right? So at first let us choose an element from the field, right? So see, let C belongs to field, right? And alpha belongs to W1 intersection W2, right? This is my set and we are choosing like that. Now see, if see alpha belongs to W1 intersection W2, what does it imply? By set theory, alpha will belongs to W1 and alpha will belongs to W2, right? And see, since alpha belongs to W1, so by scalar multiplication property we can say that this is belongs to W1. Why? Because W1 is a subspace. Similarly, C alpha will be belongs to W2. Why? Because W2 is a subspace, right? So see, C alpha belongs to W1 and C alpha belongs to W2. What does it imply? It implies that it will belongs to W1 intersection W2, right? So see, it satisfies the closure under scalar multiplication 2, right? So from the standard subspace test we can say that yes, W1 intersection W2 is a subspace. So students, if you are preparing for your semester level examination, right, so try all of these proof by yourself. Okay, now see, okay students, suppose if case 1, right, I am dividing it into two cases, right. Now suppose if W1 intersection W2, if it will be equal to this, right, then what will happen? Basically, why we are saying like that? So students, see, here it is given that W1 and W2 are subspaces, right. So this is my vector space V over F, right. This is my W1, okay, and another is my W2, right. So students, it is given that these are subspaces, but is it mentioned that whether this is proper or this is improper or this is trivial, right? It is not mentioned that whether these subspaces are proper subspaces or improper subspaces or trivial subspaces, right? So that's why we have to check for everything, right? So see, if okay, one more question, that if okay, let me write the question. See, if W1 and W2 are subspaces, okay, then is there any chance that their intersection will be equal to phi? Is there any chance that the intersection of two subspaces will be equal to phi? Just think at once, right? Pause for 1 minute and think, right? That if W1 and W2 are two subspaces, then is there any chance that W1 and intersection W2 will be equal to phi? No, there is no chance. Why? Because see, it may be possible that in W1 and W2 there are no common elements, right? But there will be at least one common element. What? That is identity element, right? Why? Because by the condition of subspaces we have seen that 0 will always belongs to the subspace, right? So since W1 W2 are subspaces, so 0 will always be there in their intersection, right? That's why we are taking W1 intersection W2 equal to this set, and we know that this is a trivial subspace and we have proved it, right? So students, since here it is not mentioned that W1 and W2 are what kind of subspaces, is it proper, improper or trivial, that's why we are breaking this proof into two cases, case 1 and case 2, right? Case 1, and what is case 2? Case 2 is W1 intersection W2 is not equal to 0, right? So for that, this is my proof. So students, I have written this proof for you here, right, in a very detailed way for semester level examination, for semester exams, right? See, what it is given, that theorem, let W1 and W2 be two subspaces of vector space V, then W1 intersection W2 is a subspace of V, right? So what they have taken, that W1 intersection W2 be two subspaces of V. See, we have to show that W1 intersection W2 is a subspace of V. For that we have to check three conditions, right? Which three conditions? Subspaces condition, right? See, case 1, intersection equal to 0, 0 is a subspace of V, trivial subspace, hence this is proved. And now this is the second condition, you can go through it, okay? And see, here I have added some diagrams also, right? So just go through it, okay? And here is my note, just read the note, right? So next, what it is saying? It is saying that prove that union of two subspaces W1 and W2 is a subspace if and only if one is contained in other, right? What it is meant, that there are two subspaces, right, and their union is a subspace only when one will be contained in another, right? Otherwise it will not form a subspace, right? So we will see the example of it, right? but let us prove it first. So see, so what we have to do, at first we have to write that given that and the condition, right? So see, what is given? It is given that W1 and W2 is a subspace, right? And W1 union W2 is a subspace, right? Now what is our claim? We have to prove that one is contained in other, right? So it means that either W1 will be contained in W2 or W2 will be contained in W1, right? So see, at first we are assuming this one, right, this thing, and we are proving this thing, and in the second part we will assume this one and we will prove that W1 union W2 is a subspace, right? So see, this is our claim. So let's begin the proof. So let's begin the proof, right? So we will prove it by contradiction, right? So at first we will write that let us assume that this condition does not hold, right? This is the way to prove of contradiction, right? So let us assume that this does not hold. What does it mean? It means that W1 is not contained in W2 and W2 is not contained in W1, right? See, this is not contained in this one. What does it mean? It means that there will exist at least one element which will be in W1 but which will be not in W2, right? So see, so implies there exists X belongs to W1, right? There will be an element X belongs to W1 such that X will be not in W2. Similarly, for this case, there exists an element Y in W2 such that Y will be not in W1. Students, I hope I am able to make you clear each and everything, right? And see, I am advising you that till now everything is clear, right? If not, then read it again and think. Okay, so now see, since X belongs to W1 and X1 is a subspace, see, this element is in W1, right, but not in W2, and we know that W1 is a subspace, right? So in a subspace, right, for each element we can get an additive inverse element. How? By using the scalar multiplication, right? If we multiply it by -1, then we will get -x, right? So since X is an element of W1 and W1 is a subspace, so it means that you can see that it means -x will belongs to W1, right? Similarly, we can show it for this one, that -y will belongs to W2, right? So see, right, now see, since X belongs to W1, right, since X belongs to W1, so this X will belongs to W1 union W2 also, right, by using the set property, that if X is an element of A, then definitely it will be the element of A union B union C, right? So by using that property we can say that yes, X can be belongs to W1 union W2, right? Similarly, Y can be also belongs to W1 union W2. Now see, it is given that W1 union W2 is a subspace, right? So this is a subspace and these are two elements, right? And since W1 union W2 is a subspace, so it will be closure under addition, right? Since it is closure under addition, so their addition will be also in W1 union W2, right? So just write it. See, so X plus Y will be from W1 union W2, right? Now see, by using the set theory, we can say that if an element is belonging from the union of two set, what does it mean? It means that this X plus Y may be in W1, this X plus Y may be in W2, right? So we will take case 1 and case 2, that let X plus Y belongs to W1, right? And in case 2 we can check for X plus Y belongs to W2, right? Or it may be also possible that X plus Y are in both of the sets, right? So see, case 1, see, X plus Y belongs to W1 or X plus Y belongs to W2, right? Next, case 1, right, we will take this one, let X plus Y belongs to W1, right? What does it imply? See, W1 is a subspace, right? And we know that minus x belongs to W1 from 1, right? So see, from 1 we have minus x belongs to W1, right? So see, this is an element of W1, this is an element of W1, right? And W1 is a subspace. So by using the closure under addition, we can say that their addition will also be from W1, right? See how I am using the logic, right? How I am using the definition, how I am using the logics, right? Just you have to learn it. If you are a semester student, then it is very helpful for you. Next, see, so add it, x plus y plus minus x, so it will be equal to this one, and this is equal to y, right? And y belongs to W1. So see what we get that y belongs to W1, but what we assumed that y belongs to W2 and y does not belongs to W1, right? So see, we have taken one thing, right, and we have reached here where we find that no, this is contradiction, right? So hence this is a contradiction, right? So what can we say? That our assumption is wrong. Okay, similarly we can show it for this one also, that if x plus y belongs to W2, right? So from here we can show that, see, we will take this one, x plus y minus of y, right? And at that case we can show that x belongs to W2, which will be the contradiction, right? So similarly we can show that this condition holds, right? So see, therefore what we get that if W1 union W2 is a subspace, then either this one belongs, W1 belongs to W2, or W2 will belongs to W1, right? So hence proved. Okay, so students, see what we have done step by step. See, at first we have assumed that this condition does not hold, right? After that we have proved that our assumption was wrong, right? And to prove it, we have used the definition of subspace and conditions of subspaces, right? So students, see, now the second part. What is the second part? We have to assume that this one, and we have to prove this one, right? So see, right, given that, let me change the color. So right, given that, what is given? It is given that either W1 is contained in W2 or W2 is contained in W1, right? Now what is our claim? Our claim is that W1 union W2 is a subspace, right? And students, there are one more condition, that W1 and W2 are subspaces, right? So by using these conditions we have to prove this. So this is very easy, right? How can we prove it? So see, if we choose this one, right? So if W1 is a subset of W2, right? What does it imply? It implies that W1 union W2, it will be equal to W2, right? How? Suppose this is your set W1, right? Suppose this is your set W2, this is your W1, right? W1 is a subset of W2, right? If you take union of it, right, what will you get? You will get W2, right? So we have done it, right? And students, we know that W2 is a subspace from our given condition, right? So hence you can say that since this is a subspace and this is equal to this, so this is a subspace. Similarly, you can show it for this one. W2 is a subset of W1, right? So W1 union W2 will be equal to W1, right? And again, see, W1 is a subspace, right? So this is a subspace and this is equal to this one, so this one is a subspace, right? So this is the complete proof. And students, I have written it for you, right? See in the next page. Just go through it. This is beneficial for your semester exams, right? So next, what it is saying? It is saying that prove that the linear sum W1 plus W2 of two subspaces is the smallest subspace of VF, containing both W1 and W2, right? So what is the given condition? See, it is given that W1 and W2 are two subspaces, right? And students, we have to prove this theorem in two parts, right? What was the first part? The first part will be that we have to prove that W1 plus W2 forms a subspace, right? And then in the second part we will prove that it is the smallest subspace which contains both, right? So see how we are proceeding. So let me change the color, right? So given that this is my part 1, okay? See what is given. It is given that W1 and W2 are subspaces, right? And what we have to prove, means what is our claim? The claim is that W1 plus W2 is a subspace, right? So students, as a mathematician, how can you think that from this given condition how can we reach at this place, right? So let's see proof. Okay, see students, at first we have to define this set, right? That how does this set will look like. So see, W1 plus W2, it will be equal to of the form small w1 plus small w2, right? Such that W1, small w1 is the element of capital W1 and small w2 is the element of capital W2, right? So basically this is our set, right? Students, now as you know that we have to check only three conditions to prove that whether this set forms a subspace or not, right? So see how we are going to proceed, right? So at first we have to check that whether the zero vector belongs to it or not, right? So students, see, since W1 is a subspace, right? So it will satisfy all the three conditions, right? So it will also satisfy this condition that 0 will be from W1, right? Similarly, by the same argument you can say that 0 belongs to W2 also, right? And students, if we choose this W1 and this W2 equal to 0, then what will we get? Then we will get 0 plus 0, it will be equal to 0, right? See, this 0 is from W1 and this 0 is from W2, right? So 0 plus 0 equal to 0, right? So students, see, we are getting an element which is of the form this one, right? Which is of the form this one. What does it mean? That it means, it implies that this 0 belongs to W1 plus W2, right? So students, see, the first condition has been satisfied, right? Now let us check the second condition. I hope I am able to make you understand each and everything. If not, then comment section is only for you. Comment there, right? Now let us check the second condition. Okay, what was the second condition? Closure under addition, right? Closure under addition. So we have to choose two elements from this set, right? So let us choose it. Let me change the color first, right? See, let U and V belongs to the set W1 plus W2, right? What does it imply? It implies that U belongs to W1 and no, let me check it. Yeah, let UV belongs to W1 plus W2. What does it imply? It will imply that, let me erase it, okay? It will imply that U will be of the form U1 plus V1, right? And V will be of the form U2 plus V2, right? Why? Because these are the element of this set, right? So see, if we add them, then what will we get? Oh, see, one more thing. Here U1 will be from W1 and V1 will be from W2. Similarly, U2 will be from W2 and U2 will be from W1 and V2 will be from W2 by this condition, right? Now let's see the addition. So add U plus V, u plus v. What will you get? You will get u1 plus v1 plus u2 plus v2, right? So students, see, if we rearrange it, then what will we get? See, if we rearrange, then we will get u1 plus u2 plus v1 plus v2, right? So students, see, u1 is from w1, u2 is from w1, right? So u1 plus u2 will be from w1, right? Similarly, v1 is from w2 and v2 is also from w2. So if we add, then we will get this v1 plus v2 will also be from w2. Why? Because w2 is a subspace, right? And similarly, w1 is a subspace. By using this logic, we can say that yes, this belongs to w1, this belongs to w2. So students, see what we get. Finally, we have found that u plus v is of this form. See, an element from w1, an element from w2. This is of this form. What does it mean? It implies that u plus v belongs to the set w1 plus w2, right? Hence, it is closed under addition 2. Right, now the last condition. What is the last condition? Last condition is scalar multiplication, right? So see, if we choose, let me change the color. If we choose C belongs to F, right, and let an element u belongs to w1 plus w2, right? What does it mean? It means that u will be of the form u1 plus u2, right, where u1 is from w1 and u2 is from w2. You can change the notation, right? No issue. Instead of u, you can tell w, a, b, c, d, whatever you want, right? But understand the concept, right? So see, now check the scalar multiplication. It will be c into u1 plus u2, right? What will you get? By distributive property, cu1 plus cu2. And students, see, this is an element of w1, right, and this is an element of w2, right? Since w1 is a subspace, so this will belongs to w1. Why? Because of scalar multiplication. Similarly, this belongs to w2. So see, cu is equal to this one, right, which is of the form this one. So it implies that cu belongs to w1 plus w2, right? Hence the scalar multiplication condition also satisfied, right? So therefore w1 plus w2 is a subspace. Proved, right? So part 1 we have completed. Now we have to prove that this w1 plus w2, right, is the smallest subspace of Vf, right, which contains both w1 and w2, right? So see, so for our understanding, at first we have to write the given data, right? So students, this is part 2, right? See, given that, what is given? It is given that first one is w1 and w2 are subspaces, right? And what is the second data? The second data is w1 plus w2 is a subspace, right? And now what is our claim? Our claim is that w1 plus w2 is the smallest subspace that contains both w1 and w2, right? So let's prove it. How can we prove it? So students, see, what will be the approach? At first I am giving you the approach, that how we are going to approach it, right? Sorry for the spelling mistake, let me correct it. See, what we have to prove? We have to prove that this set is the smallest subspace that contains both, right? So see how I am going to approach it, right? So see, I have to prove that w1 plus w2 is the smallest, right? Right? What does it mean? That if this is my w1 plus w2 set, right, which contains w1 plus w2, then this is the smallest set, right? So we will take another set, right, which contains this one, right? Sorry, this is not w1 plus w2, this is w1 and w2, right? So we will construct a set, right, which contains both of them, right? So we will construct a set. We are constructing a set U, right? See the approach. Suppose we are constructing a set U, right, which consists w1 and w2, right? So students, see, we are taking this U as arbitrary. This is my arbitrary set, right? What does it mean by arbitrary? That all the sets which contains w1 and w2, let us call it U, right? So suppose if this is your vector space V over F, right, and here is your w1 and here is your w2, right, then this U is a set that it may be U, right? See, this is a set which contains w1 and w2, right? So this may be U. And secondly, this is also a set which contains U and W. Sorry, this contains w1 and w2. So the U may be this set. Similarly, the U may be this set also, right? So we are assuming, and similarly you can say the smallest here, right, maybe this is the set, right, which contains w1 and w2, right? So it may be also mu. So it may be also U. Sorry for the pronunciation, right? See, just manage little bit, right? I am making a lot of effort for it, right? So see. So now what will we do? We are choosing a set U which contains this one, and we are saying that it's arbitrary, right? So any one of it can be it, right? So now we will show that if you choose any U, right, then I can show you that inside every U, I can show you there exists a w1 plus w2, right, which contains w1 and w2, right? So if this is your U, then I can show that there exists a w1 plus w2 inside this set, right, which contains this one, right? See, I am writing again. So see, idea is the main thing, okay? Idea, logic and approach. This is the building block of mathematics, right? And this is the beauty of pure mathematics, right? So see, this is my V over F, this is my w1, this is my w2, right? And if someone is saying that this is my U, right, then I will show them that yes, inside U there is another set, right, which contains this one, right? If someone is coming and saying no, this is my set U which contains w1, w2, then I will come and again I will show them no, inside U there is again a set, right, which contains both of them, right? If someone comes and says no, inside this there is a set, right, which contains w1, w2, right, then I will come and I will show that inside this set also there is another set which contains both w1 and w2, right? And I will show that this is not other set, this is especially this set, right? What I have said, that suppose this is your vector space V, right, this is your w1, this is your w2 set, right? And if someone is saying that this is my U which contains both, then I will show that this w1 plus w2 is inside this, right, inside U which contains both of them. If someone is coming and saying that this is my U, right, this is my U, right, which contains both, then I will come and then I will show them that inside this U there is another set w1 plus w2 which contains both, right? So students, I hope I am able to make you the approach very clear, right? Though it is taking time, but this is a very big thing to enhance your thinking, right? It will enhance your thinking, right? So this is a good investment for you. So next we are going to prove it. We will let that there exists another subspace U, right, which contains w1 and w2, right? Then we will show that inside this U there is another set w1 plus w2 which contains w1 and w2, right? Since we are taking U as arbitrary set, right, So that's why we can conclude that for every set which contains this one, right, there is a set this one, right, and by this we can prove it, right. So this is going to be our approach. So see the proof. So at first let U be any subspace that contains W1 and W2. What does it imply? It implies that W1 is a subset of U, right, and W2 is a subset of U, right. From this we get this one, right. Now what we have to prove? Our claim is to prove that W1 plus W2 is a subset of U, right. So I am writing here, okay, in a different color. What is our claim? Our claim is that W1 plus W2, this is the set, and what kind of set it is? It is W1 plus W2, right, which belongs W1 plus W2 such that W1 is from capital W1 and W2 is from capital W2, right. So this is the set, and we have to prove that this set is a subset of U, right. Basically this is our target, right, and this is our assumption now. Okay, so see, let me change the color. See, for that, see, to show that a set is a subset of other set, right, what we need to do? At first we have to take an element from A, right, and we have to show that this element is also from this set, right. So this is the approach to show that a set is a subset of other, right, where x is an arbitrary element, right. So see, we are taking an element from this set, right. So let x belongs to W1 plus W2, right. Since x belongs to W1 plus W2, so x will be of the form this one, right. So it implies let x is equal to W1 plus W2, right, where W1 is from W1 and W2 is from W2. You can take any other alphabet, right, but know the approach, okay, and always use the condition in a correct way, right. So see, x is from this set and this one, right, and students, see, here it is given that W1 is a subset of U, right. So write it. See how I am connecting each and everything. See, W1 is a subset of U, right, and W2 is a subset of U, right, and students, see, W1 is an element of W1, right. So this is an element of this small W1 is an element of W1. Similarly, small W2 is an element of W2, right. What does it imply? It implies that W1 is a element of U, right, and it implies that W2 is an element of U, right. And students, see, since U is a subspace, right, U is a subspace, right, so it will satisfy all the three conditions of standard subspace test, right. So it will satisfy the zero vector, closure under addition, closure under scalar multiplication too, right. So see, here are two elements of U, right. So if we take addition of it, right, so by using the subspace property of U, if we add them, right, so definitely it will belongs to U, right. So students, see, W1 plus W2, these are my elements, right, where W1 is from capital W1 and W2 is from capital W2, right. So students, see, this is an element of this set, right. So what it was equal to x, right. See, this was equal to x, so it implies that x belongs to U. So see, we have taken an element from this set, right, and we have showed that this element is from U. What does it mean? It means that this set W1 plus W2 is a subset of U, right. So students, see, finally we have proved it, right? Now you can think the approach what I have discussed earlier. Okay, so hence proved. So you can write it like that. Okay, and for your semester exams I have written here. Okay, just go through it. See, step 1, step 2, right? There are diagrams, just go through it also. Okay, so next, what it is saying that state and prove the necessary and sufficient condition for a vector space V to be the direct sum of its two subspaces W1 and W2. Okay, so students, see, this is actually direct sum related theorems, right? And till now I have not teach that what is direct sum, right? So I will continue after few minutes later. So wait, okay, I will teach it in this lecture, don't worry. I will not going to make a separate lecture for it. So see, next, what it is proved that the quotient set, this one forms a subspace over the field F under quotient operation, right? So students, see, here are few new terms, right? So at first let us define that. Okay, so see, what is V by W? We don't know, right? What is quotient operation? We don't know. Okay, student, basically this is the part of abstract algebra, right? When you read the group theory, ring theory, right, there you will learn it in a very detail. But don't worry, I will give you a basic idea about that so that you can prove this theorem. Okay, see, what is quotient? So students, see, suppose you have a vector space V, right? Suppose this is your vector space V over F, right? And suppose this is your subspace W, right? What is it? It is a subspace W, right? And suppose there is an element in V. Suppose this is my A, right? An element of V, right? This A may be an element of W also, right? But I am writing it outside so that you can get the clear idea, right? So what is the condition? That the A must belong inside V, right? So see, this is my V, this is my subspace, right? And there is an element A, right, in V, right? So how does a quotient is defined? So a quotient is defined as A means the element of V plus the subspace. See, this is subspace, this W, okay? This is set, okay? And this will be equal to A plus W. This is my element, right? This W is my element, okay? Such that W belongs to capital W. What does it mean? It means that this is my element of VF, right? This is my subspace. See, this is not an element, this is subspace, right? And you know that this is the element of VF and this is the element of this subspace, right? So this set, right, this set defined as this is called quotient, right? Just remember these things only, you can prove it easily. Okay, so students, see, this is my quotient, right? Now the set of all quotient, what I have said, the set of all quotient, see, set of all quotients, right, is called quotient set, right? Quotient set. The set of all quotient sets is called quotient set. What does it mean? That it is the set of all quotient, means this is the notation of set, right? And this is my A plus W, right? Where this is a subspace, this is not an element, right? Always remember it, such that A belongs to V, right? A is from V, see, this was my coset and this is the set of all cosets, right? And it is denoted by V over W, right? So students, I hope I am able to make you understand, right, step by step, right? So see students, what is the question? The question is that prove that this means this set forms a subspace, right? So we have to check that whether this set satisfies all the three conditions of subspaces or not. Okay, be patient. Okay, I am going to prove it. So students, one more question arises in our mind, that how does the operations are defined on this set, right? So see, I am going to tell. So the addition is defined as, suppose you are taking an element a equal to, no, suppose I am writing like, suppose you are taking an element a and b from V over W, right? So how does it will looks like? So it will look like a will be equal to, this will be of this form, so a plus capital W. Similarly, since b is an element of this set, so it will be of this form, so b plus W, right, where a belongs to V and b belongs to V over F, right, where this W is a subspace. This is not an element of subspace, right? This is the whole subspace, right? Now if we add it, right, then what will we get? We will get a plus capital W plus b plus capital W, right? So students, see, the addition of coset is defined like this. If we add them, then this will be a plus, means this one plus this one, element wise addition will hold, right, plus the W, right? So this is the way to add it. Okay, and how does the scalar multiplication is defined? The scalar multiplication is defined as, suppose this is an element of F, right? So how it will be defined? C into A, it will be equal to C into A plus W, right? So it will be like C into A, and the W means the subspace will remain same, right? So finally what we get, that the set of coset is called quotient set, right, and the quotient set is denoted like that, and it is defined as it, okay? And if you take two elements, right, then it will be of the form this, and if you add, then you will add like this, and if you multiply, then you have to multiply like that. Okay, so by using these things only, we are going to prove that this forms a subspace, right? So let us prove. See, so condition number 1, what it is? It is 0 element, right? So see how does this set is defined? This set is defined as equal to a plus W, right, where a is from V over F, right? So students, see, we know that in a vector space identity element is there, I mean additive identity, right? So since 0 belongs to V over F, right, so choose a equal to 0, right? If you choose a equal to 0, then what will we get? Then we will get that a plus W, it will be equal to 0 plus W, right? And we know that 0 plus W will be equal to 0, right? This is my subspace, not the element, okay? And we know that this W belongs to V by W, right? So see, we are choosing a equal to 0, right, and we are getting this, and this belongs to V by W, right? So what does it mean? It implies that this element belongs to V by W. Am I right? Okay, so students, see, we got an element, right, from 0 plus W. Now we will check that whether this is a 0 element or not, right? For that, what we have to check? For that, we have to check the additive, we have to check the additive identity property. Okay, so see, we have to let another element from the set v by w. So let another element, it may be u x. Okay, let x belongs to v by w be arbitrary. Okay, so if x is from v by w, so how does it will look like? So it will be equal to a plus w, right? So this is my any arbitrary element from v over w, right? So see, now check the identity condition, that if you add, then what will we get? So add it, a plus w plus 0 plus w, right? So what it will be equal to? So it will be equal to a plus 0 plus w, right? Which is equal to a plus w. Okay, see, we are adding an element with this element, right? And we are getting the same element as a result. Similarly, you can add like that, 0 plus w plus a plus w, it will be equal to 0 plus a plus w equal to a plus w. So see, what does it mean? It means that this is my identity element. Sorry, this is not. So it means that this is my identity element, right? So students, basically this is my 0 element, right? So 0 element of this set is looks like this one, right? So therefore 0 plus w is an additive identity and it belongs to v by w, right? So yes, the first condition satisfied. Now we have to check the remaining two conditions, right? So students, see, we have already defined, and from the operations you can check that if you take two elements from this set, right, if you add, then you will get this. And students, see, a is an element of v, v is an element of v, and v is a vector space, so their addition will be also an element of v, right? So see what we get, if we add two elements, then we are getting an element from v, right, plus w. So it implies that this a plus b will belongs to this set, right? Similarly, we can do it for this, right? C of a plus w, since v is a vector space, so this will also belongs to v, right? So yes, this set is closed under addition, this is closed under scalar multiplication, and 0 vector also belong. So that's why this is a subspace. Okay, hence proved. Okay, so students, I am going to give you a homework. Okay, what is the homework? Prove that this v by w forms a vector space. Okay, this is your homework. Prove that this forms a vector space, right? And students, don't worry, at first try at your side. Okay, at first try yourself, right? After that you can look at it. Okay, so next, see what it is saying. It is saying that prove that the solution set of a homogeneous linear system, this one, forms a subspace of Fn, right, while non-homogeneous system Ax equal to b does not, right? So student, this is basically that result which we have used, right, to show that whether a subset is a subspace or not in our short tricks, right? So see, we are going to prove it now. So what we have to prove? We have to prove that the solution set of the homogeneous system, this one, forms a subspace, right? So how does the set will looks like? So it will looks like Ax equal to 0 such that x belongs to the field Fn, right? So this is my set. Now we have to prove that this forms a subspace, right? So we have to check three conditions. So let's check it. Number one, so see, we know that f is a field, right? So 0 will be in that field, right? So choose, so if we choose x equal to 0, then what will we get? Then we will get that Ax equal to 0, right? What does it imply? It implies that this 0 belongs to w, right? So yes, first condition satisfied, right? See, we are just choosing x, right, and we are checking whether that this condition satisfies or not. Yes, this condition has been satisfied, right? That's why this is a element of this set, right? Now the second one, addition property, check it. Let us choose two element, UV. Okay, let UV belongs to W, then what it imply? Then it will imply that U will be of the form AU equal to 0 and B will be of the form AB equal to 0, right? It will satisfy this condition, right? Sorry, if UB is from this set, then it will satisfy this condition, the given condition, right? Now we have to check that whether this U plus V belongs to W or not, right? So let's check. How can we check? So see, according to the given condition, U plus V should satisfy this condition, right? So A into U plus V, right? If this is equal to 0, then we can say that yes, this U plus V is from W, right? So see, so break it, what will you get? AU plus AV, right? And students, see, from equation 1 and 2, what will we get? We will get that 0 plus 0 equal to 0. So yes, finally we get that A into U plus V equal to 0. What does it imply? It will imply that U plus V is from the set W, right? So closure under addition is also satisfied. Now the last one, scalar multiplication, right? So if you choose any element C from F, right, and any element U from W, right, now multiply it. If you want to check whether this belongs to that set or not, what you have to do? You have to multiply it with a it will be equal to, okay, use the associative property, right? Take it outside, then we will get A into AU, and we know that AU equal to 0, right? So A into 0 this. So see, we get A into CU is equal to 0. What does it mean? It means that CU belongs to W. Hence it is closed under scalar multiplication also. So by the standard subspace test, we can say that yes, these W forms are subspace, right? So this one is proved, right? Let me change the color. So this one is proved, okay? And what about this one, homogeneous system AX equal to B, B is not equal to 0, does not. So see, the 0 vector will be not here, right? It will lack the 0 vector condition, right? So that's why it will not be. So homework, okay, do it yourself. See next, see students, I have written it for you, okay, for your semester examination. Just go through it, okay? We are going to solve a lot of problems, right? See, after that we will move to the direct product, okay? So see, what is the next question? It is asking that let V1 V2 be subspaces of a vector space V. Which of the following is necessarily a subspace of V, right? So see, V1 intersection V2, yes, we have proved it, right? So yes, this will be a subspace, right? What about this one? See, what was the statement of the theorem that W1 union W2, right? W1 union W2 is subspace if and only if W1 is contained in W2 or W2 is contained in W1, right? So this was our statement, right? So here they are asking that whether this forms a subspace or not. So student, see, here the conditions are missing, right? That's why it will not form, right? If you want, then I am going to give you an example, right? Suppose this is your vector space, right? This is your counter example, okay? Suppose this is your R3, right? This is your set S and this is your set T. These are subspaces of R3, okay? So now let us define the set S such that X, Y, Z belongs to R3 such that X equal to Z equal to 0, right? And T equal to X, Y, Z belongs to R3 such that Y equal to Z equal to 0, right? So students, these are my subspaces, right? Now you have to check that whether S union T is a subspace or not, right? So see, let X belongs to S. What does it imply? So S will looks like, sorry, X will looks like X is 0, Y can be anything. So let us choose Y is equal to 1 and let Z is equal to 0, right? Similarly, since T belongs to, since Y belongs to T, so it will imply Y equal to 1 0 0, right? So students, see, since X belongs to S, right, so X will also belongs to S union T, right? Similarly, T will also belongs to S union T, right? So students, see, we have two elements from a set, right? What is it? This is basically a set S union T, right? So this is two elements from that set, right? Now add them. This is T, okay? Sorry, this is Y, not T. So if we add X plus Y, right, then what will we get? Add it, you will get 0 1 0 plus 1 0 0. What it is? It is equal to 1 1 0, right? So students, see, does it belong from this set, right? See, so how can we think about that? So see, this is our element, right, and this is of the form this, okay, and we are claiming that this is from S union T, right? So see, if, why are we taking like that? Since if this is a subspace, right, if S union T is a subspace, then it will satisfy the closure property, right? And if it satisfies closure property, then X plus Y, it will belongs to S union T, right? It will belongs to S union T. Now check whether that this element belongs to S union T or not. So see, it is given that 1 1 0 is from S union T, right? What does it imply? 1 1 0 implies S union T. It implies that either this must belongs to S, right, or either this must belongs to T, right? But students, see, neither this belongs to S. Why? Because see, in S there are elements whose entries are 0 at first and last position, but see, in the first position this is non-zero element, so this does not belongs to T. Similarly, you can see that this is not belonging to T. Why? Because in this case my X is Y and no, in this case my Y should be 0, but see, Y is not 0, right? So this element is not belonging to S, neither T, right? So what does it imply? It implies that it will not belongs to S union T also, right? So we get a contradiction that we are taking two elements, but we are seeing that is it not closed under addition, right? We are taking an element from this set and we are getting that this is not closed under addition. That's why this will not form a subspace. Okay, so this was my counter example. Next, see this one. Yes, this one will always form a subspace. Now what about this one? Think about that. Always think about the notation first, okay? See, this is not the notation of quotient group. Why? Because the notation of quotient group was like this type, see, V/W, right? But this is V1 difference V2, right? This is different relation, right? This is different sign, okay? So just think about it, okay? And students, I am saying that it will not form a vector space, right? Why? Because 0 vector will not belong to this set. Why? Because we know that 0 belongs to V2, and in this set there are only those elements which belongs to V1 only, right? Not V2, right? So see, I am just defining the set here for you. Rest will be homework for you, okay? See, it will be equal to X belongs to V1 such that X does not belongs to V2, right? This is the set, and see, 0 will not be here. So this is your homework. Prove it theoretically, okay? I hope you understand, and if you have any doubt, then comment section is only for you. Write your doubts in your comment section, right? I will make you reply. So next, what it is saying, see which of the following are subspaces of R3, right? So students, you can do it at yourself, right, using the shortcut trick. Okay, so clearly you can see that yes, linear 0, yes, linear RHS 0, yes, linear RHS not 0, not a subspace, not 0, not a subspace, right? This is a fraction of seconds question. Okay, so next, see again, this is linear 0, linear 0, yes, this is a subspace. But in this case, if you rearrange it, then what will you get? Rearrange this one, what will you get? 2x plus 3y plus 4z, it will be equal to 3, right? See, linear non-zero, not a subspace, right? Similarly, you can see, yeah, x is greater than 0, y is greater than equal to 0, right? So this will also not form a subspace. Why? A scalar multiplication will fail. If you multiply with -1, right, with this vector, then this condition will not hold. Okay, and you can say that in this case 0 vector will not be there, right? And in this case again 0 vector will be not there, right? If you write, then you will get this one, linear non-zero, not a subspace, right? So here A is the only correct answer, right? And if you are a semester level student, then please prove it theoretically. Okay, you have to check all the condition for each one, right? So next, what it is saying, see, this is a very interesting question, right? Here V is equal to this and W is equal to this, right? And in V, entries are coming from complex numbers. Okay, so we have to check that under usual matrix addition and scalar multiplication, determine which of the statements are true, right? So we have to check V is a vector space over C or not, right? V is a vector space over R or not, right? And then we have to check that whether the W is a vector space over C or not, and W is a vector space over R or not, right? So students, see, here they are saying to check vector space, not subspace, right? But students, see, what is V? We know that suppose this is your matrix, right, Mn cross C, right? We have done for Mn cross R, right? Matrices of matrices of order n cross n entries from R, right? And what does it mean? It means that matrices of order n cross n and entries from the field complex number, right? So this is my vector space, this was my vector space, right? We have proved it. Okay, and here it is given V, a subset, right? So this V is a subset of this vector space, right? Now they are asking that check whether this forms a vector space or not, right? So what will you do? Do you check all the conditions of vector space, or you check only the 3 conditions of subspace, right? So yes, you have to check only 3 conditions. Why? Yeah, you can check all of this, but this is time taking, right? So be smart, check all the 3 properties. Why? See, this is a subset of a vector space, right? So we can use the properties of subspaces to test that whether this set forms a subset or whether this set forms a vector space or not, right? So if it forms a subspace, so it will definitely be a vector space, right? Why? Because what is subspace? Subspace is basically a vector space itself. Okay, so here we will use only subspace condition. Okay, so see, according to what is V? V is equal to, okay, let me check it, right? Let us check the condition number 1. Okay, we know that 0 vector 0 0 0 0, you can see that it is satisfying this condition. A11 plus A22 means this one plus this one. See, this is equal to 0, right? What does it mean? It means that this 0 vector belongs to V, right? So number 1 condition has been satisfied. Now check the closure under addition. So choose any 2 elements from this set. So I am choosing 2 matrices, right? This one and plus this one, right? b11, b12, b21, b22. Okay, which will be equal to, suppose this is your a and this is your b. Okay, then check whether this a plus b belongs to or not. Okay, so a11 plus a12 plus, sorry, this is not plus 2 1 1. What it will be? It will be a11 plus b11, here a12 plus b12, right, and here a21 plus b21 and a22 plus b22, right. Now we have to check whether that this matrix belongs to the set V or not. For that, what we have to check? We have to check this condition. So check it, add them. A11 plus b11 plus plus a22 plus b22, right. What it will be? It will be equal to, we can write like that, a11 plus a22, right, rearrange it, plus b11 plus b22, right. And we know, since this belongs to V and this belongs to V, what does it imply? It implies that their addition will be 0, right. So from this is equation 1, this is equation 2. What it will be? It will be equal to 0 plus 0 equal to 0. So students, see, their addition is equal to 0, right. What does it mean? It means that it is closed under addition, right. And similarly you can show it for scalar multiplication also. How? See, if you choose any element C from set of complex number, right, now multiply it, it will be a11, a12, a21, a22, right. So it will be ca1, c, right. If you multiply, then you will get this one. Now add them, check whether their addition is equal to 0 or not. So if you add them, you will get this one, which will be equal to c into a11 plus a22. Okay, and students, since this is a member of V, so their addition will be 0. So c, it will be equal to c into 0 equal to 0. So yes, V forms a subspace, right. So I am writing here, wait, see, so V forms a subspace, right, over C. Okay, so since subspace is a vector space, so we can say that yes, V is a vector space over C. So option A is correct, right, option A is correct. Now what about C? See, what is R? R is a subset of complex number, right. So if a set forms a vector space over the whole set C, right, so definitely it will form vector space of its subset, right. So definitely this V is a vector space over R also. Okay, so A and C are my correct, right. Now we have to check A and C are my correct, right. Now we have to check for W. What is W? See, so W is defined as W equal to A belongs to be A12, A21 bar. Okay, A belongs to be such that A12 plus A21 bar is equal to 0, right. Now we have to check that whether this W forms a vector space, means forms a subspace under the field C or not, right. So see, at first we will check the 0 matrix, right. So see, if you take 0 0 0 0, right, so see, this one plus this one bar, okay, again this is equal to 0. So yes, 0 matrix belongs to W, right. Now check the closure under addition. Okay, see, I am writing it for you. Okay, closure under addition. Okay, see, if we choose to a matrix, let A equal to A11, A12, A21, A22, right, belongs to W, right. And similarly B equal to B11, B12, B21 and B22 belongs to W, right. What does it imply? It implies that if A is from W, then it will satisfy this condition. What does it mean? It means that A12 plus A21 bar is equal to 0. Similarly, B11 plus B12 bar will be equal to 0. Right, let it equation 1 and it is equation 2. Okay, now add it. If you add, then what will you get? You will get this one, A11, A12, A21, A22, right, plus B11, B12, B21, B22. Okay, now add them. What will you get? You will get A11 plus B11, A12 plus B12, A21 plus B21, B21 plus B22. Right? Now check whether this matrix satisfies these conditions or not. Right? So see, A11 plus B11, right, plus A12 plus B12 whole bar, right, it is equal to A11 plus B11, right, plus what it will be? It will be this one, right, because from the complex analysis we know that if, see, just remember this result, okay, since we know that A plus B bar is equal to A bar plus B bar. Okay, this condition holds, right, from complex analysis, right. This is a result from complex analysis and we are using it here. Okay, so see next. It will be equal to A11, rearrange it, it will be equal to plus A12 bar plus B11 plus B12 bar. And students, see, from 1 and 2, this is 0, this is 0, right. What does it mean? That this matrix satisfies this condition. It implies that this belongs to W, right, and this is equal to this one, this one, this one, right. What does it means? That A plus B belongs to W. Okay, it means this is closed under addition 2. Okay, now let us check the remaining condition, scalar multiplication, right. See, check. Okay, wait, right, from here, scalar multiplication, right, closure under scalar multiplication. So see, at first choose any element, let lambda belongs to C. Why? Because C is the field, right. And now let us choose an element A equal to A11, A12, A21 and A22, right. It belongs to the set W, right. Since it belongs to W, so it will satisfy this condition that A11 plus A12 are equal to 0. Let it equation 1, sorry, 1, 2, okay. So suppose this is equation 3, okay. Now check the scalar multiplication. See, lambda into A, and it will be equal to lambda into A11, A12, A21, A22, okay, and this will be equal to lambda A11, lambda A12, lambda A21 and lambda A22, okay. Now check whether this matrix belongs to this W or not, right. For that we have to check the condition, that whether it satisfies this condition or not. So check the condition. If we check the condition, then it will be lambda 11 plus lambda A12 whole bar, okay. This will be equal to lambda A11 plus lambda bar A12, right. So students, see what we get this expression, right. And see students, we know that this will never be equal to 0, right. This is never equal to 0. Why? See, here is lambda and here is lambda bar, right. What does it mean? It means if you have a complex number A plus IB, right, lambda equal to, then lambda bar will be equal to A minus IB, right. And students, you can see that this will never be equal to 0. It will be 0 only at a condition. What condition? That if lambda will be equal to lambda bar, right? If lambda will be equal to lambda bar, then you can see that then you can take lambda common, right? A11 plus A12 bar, right? And in this case from equation 3 you can say that this one is 0, that's why this will be 0, right? So in that case you can say that yes, if lambda will be equal to lambda bar, wait, see, if lambda will be equal to lambda bar, only then it will satisfy scalar multiplication condition, right? And only for this case, right, only for this case this satisfies scalar multiplication condition, and only for this case it will form a subspace, right? So for the complex number it will not form a subspace. What does it mean? That W does not form a subspace over the field complex number, but W will form a subspace over the field of real number, right? So this is the conclusion. See, here is no other way, right, to show that this is equal to 0, right? But if this and this is equal to 0, then we will take common and this will be equal to 0, right? So what will be the answer of this question? So students, see, W is a vector space over C. This is wrong. Vector space, or you can say that subspace, no issue, okay? This is wrong. And W is a vector space or subspace over R. Yes, this is true, right? And this is also true. So A, C and D are my true answer and B is my wrong answer, okay? So I hope you understand each and everything, right? So next, if you have any doubt, then ask your doubt in comment section, right? So next, see what it is saying. It is saying that let M be the vector space of all 3 cross 3 real matrices, right? And my A is defined like that. And what they are asking, that which of the following subsets are subspaces of M, right? So we have to check for all of them, right? So students, you can see that you can check it by my shortcut trick. What? LHS is linear, right? And RHS is 0, right? You can check by it, okay? You can see that yes, this will form a subspace, this will also form a subspace. Why? Because see, this is basically the condition, right? And we know that matrix addition is commutative, right? And you can see that this is my trace. What does it mean by trace? See, suppose if you have a matrix A, B, C, D, E, F, G, H, I, right? So if you add, then what will you get? You will get this one, A plus E plus I, right? And see, this is equal to 0. It is my condition that trace is equal to 0, right? So see, this is my linear equation, RHS is 0. So yes, it will form a subspace. But what about determinant? Earlier we have seen that determinant is not a linear equation, right? So that's why since this is not linear, that's why it will not form a subspace, right? So you can check it by my shortcut trick, right? Otherwise I am going to prove it also, right? So don't worry, I will prove it. So students, see, so this is the approach to get the answer in your competitive level examination like NET, GAT, JAM, okay? So I am going to give the proof for the semester level examination, right? And for your basic understanding also. So see, so what is A? A is my this one, right? So see, let W is equal to capital X belongs to M such that XA equal to AX, right? Now we have to check whether this satisfies the subspaces conditions or not, right? So let's check it. What about geovector? So if we choose X equal to 0, right, then what happen? If we choose X equal to 0, then it will be, we have to check that whether this satisfies or not, right? So 0 into A equal to 0, right? And check it, A into 0 is equal to 0. So see, this is equal to this one, right? So this condition satisfied. Therefore X equal to 0 belongs to W, right? So the first condition has been satisfied. Right, now check the second condition. What was the second condition? Closure under addition. Closure under addition. Right, see, let x and y belongs to w. Right, since x and y belongs to w, so what it will imply? So it will imply this condition that xa will be equal to ax and ya will be equal to ay. Right, give it a name, that equation 1 and equation 2. Now see, what we have to check? We have to check that whether x plus y belongs to or not. Right, so check. So now the question arises that when does it belongs to this set? So this x plus y will belongs to this set only when this satisfy this condition. Right, so check whether that this satisfies these conditions or not. So if we check, then x plus y of a, right, what it will be equal to? So it will be equal to, see, if we break, then what will we get? We will get xa plus ya. Right, and we know that xa equal to ax from 1. Right, xa equal to ax and ya equal to ay. Right, now take common. If we take a common, then it will be equal to x plus y. So students, see what we get. We get that this into a is equal to a into this, right, which is this condition. Right, so what does it mean? It implies that x plus y belongs to w. Right, it means that w is closed under addition 2. Okay, now what is the remaining condition? The remaining condition is scalar multiplication. So let's check it. Let my lambda belongs to f. See, what is f? F is my real matrices. Right, means entries are coming from real number. So my field is R. Right, so let lambda belongs to R. Right, choose and let x belongs to w. What does it imply? It implies that xa is equal to ax. Right, this is my 1. Let it be 3. Right, now we have to check that whether lambda into x belongs to this set or not. Right, for that what we have to check? We have to check that whether that lambda x satisfying this condition or not. So see, lambda x into a, it will be equal to, what it will be equal to? See students, since we know that the matrices satisfy the associativity condition, right, so by using that, what will we get here? We will get here that lambda into xa. Right, and we know that from 3 what we get? Xa equal to ax, so it will be lambda into ax. Right, from 3. If we rearrange it, then what will we get? If we rearrange, then it will be a into lambda x. Right, so students, see what we get. We assume this one, this into a is equal to a into this. Right, and it is the condition of the set. Hence we can say that yes, lambda x belongs to the w. So students, see, w is closed under addition, w is closed under scalar multiplication, and zero vector also belongs to it. Right, so by the standard subspace test, we can conclude that yes, this w is a subspace. Right, so see, this is a subspace. Right, now what about this? So see, you can see that basically this is the commutative of matrices. Right, and we know that commutativity of addition in matrices holds. Right, so let's prove it. Okay, so check B. Right, see, again let w equal to, wait, what is the set? X belongs to M such that x plus a is equal to a plus x. Right, so check whether the zero vector belongs to it or not. So if we choose x equal to 0, right, then what will happen? Right, so check at LHS first, put x equal to 0 plus a equal to a. Right, and put 0 at RHS, what will you get? A plus 0 is again a. right? So see, LHS equal to RHS, right? So this condition holds. Since this condition holds, it implies that 0 belongs to the set W, right? Now we have to check closure under addition. So let us choose two elements from the set W. So let X and Y belongs to W, right? So what does it mean? It will satisfy this condition. So since X belongs to W, so it will imply that X plus A will be A plus X, right? And similarly, since Y belongs to W, so it will satisfy that Y plus A is equal to A plus Y. See, we are just using the condition of the set, right? Now we have to check that whether X plus Y belongs to or not, right? So check X plus Y will be equal to, see, when it will belongs to the set A, right? When X plus Y, right, wait, when this will belongs to this, it will belongs to it when it will satisfy this condition, X plus A, it will be equal to A plus this, right? Instead of X, we are writing X plus Y, right, to check the condition. Okay, see, so it will satisfy this condition when X plus Y plus A will be equal to A plus X plus Y, right? So see, now if you add, then what will you get? You will get, instead of this, see, here is X plus Y, right? So we know that commutativity holds in matrices, right? And it is associative also, right? So you can write it directly, okay? It will satisfy definitely. If you add X plus Y then A, or if you add A plus X plus Y, the result will be same. This is the standard result of matrices, right? So see, we finally get the result that this plus A is equal to A plus this, right? What does it imply? It implies that X plus Y belongs to W, implies closed under addition 2, right? So we have proved two conditions, right? Now what is the remaining condition? So check scalar multiplication. So let C belongs to R, which is my field, right? Now take any element X belongs to W, right? Then what it will imply? Then it will imply that X plus A will be A plus X, right? Now we have to check that whether Cx belongs to this set or not. For that, what we have to check? This plus A. Do it, right? And students, see, since commutativity holds, so definitely it will satisfy this condition. So see, Cx plus A equal to A plus Cx, right? What does it mean? Cx belongs to this set W, right? So this W is closed under addition, closed under scalar multiplication, and zero vector belongs to it. What does it mean? It means that W is a subspace of this one, right? So yes, this is a subspace. Okay, now what about this set? See, let W equal to, what is it? It is X belongs to M, right? So see, X belongs to M such that trace of AX is equal to 0, right? So now we have to check that whether this set forms a subspace or not. So let's check the three conditions, right? So see, students, let X equal to 0, choose it, right? Now check the condition that whether this X satisfies this condition or not, right? So what it will be? It will be equal to A into 0, right? And what is A into 0? A into 0 is always 0, right? What it is? It is 0 matrix, right? This is 3 cross 3, right? So this is my 0 matrix, and we know that trace of 0 matrix is equal to 0, right? So trace of 0 is equal to 0. So what we get? We get that trace of A into 0 is equal to 0, right? Which satisfies this condition. What does it mean? It means X equal to 0 belongs to the set W, right? Now we will check the second condition, that closure under addition, right? So let me change the color. Let X and Y belongs to the set W, right? So it will satisfy this condition, right? So since X belongs to W, it will imply trace of AX is equal to 0 and trace of ay is equal to 0, right? Suppose this is my equation 1, this is my equation 2. Now we have to check whether that this x plus y belongs to this set or not, right? For that it should satisfy this condition, right? So see when it will satisfy this condition, when wait, let me erase it. When it will satisfy this condition, when trace of this a into this, see here was a into x, right? So here it will be a into x plus y. Okay, I hope I am able to make you understand. Now if it is equal to 0, then it will satisfy this condition. So check. So it will be equal to trace of ax plus ay, right? I hope it is clear, right? So students, see, in matrix theory, there is a property what that if A and B are my two matrices, then trace of AB is equal to trace of A plus trace of B, right? This is my standard property of matrices, right? We will read it in the next lecture, which will be on matrices, right? We will know about it in detail there, right? But just know that this holds, okay? So by using this property, what we get? We will get trace of ax plus trace of ay, right? So students, see what is trace of ax from 1? It is 0. Trace of ay from 2, it is 0, which is equal to 0. What does it mean? That trace of a into x plus y is equal to 0, right? It means that this x plus y belongs to the set W, right? So W is closed under addition, right? Now what is the remaining condition? The remaining condition is closure under scalar multiplication, right? So let us check it. Let C belongs to R, right? Why? Because R is my field, and X belongs to W. What does it imply? It will satisfy trace of AX equal to 0, right? Now we have to check whether that this C into X belongs to this set or not. For that it has to satisfy this condition, A into this one, right? A into this one and trace of it, right? It must have to be 0, right? So it will be equal to, student, C. What can we write from here? Trace of C into AX, right? Which is equal to, and students, see, there are one more condition that we are going to use, right? In matrices theory, it also holds that if trace of lambda A is, right, that trace of lambda is equal to lambda into trace A, right? Where lambda is my scalar. This is from scalar, right? So by using that property, we will take C outside, right? Trace of A into X, right? And students, see, what is trace of AX? It is equal to 0, so it will be equal to 0, equal to 0, right? So see, this is equal to 0. What does it mean? It means that these things belongs to W, right? What does it mean? That this set is closed under scalar multiplications 2, right? So see, 0 belongs to it. It is closed under addition and scalar multiplication, right? So we can conclude that yes, this W forms a subspace, right? So now what is the next? The next is my determinant. So students, I have earlier proved it, right? So this will be your homework. Prove it by yourself, right? This will not form a subspace. Why? It will fails the condition closure under addition. Closure under addition, it will fail, right? Take an example, right? Then do it. This will be your homework. Think about it, okay? And if you have any problem related to this question or this lecture, right, or any concept, then please ask your doubts in your comment section, right? I will make you reply, right? So next, see, this was a very beautiful question, okay? So next, it is saying that which of the following are not vector spaces, right? So students, we have to check the vector spaces, right? subspace is not mentioned. So to check the vector space, what we have to check? We have to check it is closed under addition or not. Is it closed under scalar multiplication or not? Does it satisfy all the 4 properties under addition or not? And does it satisfy all the scalar multiplication or not? Right. So students, see what is the first one. So write it. W is equal to an such that an belongs to R, right, over F, where F is my R, right. Here R is my field. Now see what is it. So basically this is A1, A2, A3 and dot 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 so on, right. And students, where A1, A2 these are from real numbers, right. So students, see what is it. Basically this is nothing but Rn, right. If you choose n equal to 2, then it will be R2, right. If you choose n equal to 3, then it will be R3, means 3 tuple, right. This is 2 tuple, right. And students, we know that this will form a vector space, right. Why? Because already we have proved that set of polynomials, set of matrices, right, set of sequences, convergent sequences, set of bounded functions, this forms a vector space, okay, in the previous lecture. So similarly you can check that 0 0 0 0 will belongs to here, right. And if you choose any 2, then it will satisfy this condition and all of these, right. So students, this will be your homework, do it yourself, and this will form a vector space, okay. But according to the question, they are asking which of the following are not subspaces, right. So according to the question, this is wrong, right, because they are asking for those sets which does not form subspaces, but this forms a subspace, okay. So basically students, Rn forms a vector space, okay. What about this one? Example 2, see, this is my set, right, and we have to check whether that this forms a vector space or not, right. So students, if you look carefully, then you don't have to check all the conditions, right. See what it is. See, this is my vector space. Suppose this is my vector space, right, and this is my subset, okay. To check whether that this subset is a vector space or not, then what we need to check? We need to check only 3 conditions, right. But this W must be a subset of a vector space, right. So see here, in this case I am letting V equal to set up all those functions, right, which is defined from the closed interval 0 1 to R, right. B is the set of functions which is defined from closed interval 0 1 to R, right. And students, see this given set, right, this given set is 0 1 to R such that f of x is equal to 0 at finitely many points, right. So students, see this is my set, right, this is my set, and if you look carefully, then you can understand that this W is the subset of this V, right. Means this V is my this one and this W is my this one, right. So now they are asking to check that whether this W forms a subspace, forms a vector space or not, right. They are asking to check whether that this W forms a vector space or not, right. Since we get that yes, this W is a subset of a vector space, right. So to check whether that this forms a vector space or not, we don't need to check all the condition of vector spaces. We will check only 3 conditions, right. See students, how I am connecting the things, right. If I want, then I can directly say that yes, check the subspace conditions, but I am not doing like that, right. I am just giving you the idea, the logic, that how to think, how to connect, right. So let's check it. Students, see, does the 0 function will belong to this set? Means check the first condition that 0 belongs to or not. So suppose this is my 0 function, right, and 0 into x is always equal to 0, right, according to the function's property, right. That 0 function always gives 0, right. So we got a 0 function as 0 into x equal to 0 for all x belongs to this interval, right. So students, see, does this 0 belongs to this set W? See here, does this function 0 belongs to this set W or not? So students, you can see here it is saying that fx should be 0 for finitely many points, right? This function should be 0 at finitely many points, right? But what about this? See, here x is my from closed interval 0 to 1, right? So for all the values of x, this 0 functions gives 0, right? For all the values of x in this closed interval, this 0 functions gives 0, right? And now see how many numbers are there. So from the real analysis, we know that in a closed interval or in a open interval, it consists infinitely many points, right? So students, in a closed interval 0 1, there are infinitely many points, right? If it is my 0, if it is my 1, then in between them there are infinitely many points, right? As we know. So what we get, that x belongs to this one, right? What does it mean? That this 0 functions gives 0 for infinitely many points in this closed interval, right? But here it is given that fx equal to 0 at finitely many points, but this is equal to 0 for infinitely many points, right? That's why this 0 vector does not belongs to here, right? Means this 0 function which does not belong to this set, right? It means it will not form a subspace. What about this? So I have proved it in the previous lecture that this does not form a vector space, right? And I have given an example. I hope you remember that example. I am not going to prove it here, right? So if you are new, right, and you have not watched the vector spaces lecture, right, then please go to the previous lecture, right? I have given the timestamps there. I have written the questions also, right? Just see the questions and know the results, right? Before that, try yourself, okay? And if you have any difficulty, then comment section is only for you. Write your comments, okay? Ask your doubts, I will make you reply. Next, okay, wait. So this does not form a vector space, this does not form a vector space, right? So according to the question, this is my correct answer, this is my correct answer. Since this forms a vector space, this is my not, according to the question, okay? See students, how we are using the subspaces condition to prove the vector space, right? So before using the subspaces condition, you have to know, or you have to be sure that this W is a subset of a vector space. Otherwise you have to check all the conditions, right? See next, what it is saying. It is saying that which of the following subsets of R3 are not subspaces, right? So these are my given conditions. So students, see what is given, x1 equal to 0 or x2 equal to 0, right? So students, at first we have to construct the set, right? See what it is, W equal to which of the subset of R3, right? Since it is from R3, so it will be xyz belongs to R3, such that what is the given condition, that x1 is equal to 0 or x2 is equal to 0, right? So this is my set, right? And what is the vector space of it? So students, see, this is my R3, right, and this is my W, right? This is my vector space and this is my subset. Now you have to check this is a subspace or not, right? So check three conditions. So at first, see, we will check for 0, right? So students, if we choose x, see what kind of elements belongs to this set. So the elements, right, or the tuples in which the first position is 0, right, second position is 0, right, and the last position may be anything, right? It may be anything, right? The first and second position should be 0, right? That kind of element will belong to this set, right? So students, if we choose z equal to 0, right, we can choose, why? Because z belongs to real number, right? So see, if we choose z equal to 0, then it will be a 0, right? So see, this belongs to W. Why? Because this position and this position is 0, right? So 0 vector belongs to W, right? So the first condition has been satisfied. What about the second condition? Closure under addition, right? See students, let let me give it a name like UV, not XY, okay? Let UV belongs to W, right? So how does this UV looks like? So at the first position it should be 0, right? And the second position it should be 0, right? Students, see what it is saying, that x1 or x2 may be 0. What does it mean? That x1 or x2 equal to 0. What does it imply? It implies if x1 is equal to 0, then that element will belongs to W. If x2 is equal to 0, then it will belongs to W, right? If any one of them means x1, x2, x3, though, see, if any one of them is equal to 0, then it will belongs to W. Suppose this is of this form, right? Then this will belongs to W, right? So students, I am choosing an element 1, 2, right? So students, see, these elements belongs to W. Why? Because this x1 is equal to 0, right? Similarly, if you choose v equal to 0, 0, okay, let me write like that, 1, 0, 2. See, this will also belongs to W. Why? Because this is 0, x2 is 0, right? So this belongs to W, right? So now add them. If we add u plus b, what it will be? It will be 1, 1, 2. Students, see, this is not 0, right? And this is not 0. Neither x1 nor x2 is 0. What does it mean? It does not belongs to W, right? If any one of them will be equal to 0, right, or both will be 0, then it can be in W. But since none of them is 0, so it will not belongs to W. What does it imply? That u plus b does not belongs to W, right? It means it fails closure under addition, right? So this set is not a subspace. Students, I think I am able to make you understand. Okay, and students, see, if instead of or, if here was and, right, x1 and x2, then in that case it will form a subspace. Why? Because in that case this will be always 0, right? And in that case it will satisfy all the conditions, right? So students, see, okay, sorry, students, actually write it yz and x0z, right? So this kind of element will belongs to W, right? Recently I think I have said that these both should be 0, right? But not like that. If any one of them is 0, then it will belong, right? So I hope I am able to make you understand. So what is my answer? Which of the following are not subspaces? This is not subspace, yes. So according to the question, this is my correct answer. See, again, this will not be a subspace, right? Why? Because 0 vector will be not be there, right? So according to the condition, this is correct answer. Now what about these two? See, what it is saying, that at first construct the set W equal to, it is 3, okay? W equal to x1, x2, x3, right? It belongs to R3 such that x1 is equal to x2 and not equal to 0. What does it mean? It means that x1 and x2 means here and here is not 0. It may be 0. Okay. So if this is not 0, right? Suppose this is 1, right? And this is also non-zero. Suppose this is 1. So students, you can see that in this case 0 will never be there. Why? Because at these two positions there are always non-zero numbers according to the condition. So this will not belongs to W, right? So this is also not a subspace, right? So yes, according to the question, this is correct. Now what about this one? So write it. W equal to x1, x2, x3 belongs to R3 such that x1 plus 2x2 not equal to 1. Right, so students, see, the given condition is that this is not equal to 1, right? It may be anything. In these sets, all the elements are there in which RHS is not equal to 1, right? See, if RHS is equal to 0, yes, then it will form a subspace. Why? Because this is linear, RHS is 0, right? So it will form a subspace, right? And if it will be any other thing except 0, right? Suppose this is C not equal to 0, right? If here C will be anything other than 0, then this will not form a subspace. Why? Because 0 vector will not be there, right? So that's why if not equal to 1 here, right? So only this will not belongs to this set, right? Equal to 1, this will not belongs to this set, right? And rest of them will belong, right? 2x2 plus 2, it will belong. 2x2 equal to 3, it will belong. And any other real number, it will belong, right? So hence this is also not a subspace. Why? Because 0 does not belongs to it, right? But when it is equal to 0, only then it will form a subspace, right? So which of the following subsets of R3 are not subspaces? See, it may be a subspace or it may not be a subspace, right? It will be a subspace when RHS is 0 and not a subspace when RHS is not equal to 0, right? So yes, this is also not a subspace, right? Why are we saying like that? So see, we can show that yes, this does not form a subspace for at least one condition, right? So that's why we can conclude that though it forms a subspace for one condition, but for others it does not form. That's why this is not a subspace. Okay, so students, according to the question, this is correct answer, right? So what are my correct answer of this question according to the question? All of them, right? I hope I am able to make you understand each and everything, right? And if you are a beginner level student, if you are a semester level student, then this is only for you. Especially this is only for you, right? Because I am here to connect each and everything from basic to advanced, right? So that when you do questions for NET, GATE, JAM, right, or NBHM or ISI, then you will not feel any difficulty in that, right? Because your basics are building in a very strong way, right? So I hope you are enjoying the lecture. So next, saying let L be the vector space of bounded continuous real valued functions on this interval. Determine which of the following are subspaces of L. Right, so students, this is very easy questions and I know you become expert, so you can do it. So this will be your homework, right? We have done lot of questions like that, right? So I don't feel that I have to do this question right now. So the next, which of the following is not a vector space? So this will also be your homework. And students, I have done this solution in the previous lecture, right, on vector space. If you find any difficulty, then please go to this lecture and check the timestamps, right? Check the question number. I have written the question in the timestamps, right, or time lapse. Go there and see the solution if you find any difficulty, right? And even after that, if you have any doubt, then comment section is only for you, right? So next, what it is saying, let Rx be the vector space of all real polynomials. Determine which of the following are subspaces, right? So see, this will not form a subspace. Why? It is the set of all negative coefficient, right? If you choose any f, right, and if you multiply it with -1, right, since f is my negative, so negative will be positive, right? So it will fail the scalar multiplication condition. Do it yourself. Similarly, degree of f equal to 4, right? So if you choose, suppose this is my fx, right, and choose a gx like that, minus x to the power 4, right? If you add f plus g, it will be x to the power 4 plus minus x to the power 4, which is equal to 0. And see, this is not a degree 4 polynomial, right? So it is, so it fails closure under addition. So this will also not be a subspace, right? And students, you can see this will form a subspace, right? we have done it earlier, right? So see, linear, right side 0, yes. What about this one? So we have done this type of questions also, right? So do it yourself. This is your homework. Okay, next. What it is saying? Yeah, this will also be your homework. Next. What it is? See that this will form a subspace, right? Linear RHS 0, right? This will not form a subspace, right? Why? Because scalar multiplication will fail. When you multiply it with -1, right, the sign will be changed. So this will not form a subspace. 0 vector does not belongs to it, right? So what was the question? Which of the following sets are subspaces of this? Right, which of the sets are subspaces? So only this is my subspace, others are not, and this will also cancel. Right, so students, do it yourself. Right, I hope you will solve it theoretically, right, for semester examination, and I know you can do it because I have solved lot of examples and lot of problems, right, similar to this example. Okay, and if you find any difficulty, then as you know, this section is only for you. Okay, next. What it is saying? Similarly, see students, this will form, this will not form, right? What it is? If you rearrange, then you will get f of x minus f of minus x equal to 0. Yeah, linear 0. Yes, it will form, right? So what they are asking, which of the following set are subspaces, right? So this is subspace and this is subspace and this is not, and this option is also cancelled. Okay, so again do it yourself as homework, right? Prove it theoretically. Prove it theoretically, right? If you prove them theoretically, right, if you solve this slide, okay, and if you make a proper note of my slides, right, then you will see that you are becoming an expert, and you can solve any book, right? You can solve MSc Mapa, you can solve Friedberg, right, you can solve Dr. A.P. Singh and many other books, right? So next, and students, you can see that what is this? This is basically my odd function, sorry, even function, right? So see what it is saying, that which of the following sets is not a subspace of this one, right? So this will be your homework, right? You can check, right? This is very easy questions, right? So what is this? Degree equal to 4, greater than equal to 3, this one, right? So check all of them. This will be also your homework, right? Next, what is this? Which of the following is not a vector subspace of the vector space of real polynomials, right? So see students, this will form a vector space, yes, this will form a subspace, right? And students, you can see that this will also form a subspace. Why? If you rearrange, then what will you get? Minus p of 1 minus a equal to 0. This is linear 0, right? Okay, and what about it? The set of all polynomials having integral coefficient. So as we have seen this result in the previous question, right? There was a question, right, in which we have proved that this is not a subspace, right? You can see that basically a scalar multiplication will fail, right? Why? Because if you choose an element from field which is my rational number, right, and then you multiply it with the integer, right, then it is not necessary that the result will be from the integer, right? That maybe belongs to rational number also. So this will be also your homework, right? And what about this one? The set of all polynomials divisible by x, right? This is a very interesting question, so do it yourself, right? I am not going to give the hand-to-hand solutions to you, right? So basically this is your homework, and if you find any difficulty, comment box is only for you, right? Write the comments, I will make you reply. So this is also your homework, and whatever questions I am giving you as homework, solve them theoretically, right? Next, see, we have done it, yes, it is done. What is the next? Set of all symmetric matrices, yeah, this is also done. Okay, What is this? Yeah, this is also done, right? You have to check. Yeah, what about next? This is your homework. Okay, these are your homeworks. Practice all the questions. What about this? So students, you can see this will not form. This is linear plus 0. And what about this? So students, see, this will form a subspace, right? You can see this is a linear 0, and if you rearrange it, c minus d equal to 0, right? Linear and 0. So this will form a subspace. And students, this is your homework, right? And you can see that it will satisfy all the conditions. Why? How does this tuple will looks like? So see, a is my, what is a may be anything, okay? A, b is my 0, c and d are my same, right? So suppose this is c, this is c, right? So students, you can check that these types of elements satisfies all the conditions of subspaces. 0 will be there, yes, if you choose a and c 0. If you add them, right, so you can see that it will satisfy all the conditions. So this is your homework. Next, what it is saying, which of the following subsets of R3 are subspaces? So students, see, this is my trivial subspace, right? 0 0 0, okay, and you can see that this is linear and this is linear, so this will form a subspace, right? This will also form a subspace. Now what about this one? So students, see, it is saying that W is equal to ABC such that ABC belongs to Q, right? And what is the field? Field is my real number, right? Field equal to R, right? And students, see, yeah, 0 will be there, no doubt. If you add two elements, right, means if you add two rational number, then again it will be rational number, so yes, addition will also satisfy. Now what about scalar multiplication? If you choose C from the field, right, and an element, suppose you are choosing ABC, okay, ABC from W, right? Now if you multiply, then what will you get, right? See, you will get CA, CB, okay, let me, this is lambda, right, because C is already there, so it will be equal to lambda A, lambda B and lambda C, right? And student, see, what is lambda? My lambda is from the field, means lambda belongs to real number, right? And we know that set of irrational number is a subset of R, right? So if we choose lambda equal to root 2, which is my irrational number, right? If we choose lambda equal to root 2 irrational number, right, which belongs from R, okay, so then what will we get? If we choose lambda equal to root 2, then we will get root 2a, okay, root 2b, root 2c, right? So students, see, if this is a rational number, means if ABC is my rational number, right, let us choose a equal to b equal to c equal to 1, right? Then what it will be? It will be root 2 root 2 root 2, right? And students, see, here root 2 is my irrational number, right, and all of them are from irrational numbers, right? So this will not belong to the set W. Why? Because it is saying that ABC should be from rational number, but we get that these elements are not from rational number, right? So this will not satisfy the closure under scalar multiplication. That's why this is not a subspace. And students, this will be your homework. I have proved it, okay, but if you want, then you can try yourself, no issue. And this is your homework, do it yourself. And if you find any difficulty in it, then don't worry, I have given you the proof here, right? At first try yourself, right, then come here, then match, then learn. And still, if you have any doubt, then comment your doubts, I am here for you, right? So next, see what it is saying. It is saying that if a vector space V is the set of all real valued continuous functions over the field of real numbers R, right, then show that the set W of solution of the differential equation this is a subspace of V, right? So students, this is a question, right, this is a subspace question related with the differential equation. Okay, so don't worry, this is very easy question, right? Don't be panic after looking at the question, right? Always try to go with the basic. Okay, see what it is saying, that W is the solution of the differential equation this. What does it mean? W is equal to this, right? Solution, right? So suppose y equal to fx. Okay, suppose this is your solution, right? Such that this y satisfies this condition, right? Minus 9 dy upon dx plus 2y equal to 0, right? Y is that functions which satisfies these conditions. I hope I am able to make you understand why we are writing y equal to x, because here these are continuous functions over the field of real number, right? Set of all continuous functions. Basically these are functions, means the solution of this, see, the solution of it are functions, right? Y, okay, and where y is of the form, okay, so that's why see W is the set of all y which satisfies this condition, right? So see, at first we will check that whether the zero set belongs to it or not. So let's check it. See, let me change the color. See, if we choose y equal to 0, right? So students, when this 0 will belongs to this set, when it satisfies this condition. So check whether that this satisfies these conditions or not. So students, I am just changing the notation, right? See, this is 2, we can write it like that. This you will learn in your differential equation series. Okay, I will teach it. This one plus 2y is equal to 0, right? So basically see, if y is equal to fx, right, then dy upon dx is equal to this one, right? And this is denoted by y dash. If you take 2 time derivatives, it will be double. If you take 3 time derivative, then it will be 3 times. Okay, so see this one, if you put y equal to 0, then what will you get? 2 into, take the derivative, it will be 0, take the second derivative, it will be again 0, right? So 2 into double derivative 0 minus 9 into single derivative again 0 plus 2 into y 0. So yes, this is equal to 0. See, y equal to 0 satisfies this condition. What does it mean? That this 0 function belongs to the set W, right? So yes, first condition has been satisfied. Students, see, here 0 is a function, this is 0 function. Okay, why? Because the set W is the collection of all solution of this, and the solution of these are basically functions, right? I hope I am able to make you clear everything, right? So next, now closure under addition, right? See, closure under addition, right? So let y1 and y2 belongs to W, right? So see, y1 and y2 are belongs to W. What does it mean? It means that yn and y2 are solution of this differential equation. So since this is solution, so this will satisfy this condition, right? So see, I am writing here, since y1 belongs to W, so it implies y1 will satisfy this condition, that 2 y1 2 time derivative minus 9 y1 single derivative plus 2y equal to 0. Similarly, y2 will also satisfy this condition, minus 9 y2 single derivative plus 2y equal to 0. Let it equation 1 and let it be equation 2. Okay, now let's change the color. Right, now we have to check that whether this y1 plus y2 belongs to this set or not, right? Belongs to this set or not, right? So when does this y1 plus y2 will belongs to this set? It will belongs only when this satisfies this condition, right? So check whether that this will satisfy this condition or not. So see, if we put y1 into y1 plus y2, right, what will we get? This is double derivative minus 9, right? Then y plus y2, okay, this is single derivative plus 2 into y1 plus y2, right? Check if this is equal to 0, then definitely this y1 plus y2 will be in w, okay? So see, it implies this is equal to 2y1 plus 2y2 double derivative minus 9y1 plus 9y2 single derivative plus 2y1 plus y2, right? And this will be equal to, and by the property of derivative we can separate like that, this one plus 2y2 this one minus 9y1 this one plus 9y2 this one plus 2y1 plus 2y2. Students, see, basically we know that in derivative this is allowed, right? Is equal to a dash plus b dash. We are using the condition of derivative here, right? Basically this is a property. I hope you know it, right? So see, it will be equal to, now rearrange it. What will you get? 2y1, right? Take another one, minus 9y1 dash this one, right? Now what is the remaining? This one plus 2y1. Now plus what is the remaining? Yeah, this one 2y2 double dash, right? Plus, sorry, this is not plus, this will be minus, okay? Why? Plus minus minus, okay? So this is minus 9y2 dash plus 2y2, right? So students, see, from 1 we can get this is equal to 0, so 0 plus 0 equal to 0. From 1 and 2 we get this one, okay? So see, this is equal to 0, right? What does it mean? It means that y1 plus y2 is also a solution of this differential equation, right? And students, what does it mean? It means that y1 plus y2 belongs to w, right? It implies that this is closed under addition 2, right? Now we will check for scalar multiplication, right? So see, I am checking here, okay? Let me change the color. Let lambda belongs to the field, and field is my real number, and y belongs to w. So y will satisfy this condition, y 2y double dash minus 9y plus 2y, right? Wait, system is lacking. What was here? Minus 9y dash plus 2y equal to 0, right? So let us check the scalar multiplication, that whether lambda y belongs to or not. For that, what we have to check, that this lambda y satisfies this condition or not. So see, it will be 2 into lambda y double dash minus 9 into lambda y dash plus 2y equal to 0, right? Sorry, this is my lambda y, okay? This is my lambda y equal to 0, right? Now we know we can take this lambda outside, right? See, 2 lambda y double dash minus 9 lambda y dash plus 2 lambda y equal to 0, right? Now if we take lambda common, then what will we get? Then we will get 2y double dash minus 9y dash plus 2y, right? See, plus 2y, right? See students, sorry, this is not equal to 0, don't write it. Actually we are going to prove it, right? So it will be lambda into, see, this is equal to 0 from this condition, right? So this into 0, which is equal to 0. So students, see, lambda y also belongs to w, right? So see, since this w satisfies all the conditions, so this w is a subspace, right? And this is the way to prove it. I hope you understand each and everything, and if you have still any doubt, then write your doubt in comment, okay? And if you have any further question, or any other question, then or any suggestion, then please comment, right? So next it is saying is R2 is a subspace of R3, right? So students, I advise you that pause the video, right, and think 2 minutes, right? So pause it, okay? So I hope you paused the video and you thought for 2 minutes, okay? Means at least 2 minutes, and I hope that you found the answer, right? And if you did not find the answer, then don't worry, I am going to teach you, right? What it is saying that R2 is a subspace of R3, right? So basically they are trying to say that, see, what was the first condition of subspace? That there will be a vector space, right, V over F, okay, and then there will be a subset of that vector space, right? So what was the first condition? That this subset should be the this set should be the subset of this vector space, right? So students, see, if this is my R3, right, then check whether that this R2 is a subset of R3 or not, right? If R2 is a subset of this R3, this is a vector space, we know, right? If this R2 is a subset of R3, right, then further we proceed, right? If not, then we will stop here, right? So see, how does this R2 looks like? R2 looks like AB, right, where A and B are from AB from real number. And how does this R3 looks like? Okay, it looks like AB and C such that ABC belongs to R, right? So students, see, this is the set of all 2 tuples, right, and this is the set of 3 tuples, right? And you can say that yes, this R2 is not a subset of R3, right? That's why it will not form a subspace, right? Why? Because it fails the subspace property, subset property, right? Now the question maybe arises that suppose this is your R3 XYZ, right, and if you choose X, Y and 0, right, so the question maybe arises, even the many student thinks that this is from R2, but no, this is not from R2. This is considered isomorphic to R2, right, but this is not the subset of R2, okay? This can be considered as isomorphic to R2, but this is not a subset of R2, remember it, okay? That's why this R2 is not a subset of it, right? Why? Because here are 3 tuples, here are 2 tuples, right? So remember it. This is a very nice question, okay? So next, what it is saying, let V equal to this one be the vector space of all real valued continuous functions on this, determine whether the set this is a subspace or not, right? So students, this is a very beautiful question. Why? Because many students will see that yes, this is my log, this is my sine, so yes, these are my non-linear function, right? Since these are non-linear, so this will not be a vector space or subspace, right? They will think like that, but this is not correct. Why? See, what is the element here? Here it is F, right? F belongs to V, right? And students, see here, F is my linear, right? So conditions are always checked on these things, okay, right? So students, check it, it will form a subspace, right? Check all the 3 conditions and you will get the result. This is your homework, right? So be smart and okay, so be smart, okay, and be happy. And if you have any problem related to the subject, then comment section is only for you. Write your comment, ask your doubts, okay, I will make it clear, right? So try it, and if you find any difficulty, then here I have written the solution for you, right? Go through it, okay? And still if you have any doubt, right, related to the subject or related to other topics, then please comment, okay? So see, now Now we will move to our next topic. Okay. So finally, we are ready to begin the direct sum of subspaces. So let's see that what it is. Okay. See, students, till now we know the definition of vector space. We know the definition of subspace, and we know that what is sum of subspaces. Right, what was that? That if W1 and W2 are my two subspaces, right, then their sum will be defined as W1 comma W2 such that W1 is from capital W1 and W2 is from capital W2, right? So this was my sum of subspace, right? Now the question arises that what is the direct sum, right? Now the question arises that what is direct sum, right, and why it is needed. So students, see, direct sum is nothing, right? It is nothing but this is just a special case of sum of subspaces, right? So see, direct sum is nothing but just a special case of sum of subspaces. So now we will discuss that why it is special. So I would like to proceed by an example so that you can understand very easily. See, students, we know that this is our vector space, right, and this is my W1 and this is my W2 subspace, right? After that we are adding it. Okay, so students, see, I am going to give you an example. Okay, see, if we choose W1 is equal to R2, okay, and W2 is equal to R2. So students, see, W1 and W2 both are my subspaces. Now students, let us choose an element, right? Suppose I am choosing an element 1 comma 1 and you know that it will be from R2. Till now I think everything is clear. Okay, so see, students, this is an element, right? And see, if we want to write it, if we want to write it, let me check it. If you want to write this element, write it in the sum of two subspaces, then how can we write? See, if you want to write it in the form of W1 plus W2, right, where W1 is this term and W2 is this term, then how can we write it? See, one way is that you can write it 1 comma 1 in the form 1 comma 0 plus 0 comma 1. See, this belongs to my this one and this belongs to my this one, and this is basically R2 and R2. Clear? Okay. Now next, see, again I can write this element in the form 2 plus minus 1 and minus 2, right? Again we can write this element 3 plus minus 2 and so on. So students, see, there is an element, right, and we can write it in a infinitely many ways, right? There is an element of R2, right, and we can write it in the sum of two subspaces in many ways, right? So this is my sum of subspace, right? So what is the quality of sum of subspace? That you can write any element as the addition of two subspaces, right? And you can express this element in many ways, right? There is not unique way. Just mention it. Not unique way, right? And student, this is my sum of subspace, right? So I think that you get an idea that what we are going to do. Students, see, now the question arises that what is direct sum, right? So what is direct sum? Okay. So see, this is a special kind of sum, okay, in which the representation of any elements are unique, right? See, this is a, wait, let me change the color. This is a special kind of sum of subspaces in which the elements can be represented uniquely, right? So this is for your understanding, right, that why the direct sum concept had been introduced. Okay, so see, so I am going to give you an example, right? After that we will move to the definition. See, let us choose a subspace W1 equal to x comma 0 such that x belongs to R, right? Similarly, let W2 be another subset, okay, such that y belongs to R. And student, you can see that this is the subspace of R2, right? And this is the subspace of R2. So basically what it is, this is my R2, a vector space, right? And this is my W1 and this is my W2, right? So students, see, now add them, okay? Wait, suppose now write 1 comma 1. This belongs to R2, yes. So how can you represent it? If you want to add W1 plus W2, right, then how can you represent? You have to choose x equal to 1 comma 0, right? See, this belongs to this set, right? Similarly, add them, you will get 0, y equal to 1, right? And what it is equal to 1 comma 1. So students, you can see that this 1 comma 1 can be represented like this, right? Where W1 and W2 are my subspaces, okay? And I am giving you guarantee, right, that this is unique. There is no other representation in this subspace, okay, to represent it, right? And I give you challenge. If you find anyone or if you find any other, then please comment, okay? But I assure you that you will not find. Why? Because it is unique, right? So this is the motive behind the direct sum, right? To represent the elements uniquely, right? Now students, here are some observations, right? Instead of taking a particular example, let us move to the generalization form, right? See, let me choose the color, this one, okay? Color of peace. See, what is my x0? No, okay, if we add them, W1 plus W2, what will we get? We will get that it will be x comma 0 plus 0 comma y, right? Such that x comma y belongs to R. Now add them, right? What will you get? xy such that xy belongs to R, right? So students, see what it is. It is basically R2, okay? So what we get, that W1 plus W2 was the W1 and W2 was the subspace of R2, right? And when we are adding this W1 and W2, we are getting R2. See, means when we are adding two subspace, we are getting the whole vector space, right? Add two subspace equal to whole vector space, right? So this is my observation. This is my observation number 1, right? Now students, do you find any common element between them? So yes, since it is a subspace, so 0 will be there. Since this is a subspace, so 0 will be there, right? So see, 0 and 0, okay, so in their intersection there will be a common element, and that is identity element, okay, identity under addition. So if we take intersection, then you will get 0, 0, right? So see, what is direct sum and what is the definition of it? So you are ready to read the definition, okay, to understand the definition, to connect the definition, okay. So see, what is the definition? Definition is nothing. See, just remember this thing, that when you add these two subspaces, you will get the whole vector space. When you intersect them, you will get only one element as common. See, only one element should be in common, right? So see, this is the definition. What it is saying, that a vector space V, right, a vector space V, this is my V, it's called the direct sum of W1 and W2, right? Suppose this is my W1 and the rest are my, this is my W1, right, and this is my W2. This is my W2, this is my W1 and this is my W2, right? If W1 and W2 are subspaces of V, yes, this is my V over F, okay, such that W1 intersection W2, what does it mean? That in it only identity element will be in common, right? So W1 intersection W2, there will be only one element in common, right? No other element should be in their intersection, right? Only one element should be in common, and it should have identity element, right? So write it, one element, one element will be common, sorry, one element will be common, okay, it should equal to 0 element, right? And the third one is, it should unique, right? So see, such that W1 intersection W2 should be equal to 0, and the second one is W1 plus W2 equal to V, right? So this one, only one element in common, right? And when you take the sum of it, you will get the whole vector space, right? So this is just for your understanding, right? So that you can remember it for a long time, okay? Just remember it so that you will be able to understand, and you don't have to remember the statement, right? Because if you remember it, right, then one day you will forget after few days. But if you remember like this, as I have told you, then you will remember for a long time, okay? And see, we denote that V is the direct sum of W1 and W2 by writing this. So see, what was the direct sum? See, what was the normal sum of subspaces? It was V equal to W1 plus W2, right? And for the direct sum, there is a special notation, a circle over addition, okay? This is the notation of direct sum. Whenever it is written, so whenever in the question you will find that this representation is written, then just understand that W1 and W2, their sum is equal to V, and in their intersection there is only one element, right? So now I hope I am able to make you clear this concept, right? And still, if you have any doubt, any questions regarding to the subjects or anything, then comment section is only for you. Ask your questions, ask your doubts there, right? I will make you reply. So next let's move to the questions. What it is? It is saying that so that Fn is the direct sum of the subspaces, this one W1 and W2, where W1 is defined as this one, right? And what is the condition? That An should be equal to 0, means this last one should be 0, right? And what about these things? So it can be anything, right? It can be 0 or can't be 0, okay, no restriction. Similarly, W2 is defined as this, and you can see that till An minus 1 it is equal to 0, means till here all of the entries are my 0, right? And what about last one? So there is no restriction, this is my free. Okay, so what we have to prove? We have to prove that Fn equal to this one, right? So we have to prove that this is the direct sum. So for that, what we have to prove? For that we have to prove that W1 plus W2 is equal to Fn, and the second condition we have to prove, if we take intersection then there will be only one element, 0, right? So students, see, so at first we will let an element from the Fn, let x belongs to Fn be arbitrary, right? Why we are taking arbitrary? What does it mean by arbitrary? So students, arbitrary means you are taking an element from Fn, right? And if you are taking an element which is arbitrary, it means that this x represents all the elements of Fn, right? Means this x is the leader of all elements of Fn, right? If x satisfies anything, then then all the elements of Fn will also satisfy that thing, right? So this is the meaning of arbitrary. Okay, you can think like that. So we have to show that their representation is unique. So see, x, see, let x belongs to Fn. What does it mean? It implies x will be of the form this one. Why? Because this is Fn, okay, n tuple. So a1 a2 dot 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 an, right? Where a1 a2 dot 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 an are from field. You can relate it like this is Rn and this is R, just because of your understanding. You can think like that, okay, so that you can connect each and everything. Now let's check it. If we write x equal to, okay, so see what it is. If you want to write as the sum of W1 and W2, so see what is the element of W1? So only the last one should be 0, right? And what about this thing? No condition. So write it a1 a2 dot 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 an minus 1 and an is 0, right? Plus what about this? So except an, all of them are 0. So write it 0 0 0 dot 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 dot, and the last one is my an. Okay, so students, see, if we add, then we will get a1 to an, a1 plus 0 a1, a2 plus 0 a2, right? And similarly you can see that we will get this one, which is my x. So yes, see what is it? This is from W1 and this is from my W2. So students, see, finally we can express this x as sum of two subspaces, right? And since this is arbitrary, so this will hold for each element of Fn, right? So therefore W1 plus W2 equal to Fn satisfies. Okay, now check the second condition. What was the second condition? The second condition was intersection, right? See whether is it true or not. So students, see, just relate it with the previous example, right, which I had explained. See what I have said, that in the case of R2, right, if we write x comma 0 and y comma 0, right? So what was the common element of that? This was 0 0. If we choose x equal to 0, y equal, sorry, y was here. If we choose x equal to 0 and y equal to 0, right, then we get 0 0, right? And if you choose any other thing in the place of x and y, right, if you choose any other thing, no issue, right? except 0 no one will be in intersection, right? So you can try if you want. Now see what it is. How does the elements of W1 looks like? Last element is my 0, right? And how does the element of this one looks like? Last element may or may not 0, rest at 0, right? So students, see, these are my free variables, so I can choose anything, so I am choosing 0. And here I can choose it anything, so I am choosing it 0. So see, this is 0, this is 0, and their intersection will be also 0, right? So students, see, in intersection there is only one element, right? So since it satisfies all the conditions, so yes, Fn is equal to W1 plus W2, and this is the way to prove it. And students, if you find any difficulty in this subject, in this topic or any topic, right, so comment section is only for you. Write your comment, ask your doubt, I will make you reply, right? And if you need any guidance related to this subject, then feel free to call. Okay, next, what it is saying, let W1 denote the set of all polynomials fx in Pf such that in the representation this one, right, this is the representation of a polynomial of degree n. Okay, and what is g? This is my g, right? And what we have to prove, such that a1 equal to 0 means all the coefficients are 0 whenever I is even. O means for the case a0, a2, a4 and so on, these all are 0. Okay, and what about these two? Likewise, W2 denote the set of all polynomials this is my representation, bi equal to 0 whenever I is odd, means b1 equal to b3 equal to b5 equal to b7 equal to dot 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 equal to 0, right? For the odd case it is 0, for the even case this is 0. Now we have to prove that Pf equal to W1 plus W2. Okay, what we have to prove? So we have to prove W1 plus W2 equal to Pf, right? Here Pf is my vector space and W1 intersection W2 equal to 0 polynomial, right? So students, I hope you can show it. This is your homework, and if you find any difficulty, then comment section is only for you. Write your comment, ask your doubts. Okay, so students, what is W1? So W1 is this form. Okay, f of x such that a(n)(xn), you can write it like that. Okay, construct the set yourself, right? Try it yourself, and if you have any difficulty, then don't worry, I am giving you the solution also in the next page. Okay, so see, just go through it at once, right? But before that you have to try yourself, right? So next, what it is in this is the set of matrices of m cross n. Define this W1 equal to this and this equal to this, so that this. Okay, so what we have to prove? We have to prove that this W1 plus W2 is equal to m of n cross n over f. Okay, and the second one, W1 intersection W2 equal to 0, right? So see, what is W1? So see, W1 is equal to this one, right? So it is a matrix of order m cross n. So we will try it by taking a square matrix, right? Then we will do it for this one, right? So see, at first we will check that for a matrix 3 cross 3, right? So see what it is saying. At first write it a1 a2 a1 3 a21 a22 a23, right? a31 a32 a33. So it is saying that whenever I is greater than, right, W1 equal to, right, whenever I is greater than j, means I is greater than j, I is greater than j means this. So see, here I is greater than j, right, means 2 1 3 1 3 2 means these 3. Then aij equal to 0 means this is equal to 0. Then what will be the matrix? It will be a11 a12 a13 a21 means 0, then a22, then a33, right? Then a31 0 a32 0, then a33, right? So this is my W1. And what about W2? W2 is this one, that if I is less than equal to j, then here are basically two conditions, that if I is equal to j and I is less than j, right? So see, if I is equal to j means a11, a22, a33 means this will be 0, all the diagonal elements are my 0, right? And what is it, I less than j means, see, I less than j, I less than j, so this will be 0, 0, 0, right? And what is this? This is my a21, a21, a31, a32, right? So this is my w1, this is my w2, right? So if we add them, then what will we get? w1 plus w2, wait, let me write it. If we add them, then we will get, see, this, okay? So basically we will get this matrix, right? So it will be equal to a11, a12, a13, a21, a22, a23, a31, a32, a33, right? So student, yes, see what it is. This is basically upper triangular matrix, right? So here W1 is nothing but the set of all upper triangular matrix, upper triangular matrix, and this is my lower triangular matrix. And students, see, since this diagonal is my also 0, right? So it is called strictly lower triangular matrix, right? So see, so we have proved that w1 plus w2 will be equal to the whole set m n cross n, right? Choose any, suppose this is my any element from m3 cross 3 over f, okay? So see, each element of m3 can be written as sum of these two subspaces. Now check intersection. So yes, you can choose here 0, 0, 0, 0, 0, and you can choose here 0, 0, 0 also, right? So you will get a 0 matrix as common. So yes, this is a direct sum of these two one, right? But students, see, here it is asking for order m cross n, but I am proved for 3 cross 3, right? So prove it for order m cross n. This is your homework, right? And if you find any difficulty, then don't worry, I have written here for you, right? And after that, if you find any difficulty, then comment, right? I will make you reply. Next, what it is saying? It is saying that let V denote the vector space consisting of all upper triangular n cross n matrices, and let W1 denote the subspace of V consisting of all diagonal element, right? So what is W1 and what is W2? See, here is W2. So W1 is defined as set of all upper triangular matrices, right? Sorry, V denote the vector space consisting of all upper triangular matrices. No, V is the set of all upper triangular matrices, right? This is my V, okay? And W1 denote the subspace of V. This is my W1, right? And this is the diagonal matrices, right? So W1 is my diagonal matrices. So students, what is the definition of diagonal matrices? So a matrix is called diagonal if no matter what is at its diagonal position, right? So in a matrix, it does not matter that what is there in the diagonal position, okay? Except diagonal, everyone should be 0. Except diagonal, every element should be 0, right? Then this kind of matrix is called diagonal, okay? So this will be 0 dot 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 0, right? And it will be a22, and similarly dot 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 ann, since this is a n cross n matrix, right? And similarly all of them will be 0, right? 0, 0, 0, 0, 0, 0 and 0, okay? So this is my diagonal matrix. Then what it is saying, W2 is equal to this one, right? I greater than equal to j equal to 0 means a11, a12, a13. See, I is greater than 0, no, a21, right? A31 means all of these entries are my 0, right? So write it. And see, for equality, this is also 0, means there are basically two conditions, I greater than j, I equal to 0, right? So all the diagonals are my 0, so it will be 0, right? Here is a12, a13 dot 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 a1n, right? Similarly, here it is 0, again diagonal is 0, right? And it will be a23 dot 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 a2n, right? And so on, all of them are my 0, this will be like that, right? And all of these are 0, right? Write it properly, this is my n cross n. Okay, so we get the w1 and w2. Now what we have to show, that v equal to w1 plus w2, right? So clearly you can see that if you add these two matrices, then definitely you will get the upper triangular matrix, right? Means all of them will be 0, this is my 0, right? So this will be my upper triangular matrix when we will add w1 plus w2, right? Do it. And what about w1 intersection w2? So you can see that 0 matrix is a diagonal matrix and 0 matrix is a this kind of matrix, so yes, 0 will be there in their intersection, right? So you can see that the questions are very easy, right? You just have to go at least once, right? Just solve at least once in your hand, only then you will be able to solve the questions in your examination. Okay, so see, this is for your semester level examination, right? So at first do it yourself and after that check it. Next, what it is saying, it is saying that let w1 is equal to this. Basically this is the set of all skew symmetric matrices, right? And this is my set of all symmetric matrices, right? So what we have to show, we have to show that this m n cross n is equal to w1 plus w2, right? So students, basically this is a standard result, right? This is a standard result. What is the result? See, I am writing here that every n cross n matrices can be written as the sum of symmetric and skew symmetric matrices, right? Every n cross n matrices can be written as the sum of symmetric and skew symmetric matrices, right? So now we are going to prove it. As first we will show the intersection condition, then we will show the sum condition. Okay, so students, see, at first this one, so we have to show that a 0 vector belongs to w1 intersection w2. So see the approach. Let, how we are going to prove it? See, let a belongs to w1 intersection w2, right? Now we have to show that this a is equal to 0, right? So for that, what will you do? So see, what we have that a belongs to w1 intersection w2. By set theory, what we will get? If we get that a belongs to w1 and a belongs to w2, right? Since a belongs to w1, so it will satisfy this condition, means a transpose is equal to minus a. And since a belongs to w2, so it will satisfy this condition, means a transpose is equal to a, right? Suppose this is my equation 1 and this is my equation 2, right? Now change the color. So from 1 and 2, what we get? From 1 and 2 we get that, see, a transpose equal to this, a transpose equal to this. What does it imply? That a will be equal to minus a, right? Which implies that a plus a equal to 0, right? We take it this side. Okay, what does it mean? It implies that 2a is equal to 0, it implies a equal to 0, right? So students, see, we took a matrix A from this set, right, and we get this A equal to 0. What does it imply? It imply W1 intersection W2 equal to 0. Can we write it? No. Why? Because we have not tried that what kind of A it is. Let W1 intersection W2 be arbitrary. Now this A represents all the matrices of this set. Yes, now we can write this. Yes, so the first condition has been satisfied, right? Now what about the second condition? So students, see, let me change the color. Which color? This color. Okay, so students, suppose this is a matrix A, right? Now we have to write it in the form of symmetric and skew symmetric. So now I am going to use a result, right, of matrices that see, I will prove it, don't worry. Suppose this is A plus A transpose, right, by 2 plus A minus A transpose by 2, right. Suppose this is my S and this is my T, right. So basically what I have done, that I have written A as the sum of these things, right. Now if we can show that this is my symmetric and this is my skew symmetric, right, then we have done. If this is symmetric and this is skew symmetric, then we can say that yes, A can be written as the sum of skew symmetric and symmetric matrices, right. So what we have to prove? Now we have to show that this is symmetric, right. So see students, I hope I am able to make you understand, right, and I advise you this thing and this thing, remember it, okay. You will get benefit in future, right, in your competitive level examination. Remember it, this is important. You can see the questions in NBHM ISI level, okay, CMI, ISI, TIFR. You can see the application of this result. So what is S? S is my A plus A transpose by 2, right. So students, see, if we take transpose, what is the meaning of transpose? Sorry, what is the meaning of symmetric? That if it satisfies this condition, means something transpose is equal to that thing, something transpose equal to that thing, right. So this is my something, I am taking transpose, right. So see, so what it will be? It will be A transpose, then A transpose of transpose by 2, right, and it will be equal to, students, see, anyone may be confused that how we are getting that, right. So see, this is the standard result, that this is the standard result in matrix theory, that A plus B transpose is always equal to A transpose plus B transpose. This condition holds in matrix, and from there we are getting, right, and we are using it here, okay. So see, so A transpose, this is plus, right. So A transpose is equal to A, see, A transpose plus A transpose of transpose, this is equal to A, right, and this is equal to 2, and this is equal to A plus A transpose by 2. So students, see, something transpose equal to that thing. What does it mean? That this thing is my symmetric, and this is equal to S, so this thing is my symmetric. So yes, this is symmetric. Similarly, we can show that this is my skew symmetric. So students, see, I am going to prove it again. I hope you are enjoying the lectures, right, and if you have any suggestion, then please, you are welcome, right. T by 2, okay. So A transpose is my equal to minus A, right, and A transpose of transpose, this is equal to my minus the transpose of transpose. What does it mean? If this is my transpose, right, so what will we get? This one, right. See, what was here? That here was A, right, we are taking a transpose of an element. Okay, let me erase it first. See, wait, what happened? Work. Wait, see, Okay, I understand. So see, what is here, that if you take transpose of something, right, then you are getting that thing with a minus, right? Something transpose equal to minus that thing, right? So what is here? A transpose, right? We are taking A transpose of transpose. So A transpose of transpose, what does it mean? That it will give minus plus the thing inside it, right? So A transpose. So we will get this one, right? So put it here, minus A transpose. A minus minus will be plus. Why? Because this is equal to minus A transpose, and this minus plus. This is equal to 2, right? And students, if you take common, right, if you take minus common, then what it will be? It will be equal to A minus A transpose by 2, right? So you can see that something transpose equal to minus that thing. So this is my skew symmetric, right? So finally we are able to show that this A can be written as the sum of symmetric and skew symmetric matrices. Hence, what does it mean? It means that it satisfies the both condition and this condition holds, right? So this completes our proof. And always remember this is a very important result, okay? You will see the application of it when I will solve the questions of NET, GATE, JAM, CSIR NET, etc. Okay, and at that time you will understand that how valuable these things are and how valuable this lecture and this content is, right? Next, so students, this is for your semester level examination, right? Just go through it. Now next, theorem. What it is saying? It is saying that let W1 and W2 be subspaces of a vector space V, then V is the direct sum of W1 and W2, right? Means V is the direct sum of this one, right? If and only if every vector V belongs to V can be expressed uniquely as V equal to x1 plus x2, right? When x1 is from W1 and x2 is from W2. So students, I have already explained it, right, in the beginning of this topic, okay? So now we have to prove that every vector can be written uniquely, okay? So see, basically this is a theorem, so we have to start like given that with the given data, right? So see, proof, right, given that, right? And what is the given data? Number one, that W1 and W2 are subspaces of V. W1 and W2 are subspaces. Let me write it, are subspaces of V, right? Now what is the second condition? That V equal to W1 plus W2, means V can be written as the direct product of W1 and W2. Now what we have to prove? What is our claim? That V can be expressed as x1 plus x2, right, such that x1 belongs to W1 and x2 belongs to W2, right? And this representation is unique. This is our claim. So students, as a mathematician, think that from here to here, how will you reach? By using your logic, by using the definition of subspace and by using the definition of direct sum, right? So let's see. I will advise you pause for 2 minutes, right, and think and try it yourself at first. At first try yourself, right? After that come back here and see the proof, okay? So see, students, see, from given condition what can we conclude? See, since V is a direct product of W1 W2, so from here what can we say? That yes, V is the direct sum of W1 plus W2, and the secondly we can say that yes, their intersection is equal to only 5 or only 0, sorry, not 5, only 0, right? So this is our given data right now. Okay, it was given and this is nothing but this thing. So 1 2 3, there is only 3 given data and 1 claim, right? So see, how can we approach? So students, see what we have to prove. We have to prove that this is unique, right? So let's write it at first. V equal to x1 plus x2, right? Let V equal to x1 plus x2, where x1 from W1 and x2 from W2, right? And it is true for all V, right? And right, for all V belongs to V, right? So V is from vector space, right? And since V is arbitrary, right, I am not writing arbitrary because I am written here for all, right? So this V represents all the elements of V, right? So an element of V means every element of V can be written as x1 plus x2, right? Now we have to prove that this is unique, right? So what we let us consider that this V can be also represented as V equal to y1 plus y2, right? It was given. Now we have to prove that this is unique, right? For that we are letting that there is another representation, right? Now we will check that whether is it true or not. So this is my equation 1, this is my equation 2, right? So from 1 and 2 we can say that yes, from 1 and 2 what we have, we get that, see, V equal to this one, V equal to this one, right? So this one will be equal to this one, so write it. From 1 and 2 what we get, we will get this one, right? Now rearrange it, take it this side, right? So x1 minus y1 will be equal to y2 minus, take x2 this side. Okay, students, see here x1 is from W1, right? And y1 is from W1, right? Why? Because we are letting here, sorry, I have not written here, y1 belongs to W1 and y2 belongs to W2, right? So see, and x2 belongs to W2 and y2 belongs to W2, right? So since x1 is from W1, y1 is from W1, and we know that W is a subspace, right? So this element also will be there, right? This is nothing but this is plus minus y1 equal to y2 plus minus of x2, right? So we are adding 2 elements, right? So students, you can see that this belongs to W1, right? Just write it. Let me change the color, right? So it implies that x1 minus y1 belongs to W1, right? And again you can see that this y2 minus x2 belongs to W1, right? This is not W1, this is W2. And students, give it a number, this one, right? This is my 3, right? So students, see this y2 minus x2 belongs to W2, right? And we know that from equation 3 we know that this y2, this one, okay, this y2 minus x2 is equal to x1 minus y1, right? This is y. So we can write that x1 minus y1 belongs to W2, right? How we get? See, x2 minus y2 belongs to W2 since W2 is a subspace, right? And we know that y2 minus x2 is equal to this one, so this one belongs to W2, right? So students, see, this is my equation 4, this is my equation, not equation, this is expression 4 and this is 5, right? So from condition 4 and 5 what we get? Wait, therefore from 4 and 5 we get, see, this belongs to W1 and this belongs to W2 also. What does it mean? It means that it will belongs to their intersection, right? We get x1 minus y1 belongs to W1 intersection W2, right? Why? Because this element is in W1 and this is also in W2, right? And students, see what is the given condition here. What it is, that since it is a direct sum, so in their intersection there will be only one element, and that is 0 element, right? So see, this belongs to this set, and we know that in this set there is only 0 element. What does it mean? It is equal to 0, right? Only then it will belong to this set, right? And if this is equal to 0, what does it imply? It will imply that x1 equal to y1, right? And if x1 is equal to y1, similarly we can show that x2 is equal to y2, right? If x1 is equal to y1 and x2 is equal to y2, right, then what will we get, right? If x1 is equal to y2, right, x1 is equal to y1, means y1 is equal to x1, so this y1 is nothing but x1. Similarly this y2 is nothing but x2, right? So see, this is the sum of two elements, right, of W1 and W2. So students, see what we get, that the new expression which we assumed was nothing but just the previous one, right? So what does it mean? That the representation is unique. If you take any other representation, right, then you will come here and here, okay, then you will take this, make equal, put it, you will get this one, right? So the representation is unique, okay, proved. So this is a very beautiful theorem, right? I hope you enjoy the proof, okay. So what is the second part? We have to let this one and we have to prove that this forms a direct space, right? So see on the next page. So at first write given that, this is my converse part, okay, converse. Given that, what is given? It is given that every vector can be expressed uniquely as this, okay. Wait, every vector of V can be expressed uniquely as V equal to x1 plus x2 such that x1 belongs to W1 and x2 belongs to W2, right? This is my given data. Now what is our claim? What we have to prove? We have to prove that V equal to W1 direct sum W2, right? So students, this is my given data and this is our claim. Now think as a mathematician that how can we reach from here to here, right? So student, basically we have to show two conditions, that intersection is 0 and V equal to W1 plus W2, right? So students, see what it is said, that every vector can be expressed uniquely as this, right? So since from the given data we are writing, since every vector V belongs to V can be written in the form V equal to x1 plus y1, x1 plus x2 such that x1 belongs to W1, x2 belongs to W2, right? See, it is mentioned that you can write every vector of V in the form of this, right? What does it mean? So obviously V will be equal to W1 plus W2, right? We don't need to check for it. Why? Because they have mentioned it in the question that yes, you can write. So yes, I have written. So the first condition has been satisfied. This is obvious, okay. Now what about the second one? So students, see, we have to prove, what is our claim is here, that we have to prove that 0 belongs to W1 intersection W2, right? So students, see how I am making the approach. Let Z belongs to W1 intersection W2, right? Be any element, right? See, be arbitrary, right? So what does it imply? It implies that Z will be in W1 and Z will be in W2 also, right? Since Z is in my W1, right? So we know that in every vector space there is a common element, right? In every subspace, 0 element must be there, right? So students, we can write this Z as Z equal to 0 plus Z, right? Where 0 belongs to W1, right? See, since this is my subspace, right? So I can write it like that: identity element plus Z equal to Z, right? Similarly, for this case we can write that Z is equal to Z plus 0, where 0 belongs to W2, right? So students, see what we have done. We have taken an element, see, I am writing, we have taken an element Z, right? And see what it is. Here Z is an element of W1, right? Sorry, Z is an element of W2. Here this belongs to W2 and this belongs to W1, right? So see, I got an element, right? And this belongs to my W1. This 0 is my from W1 and this 0 is my from W2. So we are getting an element, right? We can write it like that: element of W1 plus element of W2, right? Similarly, we can write it element of W1, element of W2. I hope till now everything is clear. Just take a pause and think about it, what I have said. See, we have assumed that Z belongs to this one, right? If Z belongs to this one, then Z will be in W1 and Z will be in W2 also by set theory. I hope till now is clear. And we know that every vector space there is 0 element, right? And so here will be a 0 element, here will be a 0 element, right? Now we are taking the Z as a element of W1, right? We are taking Z as an element of W1, right? And we are taking 0 from this set, right? So we are taking an element of W1 and we are taking an element of W2, right? And we are getting it Z, right? Similarly, in this case, what we did, we are taking 0 element from this set, right? And an element Z from this set. And see, I am writing it here. Okay, so see, basically we are getting two expressions, right? So write here, we can represent Z as two sum of subspaces, right? So here we can represent Z in two ways, right? Represent as two ways of sum of subspaces, right? So when it happen, it will happen only when Z is equal to 0. Why? Because it is said, see, what is the given data, that B can be expressed uniquely as, why? Because B can be expressed uniquely, right? And this condition holds only when Z is equal to 0. Hence, this Z is nothing but 0. It implies 0 belongs to W1 intersection W2. Hence proved. Okay, I hope you understand it. If not, then comment, ask your doubt, right? I will make you reply. So I think I am able to make you clear each and everything. Don't worry, I am going to give the proof. See, this is your proof, right? Go through it at least once. It will be helpful for your semester examination. Next, students, modular law. This is a very beautiful theorem. Okay, beautiful theorem. And student, I want that please do it yourself, right? I am not going to make any help for this proof. Okay, why? Because I have solved each and every questions, almost each and every questions, and I have proved all the theorems, right? So what is the way to prove, how to write the proof, and how to approach the proof, right? You know everything. Okay, so based on that knowledge, try yourself, right? I hope you will do it, right? And let me know that whether you are able to do it or not in the comment section. Okay, write modular law and then make a comment. Okay, so next, okay students, for your convenience I have given the proof here, okay, and with a note, just read it at yourself. But student, I will suggest don't do it. Okay, don't read it at first. Try yourself, take 1 to 2 days, okay, and try yourself. After that, come here. Okay, this is my suggestion to you, my request to you, and my advice to you. Okay, so students, and also solve some problems based on this theorem. Okay, and I am not going to give the solution of it here. Okay, if you find difficulty, comment, right, and raise your doubts there. I will make you reply. Okay, so next, so finally we have learned a lot of things about vector spaces and subspaces, right? So this is the time to check your knowledge, that whether you are ready for it not. Okay, so students, I have included here 2 tests, okay, where +2 is for correct answer, -2 is for means -1 for false answer or incorrect answer, and -4 for not attempting any question. Okay, so I hope that you are ready to give the quiz, and if not, then pause the video. Okay, go back to your slides, to your notes. Okay, revise them carefully. Okay, so that you can score a good marks, and let me know the score in comment box, right? So see students, this is your first test, right? This is your questions. What are the patterns? True false pattern. Write the justification here, right? Only then you will be able to get 2 marks, and if you make a false, then it will be -1, and if you don't attempt any question, it will be -4. This is your test 1. Okay, just mention your marks in comment section, right? Just comment like that, test 1, then obtain marks equal to your marks. Okay, and see, this is your second test, test 2, right? Comment like test 2, then obtain marks equal to your marks. Okay, so be honest in your test. Okay, because I am not there to see that whether are you cheating or not, right? So be honest to yourself. Okay, this is very important. Good. So next, so finally we have completed the lecture, and congratulations students, finally we are ready to see the summary of this lecture, right? See, so what is the summary of this lecture? So students, at first we have seen the introduction, then we have seen the application, then we have seen the definition of subspaces, then we have solved lot of problems, right, based on semester exams and for NET, GATE, JAM also, right? and then we have done some theorems. Okay, I am writing here, wait. Solve many problems for semester examination, fourth semester and NET, GATE, JAM. Okay, the questions I have included in these slides are basically from NET, GATE and JAM. Okay, not all of them, but few of them, even you can say that many of them. Okay, we have done this, right? Then we have learned the concept of direct sum, right? Then we have solved a lot of problems on it, and then we have done the modular law. Okay, and then we have seen some problems on it, then we have seen the quiz. Okay, so this was my summary of this lecture. Okay, and students, one more thing I want to conclude here. What? See, what was the definition of subspace? That this is a vector space, right? And this is my subset W. Okay, and this forms a subspace when it satisfies three conditions: that zero vector belongs to W, secondly it should be closed under addition, and the third one, it should be closed under scalar multiplication, right? And students, as we know that mathematicians are lazy persons, right? So you know what they tried? They have tried to make it short. Okay, they have tried to make this definition more short, right? And they got an idea. What was the idea? They have seen that if any set W satisfies this condition, right? What condition? Suppose A alpha plus B beta belongs to W. If a set satisfies this condition, that if in a set A alpha plus B beta belongs to W, then this W is a subspace. Okay, so students, see what it is. This is nothing but just the shortcut of all of this. If you choose A equal to 0, B equal to 0, right, then what will happen? Then this will be equal to 0 and 0 belongs to W, right? Hence the first condition satisfied. If you choose A equal to 1, B equal to 1, then it will be alpha plus beta which belongs to W. Second condition hold. What about the third condition? If you choose A equal to 1 and B equal to 0, what does it mean? It means that, sorry, if you choose B equal to 0, then what will happen? It will be equal to A alpha belongs to W, where A is from scalar, right? So students, these are A and B are my from scalars, okay, and alpha beta are my vectors. So see students, we can merge these conditions into this single result, but I advise you, don't use this thing. Okay, you may use, right, you may think that yeah, this is one condition, I can do it very easily, but for your understanding this is very important. Okay, so I will suggest you to go with it as I have teach you. Okay, so next, finally we are ready to see the references of this lecture, that in this lecture which books I have used, right? So students, you will be happy to know that in this lecture I have covered all of 3 books, right? I have covered all of these books. And students, if you are a beginner and you don't know anything about linear algebra, then you will be happy to know that this is the basic book of linear algebra in the market. Okay, so if you are a beginner, then I will suggest you to go with this book, and this book is a high level book, a standard book for linear algebra, right? Friedberg. Okay, you can go with it, but I will suggest that if you don't know anything, then go with this. After learning the concept, move to it, right? And if you want to prepare for your competitive level examination like IIT JAM, CSIR NET or GATE or TIFR, this kind of examination, then this is the best book in the market. Okay, what it is? This is the best book in the market. This is the best book in the market. Okay, why it is best? Because in this book all the results and all the properties, right, and all the shortcut tricks are mentioned, right, in a place, and you can see the pyq questions of netgate here also. Okay, so you can get it. But student, you will be more happy to know that after completing this lecture, if you are watching this lecture till now, right, then I am very happy to say you that you are ready to read all of these three books. Not even ready to read, but you have already mastered all of these three books. Okay, so I hope you enjoyed the lecture. So finally, thank you for watching the lecture, and thank you for your all of the attentions. And students, stay curious, stay healthy, and read and read. Okay, just learn the concept from the basic. Okay, just try to connect each and everything, learn the mathematics, learn the logic, and learn that how to use them in the real life. Okay, so students, see what I have written here. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding, right? By David Hilbert. He was a great mathematician. You will read a lot of things from him in future. Okay, so students, all the best for your mathematical journey, and see you soon in the next lecture. Bye bye.